Your USDC, in this case, cannot be prioritized over your Mudang coin. And so the solution to this is state archival. So unfortunately, we're going to have to kiss our mascot goodbye. So with state archival, each piece of ledger state is given a TTL value. Now, when this TTL can be extended by what we call rent payments. Now, what the rent payment system does is it essentially reconciles the fee system, where we have a reoccurring rent cost to now match this, or a reoccurring rent fee to match this reoccurring cost that the storage puts on the network. Now, after a TTL expires, the entry is archived and actually deleted from validator databases, freeing up these resources. And any transaction that touches an archived piece of information immediately and atomically fails. But don't worry, even if an entry has been archived and deleted, it can always be restored back to the ledger and used again. To do this, we store all archived state off-chain in a series of immutable Merkle tries. Then, if you want to reuse that state again and restore it, you can do so by providing a Merkle-style proof of existence to validators. Now, to demonstrate how this works, let me give an example as to how we construct these archival Merkle tries. So here what I have is an example of a data or the validator state at the very beginning of state archival before we've turned it on. And you can see here that we have a validator on-chain with a bunch of entries that have live TTLs and an empty archive off-chain. Now, some time will pass, and eventually these TTLs will expire. And so we see the first entry expires. What we're going to do is we're going to remove this entry from the live ledger state and put it in what we call the hot archive. This is a Merkle try stored locally on validator databases. And so we haven't actually deleted the expired or archived state yet from validators. It's still maintained locally for now. And so we have this Merkle try here. Some more time will pass. Another entry will become archived, be removed from the live state, and add to this hot archive. Now, at this point, the hot archive is considered full. And so what we're going to do is persist just the Merkle root of that tree, and then delete the rest of that Merkle try, and now publish it to the off-chain archive database. And so what we're left with is a validator that only maintains the Merkle root of this archive try, but not the actual archive state. This process then continues recursively, and you can imagine that over time, the validators store many Merkle roots, and then we have many Merkle tries in the off-chain archive. So this is the high-level design. Now I'd like to talk about a couple of the particular attacks that this exposes and how we defend against them, beginning first with what we call the double restore attack. So in the double restore attack, consider that I'm an attacker that has a 10 USDC balance, and I'm going to allow this to become archived as TTL expires. So here we have an image of what the archival try looks like. I have my 10 USDC balance in the first archive try 0 that's off-chain. So I'm going to then restore my 10 USDC by providing a proof of inclusion to this Merkle try to the validator. Now, because the validators maintain the Merkle root, they can ensure the integrity of this entry and actually prove that the 10 USDC really does exist. So it gets restored. Now, I, the attacker, will spend 5 of my recently restored USDC and allow the new entry, which now only has a 5 USDC balance, to become archived again. And so with this new 5 USDC value will become archived, but it will be in the next new archival try. Remember, because each of these Merkle tries is immutable, we can't actually remove the 10 USDC leaf once it's restored. And now I, as the attacker, have a new up-to-date 5 USDC balance in archive try 1 and an outdated 10 USDC balance in the older try. And what I'm going to do is, instead of restoring the new balance like I should, I am going to restore the outdated 10 USDC balance, and it will now essentially result in a double spend. Now, the validators have no way of knowing that this is an incorrect value because a valid Merkle proof of inclusion does exist. And so to defend against the double restore, what we're going to do is we're going to require a more complicated proof system. And so just like before, if I want to restore an entry that's currently archived in try n, I will have to include a proof of inclusion for try n. Additionally, I'll have to provide a proof of non-inclusion for the given key in every newer try. What this does is it enforces that only the newest version of an entry can be restored at any given time. Now, this does come with one unfortunate performance caveat, and that is, in order to prevent against a double restore, we need to write both archived entries as well as deleted keys to the archive. You can imagine if I restore my 10 USDC, spend it all such that the key is deleted, I don't want to be able to restore that 10 USDC balance a second time in double spend, so you have to record both the archived entries themselves as well as the keys of deleted entries so that you have protections via this proof of non-inclusion property. The second attempt, or the second attack, is malicious archival. And so in this scenario, the attacker is going to take out a loan, and that loan is going to have some token balance as collateral. Now, as the attacker, I'm going to purposefully let my collateral become archived such that its TTL expires. And I'm going to then default on my loan. Now, the loan provider actually cannot collect that collateralized material because it's in the archive, and they don't have the private key in order to restore that entry. And so to prevent this type of attack, what we're going to do is consider that all TTL extensions and restorations do not require private keys, state ownership, or any sort of authorization. Now, this is generally fine. It has no drawbacks. There is really no negative impact to having an arbitrary member extend the TTL or restore an entry they don't own. There's nothing negative this can do, and it allows the liquidator, in our case, to restore someone else's state that they defaulted on. The only issue with this is that smart contracts cannot use the TTL value for security enforcement because any arbitrary party can extend that TTL. So you can't use TTL to enforce like a signature expiration in this case. That's fine because there's much other design paradigms that smart contracts can use to enforce these properties. The final attack I want to consider is what's called the double nonce attack. And so in this attack, I'm going to have a victim that creates a nonce, a deterministic key, and that nonce is going to become archived. Now, what the attacker is going to do is instead of restoring the nonce value that does exist in the archive, it's instead going to recreate the nonce at the exact same key, but with a different value. Now, the issue is the validators have no way of actually preventing this because the validators don't know what keys exist in the archive. And what the result is that this is an eclipse attack, where the attacker has a valid nonce live on the ledger state that actually eclipses the legitimate value stored off-chain in the archive. And so to prevent this, what we're going to do is kind of like we required proofs of non-existence in restoration cases, we are also going to require proofs of non-existence when creating a new key for the first time. In particular, when creating a key for the first time, you'll have to prove that that key does not exist in every single try in the archive. Obviously, this is really inefficient and not a very good situation for the end user, so we're actually going to optimize away the proofs of non-existence. And so for each Merkle try, in addition to holding the root node persistently, validators are also going to store a binary fuse filter set of all the archive keys. A binary fuse filter is just an optimized Bloom filter. Now, the binary fuse filter does produce a false positive because it's a probabilistic set, but the properties of the binary fuse filter are such that it favors safety over liveness. What this means is that a false positive will sometimes not allow restoration of a valid entry, but it will never allow restoration of an invalid proof. Now, in the event of a false positive, you can always provide the real full proof of non-existence to override the false positive such that liveness can still be maintained. Now, the reason we use binary fuse filters is that they're super efficient, and this has essentially zero storage overhead compared to the space savings we would have if we stored all of these archive keys as a traditional set. So where are we at? This is not a theoretical work. We've actually implemented this. So earlier in February, we launched the interface for smart contracts on mainnet, and currently the full proof system with entry deletion is code complete and is expected to hit mainnet later in 2025. Thank you very much. If you have questions, you can, of course, follow me on GitHub or ask me on the Discord. Thank you very much.
Thank you very much. Next up, we have Robert presenting Hacking on Solana.
Can you hear me? Ah, nice, okay. So, good morning. Thanks for waking up so early. I know it's hard at a conference. So, I will be presenting today about Solana, and specifically hacking on Solana. Briefly on my background, I'm a 2.5-year Solana auditor. Previously, I worked at Neodyme, and now I'm currently starting my own security and research company focused on Solana. It's called Accretion. And yeah, I have 10 minutes to talk to you today. I think it's not enough time to explain Solana. So I think I also don't want to do like a common bugs type of thing, because you can find that easily online if you're interested in these kind of things. So I want to try something else. Specifically, I want to spark the interest of some EVM people to hack on Solana maybe. And obviously, the favorite bug class of Ethereum people is Reentrancy. And what better way to introduce you all to Solana than through Reentrancy, right? So I probably don't have to explain to you what Reentrancy is, because you know it better than me as a Solana guy, right? So the gist of it, though, is that we have like a contract, and that contract has a function that can be called, and during that function call, it might perform some kind of callback to the caller through maybe a send. And in that callback, the contract is in an immediate state, and the attacker can abuse this immediate state to call back into the victim contract and do some action twice maybe, or some other things. Well, and I'm here to talk about Reentrancy on Solana, right? And the question obviously is, does it exist on Solana? You probably heard of these things if you have ever researched this. That, yeah, let's just read it out. Like calling a program from an intermediate state, blah blah blah. In this case, reentry is limited by a simple self-recursion and limited depth. Okay. Second, Solana's execution model rules out a large category of attacks such as reentrancy. Oh, okay. Note that reentrancy is inherently limited on Solana due to its execution model. The Solana runtime restricts CPIs to a maximum depth of 4 and enforces strict account rules, blah, blah, blah. Okay. Solana considered more secure? Okay, interesting. Because the execution model disallows reentrancy? Okay. Apparently, I got something wrong and it's not possible on Solana. So sorry, I guess. But actually, if you think about it and read this in detail, you realize, okay, it's only self-reentrancy that's allowed on Solana. So what's disallowed is calling another program and then calling back to our original program. And stack depth, so we cannot call another program and then call another program and call another program and call another program, because there would be 5 programs being called. The stack depth is limited to 4 on Solana. And somehow these articles drew the conclusion that this means there's no reentrancy bugs. And yeah, I think this is wrong. And it simply works like this. The reentrancy type of bug that is disallowed on Solana is specifically the one that we saw before, which is like this normal reentrancy where the hacker calls the contract, the contract calls back to the hacker. So far it would work. And the hacker then calls the contract again. At this point, the runtime sees, oh, we have another contract call that already exists on the stack, and it's not a self-reentrancy. So we're going to abort this whole transaction. However, what works on Solana is the second case where the contract just calls itself. So the hacker calls the contract, and the contract calls itself. So you might think, okay, when would this ever happen? It's kind of weird architecture. So specifically, our plan would be obviously to have this. The hacker calls a contract, and the contract calls itself. Specifically, as a hacker, we probably want to make the contract call itself in an unexpected way if we want to exploit a reentrancy, right? So we have to look for contracts that we can tell how they can call something else. So specifically more like this. The contract might expect to call another contract. So what kind of contract does this kind of thing? If you think about it, actually there's a lot of contracts that do this. First of all, multisig. So multisig works by you proposing some instructions, and then this contract executing these instructions on behalf of a group of people. The same as a DAO, practically almost the same as a multisig. Then there's a virtual machine. I'll explain it later. And I think yesterday we had a talk that explained that letting bridges call arbitrary functions might be dangerous because also on Solana it could have self-reentrancy. And flash loans also might allow you to call arbitrary functions. So actually there's a lot of candidates for this kind of bug. So I have an example for you. So first of all, a multisig self-reentrancy. How would this look specifically? So so multisig simplified has a couple of operations that you can do. You can propose a new instruction or proposal, and people can vote on it in the multisig, approve it, reject it, and maybe they can also revoke once they have approved a proposal and it hasn't been executed yet. They can revoke their approval. Maybe something changed in the surrounding prerequisites that they thought. So a normal, and you can execute it. So in a normal operation, a multisig would like someone be proposing an instruction, then everyone signs on it, and then the last person executes this instruction. Right? So far, so easy. And I've also drawn this up as a little flowchart. The proposal lifecycle specifically. So first of all, we have a new proposal that's being created. Then people start voting on it, and it's voted until the threshold is kind of met. And at any point, people can like withdraw their votes again. And when the threshold is met, the proposal becomes executable. And once it's executable, it can only be canceled or executed. Right? Those are kind of all the state transitions here. And now let's inspect a vulnerable execution function. So this would be the execution of the proposal once it's approved. And this case would be a vulnerable implementation, for example. So we first check the proposal state. Is this proposal executable? Then we just execute all the instructions in this proposal by adding our multisig signature to the instruction and then executing it. And then lastly, we mark the proposal executed. Simple, right? And I think if you're an Ethereum researcher, you should have spotted already the mistake here that we are doing checks and then interactions and then effects kind of pattern. Obviously, we want to have our effects before the interactions. So it's a classic candidate for reentrancy. The exploit would look like this. First, we just propose two instructions. One is to transfer one sol. Second one is Bob, who's a multisig member, is going to revoke his vote. Only Bob will be able to execute this proposal. So this is kind of a weird case because the multisig will add its signature to these instructions, but Bob can also add his signature. So that's why the multisig can revoke Bob's vote. So let's think what happens. The proposal is in a state of being executable. That's our starting point here. Bob starts execution of the proposal. The proposal state is checked. It's executable, so the execution can proceed. Then one sol is transferred, and then Bob's vote is revoked. That's the second instruction of the multisig proposal. And the proposal changes because one vote has been revoked into the state of being cancelled. And then the execution ends, and suddenly the proposal changes into the state of being executed. So we have suddenly a weird state change that goes from executable, and during the executing node, we suddenly change into the cancel state. And then after the cancel state, we jump into the executed state. So we have like invalid state transitions and kind of unexpected behavior. So that's the kind of bug here. Now you might think, okay, it's a weird bug. I don't know if this has any real impact. It depends a bit on the implementation details. If you implement it in a certain way where you don't, like you do effects first and the interactions later, but you don't write your effects to chain, which often happens on Solana if you're an experienced developer, then you might end up with the proposal being canceled at the end, even though it has been executed. So that would be obvious bug. Another issue would be that events would be emitted for cancellation and for execution. So it might confuse your front ends. So worst case, your front end shows this proposal as cancelled even though it's executed. And yeah, if there was no cancel state but a voting state that we're going back to when we revoke a vote, we might even be able to execute the same proposal multiple times. So yeah, the counter argument for this one is obviously that everyone sees what they're voting on, so it's kind of a weird bug. We classified this as low when we reported this, but it's still a very interesting kind of bug pattern. I have little time, so I'll go through this quickly. There was a second example with a critical impact. There's an EVM on Solana, which simply means EVM fully implemented as Solana instructions running the EVM. So Ethereum contracts, Ethereum accounts, and so on are encoded as Solana accounts, and they can mostly interact with each other, with other Ethereum accounts on Solana. It's not the Ethereum chain, it's like a different chain that's like Ethereum, but running on top of Solana. So it kind of looks like this. These EVM contracts interact with each other mostly, but they added a new precompile contract, yeah, which allows these Ethereum VM contracts to call Solana. So to call to the outside world of this virtual machine. It's like you run a VM on your computer, which like has a Windows machine, and this Windows machine can just call your Mac to the outside. And in this, we had like a reentrancy bug where these EVM contracts wouldn't just call any contract on the whole Solana blockchain. They would call this specific EVM contract that's implementing this EVM and re-enter into a different contract. And this would be like a re-entrancy through like a host escape kind of thing. And this led essentially to the issue that we could double spend any ERC20, or it would like defy constraints like static calls. We could make them non-static. Yeah. So yeah, that was a critical issue. Yeah, other vulnerable contract types, as I said, DAOs, pretty much the same as multisigs, bridges, if they can call arbitrary contracts, it can be dangerous if they can call themselves. Flash loans, I haven't seen a vulnerable implementation for flash loans yet, but there's not many flash loans on Solana, so they might be vulnerable as well. But essentially what I'm saying is for every one of these types of contracts, we found the same self-reentrancy bug on Solana, simply because most Solana devs think there's no reentrancy on Solana. Yeah, how to fix these? It's actually kind of easy. You use this checks effects interactions pattern correctly. You make sure that you write your effects to chain before you call your interactions. Secondly, you can enforce that all your critical accounts are only passed read-only when you do your interactions. And lastly, you just forbid self-reentrancy. So every time someone tries to call another instruction, you check, are we calling our own program? Or you just disallow certain instructions from being called by doing introspection. All right, thank you. That was my talk. The takeaway, self-reentrancy exists on Solana, and you can find me here. Yeah, thank you.
So while we wait for the next speaker to come up, I have a question. So you talked mostly about self-reentrancy in Solana. We have another family of reentrancy attack, which is cross-reentrancy, where you have multiple contracts that needs to stay in sync. Do Solana have any protection against that, or is that another attack vector?
So you mean it's the same program that just has multiple subprograms? I had exactly another bug like this for you for this talk, but removed it because I thought it's not self-reentrancy. But yeah, I had it like this exists as well, because you're calling a different program technically, right?
Perfect. Thank you very much.
Yeah.
So our next speaker is, I'm sorry if I'm pronouncing it incorrectly, it's Thibault, talking about the challenges of non-custodian embedded wallet. Thank you.
Can you hear me okay? Yeah. Yeah, so I'm Thibaut, and today I'm going to talk about embedded wallet security. So what is an embedded wallet? The goal of embedded wallet product is to improve the Web3 onboarding experience, to like remove the friction of having to write down a list of words and like secure it in order to secure your funds, and instead to like get closer to what we have in Web 2, which is you can create a wallet by a click of a button, and you can like recover your account, recover your wallet if you lose your credential. But we still want to have the Web3 guarantees, which is like ownership, creating non-custodial wallet, and decentralized trust. So in terms of UI, we start to see more and more on decentralized application. So it's like whenever you click the like usual Connect Wallet button, you have like your MetaMask, Open Wallet, Wallet Connect experience. And then we start to see like enter your email to create an embedded wallet, or like just scan your face, scan your fingerprint, and you're gonna be able to create a wallet. So that's the experience that you're exposed to when you go through the embedded wallet flow. So how is it implemented? Most of the time for the decentralized trust, you have some cryptographic protocol like Shamir secret sharing or multi-party computation, where the private key doesn't live in one place, but instead you have multiple key shares that are used to perform a valid signature. And we also see like more and more passkeys that are used in order to create embedded wallets. So for ownership, whenever you have like Shamir secret sharing or multi-party computation, I mean, not always, but usually you have like one key share that is pushed on the client side and that lives on the browser local storage. Another type of implementation that we see is you have like the on-chain private key that is decoupled from the credential that you use in order to interact with your wallet, and that creates like a dual security layer. We also see a mix of the two, where you have like some client credentials that does not represent the on-chain private key, but that are used to unlock some specific on-chain operation that usually requires some like specific core blockchain protocol. Some support at the blockchain level. The Stellar folks are doing some great things about that, so you should talk with them if you want to learn more about it. So how does that look? Usually when you have like the embedded wallet experience, you have three parties. You have the clients that interact with the dApp, and then whenever you click like the Connect Wallet button, you're gonna interact with the embedded wallet provider, which is another party. So as a user, you're gonna authenticate to the dApp. It's usually like a standard Web 2 authentication. And whenever you click the Connect Wallet button, you're gonna, like the user experience of the embedded wallet is gonna be loaded through an iframe or through a new window. And you're going to be able like to enter your email, authenticate with the embedded wallet provider, and then create a wallet, and you're going to have a local share that is generated on your local browser, and then you can leverage that to perform a signature. In addition to that, usually we see an implementation of another flow at the same time, which is a recovery flow implementation. And so it's used to like recover access to your wallet in case you lose your credential, or in case you like change device. So like if you go from like desktop to mobile, since you have a share that is like generated locally, when you go to another device, you don't have this share anymore, so you need a way to like recover access to your wallet. So how is it done? What we've seen in production is that during the wallet creation, you have the embedded wallet provider that's going to share the authentication token with our decentralized application. This will usually be set as a cookie. And so whenever you change a device, you're going to authenticate with a decentralized application, and then the decentralized application is going to return the embedded wallet authentication token. That's fine. You're going to use this token to authenticate with a wallet provider, and then you'll be able to like generate a new, perform a key share refresh and generate a new shares, and so get access back to your wallet. Okay, that looks fine, but if it's not done properly, this can create some issue. So as I said, you have two steps. You have like the embedded wallet provider that's going to share the authentication token with a decentralized application. And by the way, can you see all the text? Oh yeah, okay, that's fine. And then you as a client, you're going to use this authentication token to authenticate with the embedded wallet provider, and then perform a key refresh and get back into your wallet. So if it's done just like this, the first problem is that the embedded wallet provider is going to share an authentication token with a decentralized application. And this authentication token usually, in some implementation, lives as a cookie under the dApp domain. And so then this cookie can be, and we've seen that in production, sometimes it's the only thing that is needed in order to perform the key refresh operation, so to authenticate with the wallet provider and perform a key refresh operation. So in other words, that means that the security of your on-chain private key is as strong as the security of your authentication token. So that's the first problem. The second problem is that this authentication token is shared with a decentralized application. So in other words, the decentralized application has access to all the secrets that is needed in order to recover your on-chain private key. So they become, sometimes without even knowing it, like a custodian of your wallet, because they can just access your private key. Also, cookies are notoriously very difficult to secure. They can live on different data stores under your infrastructure, Sentry, Datadog, and all of that. And so remember, this now lives under the decentralized application infrastructure, and so it's difficult to secure, it's difficult to understand who has access to it. So putting all of that together, I was able to write a simple script that takes as the input this authentication token that now you get whenever you authenticate to the decentralized application. And you can just pass that to this script. This script is going to make few API calls to the wallet provider, and then it's going to recover your private key. OK. So now you may wonder, this experience looks cool, but how do I know if I'm interacting with a secure system or not? So you actually have a very simple way of checking that. Is whenever you're exposed on a decentralized application to the embedded wallet experience, you can just open your console under the application tab. So you will usually see multiple storage that are dedicated to the dApp. That's fine. You don't have to touch those. And then you will see some local storage that belongs to the embedded wallet provider, so under the embedded wallet provider domain, cookie and storage. So what you want to do is you want to clear those storage. So you simulate that you change device or that you don't have the authentication token anymore. Then you just refresh the page. And if you see that the wallet is loaded again without you as a user having to input any secret, that means that the dApp has all the information that is needed to recover access to your wallet without any information from you. And so that's a problem. You're not interacting with a secure implementation. So now if you ever want to develop an embedded wallet experience, my advice for a secure implementation is two things. The first thing is to leverage as much as possible public key cryptography. So you want the client to have a private key. It's not necessarily linked to the on-chain private key, but as a private key, and you as an embedded wallet provider, you only have the public key, and you only use this public key to validate authentication. We've seen some embedded wallet provider using TOTP to secure access to their system. That's not advised because TOTP is based on a shared secret. And so that means the embedded wallet provider has all the information that they need to like fake access to your wallet. And you won't be able to prove that it's not you that access your wallet because this is based on a shared secret. So always use public key cryptography so that only the client can perform some signature to authenticate to your system. Like WebAuthn and passkey, again, are great implementation of that. And also another advice is to not expose the on-chain private key inside the client, like browser local storage, because then when you lose your device or when you go from one device to another, you need to perform a key refresh operation. That's a very sensitive operation. So advice would be to use a credential to decouple the security of the credential from the security of the on-chain private key. OK, that's it. Thank you very much. What we can say is that when we look into that, we encounter various flawed operations in production. We reported the issue to like the wallet provider each time. And so we've seen some mitigation that have been deployed following our report, so that's great, but we still have some insecure implementation in production. And so one last thing is I'm talking with a lot of people that perform like smart contract security audits, security firms that are like dedicated to smart contracts. There is a lot of things to do on the infrastructure side as well, and all these like off-chain systems that interact with the blockchain. And yeah, there is a lot of like improvements that can be done and things to do. So don't hesitate to go look around that because that's an interesting area as well. Thank you very much.
Thank you, Thibaut, for sharing the dark arts of embedded wallets. Next up, we have Carlos from Forta talking about AI-driven detection and prevention of malicious blockchain transaction.
Great. Awesome. Good morning, everyone. Thanks for coming instead of staying sleeping. I really appreciate that. I know it's hard because it's 9 a.m., but really appreciate it. I'm Carlos. I'm the head of AI at the Forta Foundation. And I'm going to be explaining to you today how we are using AI to actually prevent malicious transactions. And yeah, in blockchain, I know AI, blockchain, I'm a big fan of saying these keywords. I promise there is only one more over the presentation, but it's going to be fine. So first of all, I want to give you a little bit of context of, because now I'm talking AI for prevention, but Forta started a couple of years ago with monitoring. So we started using machine learning to analyze blockchain activity. And we were looking at how a particular address was funded, the smart contracts they were deploying, and we were using machine learning in several different flavors to be able to detect when something was going to be attacked. But we were doing monitoring, right? Which means that we were finding that someone was potentially an attacker, and we were saying, you have an attacker here. But that's it, right? And that's not so enticing. It's not so interesting because, yeah, OK, I know that's an attacker, but I don't have any of these tools to actually stop this attack. Today, we are moving a little bit forward, and instead of just using this previous part that we were commenting of, we are looking at funding, we are looking at the smart contract that they are deploying, we are just directly screening the transactions themselves to try to identify whether a transaction is actually performing an attack or not. One of the things about detection, especially in these last couple of years, is a lot of people have been working on this thing, and detection methods have been gotten much better. And a lot of attacks that before we were not able to detect, now we are able to detect before they actually incur into any losses, right? But we are able to detect does not mean that we are able to stop them. And even in cases when we can see an attack and we say, like, OK, this is coming, you might even start losing some of the funds because like a couple of transactions already went through and you were a little bit too late. Plus, there is the problem of there is not a very strong mechanism on what to do to actually stop these attack transactions, right? Because you can stop your protocol, but then it comes with a lot of other problems. People cannot do like normal operations, and you are just like blocking completely, and it's like a very extreme measure. So we think that there is a better way of doing that, and this is what we are introducing as Forta Firewall, which mostly what it's doing, it's like it's looking at the transactions from a stateless point of view, and this is something that I'm going to spend a lot of time afterwards because I think it's really interesting, and it's really important in order to be able to stop transactions. And this system is actually able to block these transactions before they are happening. We are not talking about pausing the protocol. We are not talking about further influence, that literally just stopping the transaction itself, that it's an attack transaction. So there is no other problem to operations other than you are not losing your funds. That sounds amazing, right? Great. So now let me give you some more information on, I have stateless here. I'm going to explain why I mean by stateless at this point. And I'm going to also explain a little bit to you how to create these AI systems and what to do with them, what's the process to improve them, how to validate them, and so on and so forth. So great. By stateless, now imagine that we are looking at a transaction. And we are just looking at a transaction, right? And we want to identify whether that transaction is an attack or not. Like, is it behaving in a different way how it's supposed to be, and someone is gaining money or funds or whatever in an illicit way? Yes, then we stop it. Easy, right? Well, not so much, otherwise we would have already been doing it, like and no one would lose anything. But let's look at the transaction itself. What do we have there? We have what we are using to generate this transaction, which is like who is sending the transaction, right? Where it is being sent, and what is being sent. So the data and the state of the chain, like you need the block number just to have an idea of how things are there. OK, that's your input. You have nothing else. Then what you can do is, using that information, since it's deterministic, you can simulate your transaction. And then on top of having the from, the to, and the input data, you would get the logs of what actually happened in the transaction and the traces. So who is interacting with who, like who is sending like whatever delegate call to whoever other contract, and all that information. And that's it. That's all the information that we have, right? It's quite different to how a normal person right now, a security researcher, would go into a transaction and identify, OK, this is an attack, or this is not an attack. We are just looking at the transaction. And actually, in my opinion, this one has a little bit of a problem also, because we don't necessarily want to stop people just because of who they are or who they interacted with to actually stop things, right? So just because you are a person that was interacting at some point with Tornado Cash doesn't mean that what you are doing in this particular moment is actually legit, and you just want to be completely anonymous. You don't have like any malicious intent. So just the fact that you are funded by one of these mixers doesn't mean that necessarily you are going to have this illicit content, right? So the from and the to, even though we are using them as flags because it's a lot of valuable information to know within the interaction who actually started the transaction, right? Like we know that a certain address actually is the one that is doing this call to this other address, but we don't have any extra context about that address. We just know that this is the address that initiated the transaction, and that's it. We don't know anything about it. So this is what we mean by stateless. Like each transaction is stateless, is completely independent on anything that has happened before. And this is something very interesting, because let's compare it to how a stateful, or like how right now any security researcher would understand what is an attack. You would see a transaction that is weird, that you have like there are a lot of funds moving, and so on and so forth. And then you would go to the address that is starting, you would check their funding, you would check whether it's coming from a mixer, whether they are like coming from other illicit accounts, like how are they getting funded, how are they getting their initial money. What is their past behavior, right? So are they doing also weird stuff? Do they have like a history of scamming people before and it is known? Or do we have like any extra information about what this address is doing? Or like which smart contracts have it deployed? We can analyze these smart contracts. We can see whether they were good or bad. They were potentially malicious. If they have a story of deploying malicious smart contracts and were funded by Tornado Cash and had already scammed people, then, well, I guess this person is probably a scammer or an attacker, right? So it's kind of dangerous. And then we also have like some heuristic rules of like, OK, you are completely emptying the pool, blah, 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 that it's like either very general or very protocol specific. So in the end, what I want to say here is that this is a lot of extra information that we are taking into consideration, right? And this is what we are considering by stateful detection, because we are taking into state the previous state of everything that has happened, and we need to have all this context for transactions and so on. But having this context obviously helps, right? Because it's always nice to have more information about it, but it's slow. Like whatever you do, you have to have this thing somewhere. You cannot have it like you cannot have like a huge memory with all the others and understanding what each one of those is doing. So even if you have like a nice system where all of this is together and you still have to call it, you are still adding like a couple 100 milliseconds for every transaction that you are trying to detect. And when you want to go at a proper scale and you want to go more to, like when you want to be working on a rollup instead of just protocol specific, that is just too slow. You are going to potentially break the stuff, and this is something that it's just not acceptable to be that slow when you are doing this thing. So this is why doing stateless and just looking at the transaction itself, it's really valuable, right? It has like these two main points of, first of all, it's faster because all the information is already there, and you just need to run code over it. Plus, there is the, I completely lost my line of thought. Whatever. Cool. So now let's go to how we can train a machine learning model up until now, right? This is a very standard machine learning lifecycle of what you would do. And here you're going to have to apologize me. I'm going to use the word model a lot, and it's going to mean two different things. Because like you have the model of when you're modeling the data and the model of like the deep learning model when you're doing inference. I'm going to try to do deep learning model. If I don't, you can hate me afterwards. You can find me for a coffee and should throw it in my face because it was confusing. So great. So how do we start? We have the transaction, right? And we have like the from, to, data, logs, and traces. And that's it. The first thing that we need to do is model the data. And that, in this case, model the data means we take whatever input data that we have, and we transform it in a way that it describes our transaction in a unique way. And it has a format where it can be passed to a machine learning model, in our case, a deep learning model. Like deep learning models here, and in this talk, when I'm talking about AI, I'm not talking LLMs. LLMs are not necessarily the best tool for this job, but AI is a bigger umbrella. There are other type of deep learning models, which is what we're actually using. Just imagine what we have been seeing like some years back, this computer vision, where we were identifying things there. The model of the data was the image itself, because it's good enough. But now what we need to do is transform it. So just for the sake of the example, let's imagine that we are modeling into a table, which is an input that you can actually pass to a machine learning model. So we can start with like a very simple model, right? And we start with something very simple, and we will just assess and have it as a baseline. For that, we would create like a model that has, again, I'm going to be extremely simplistic, but what was the total profit of the transaction? So which address profited the most, and how much did it profit? And how many traces did the transaction have? So did someone profit a lot? Was it a complex transaction? That's like an extremely simplistic model of the data, but that's something that already allows us to keep moving into this, into creating this machine learning model. What is the next step? We have to collect a data set. We are going to use what is called supervised learning. Supervised learning, mostly what it means is you present the model with a set of data, and you are telling the model, like, hey, you see this observation? This is bad. You see this observation? This is good. And you do that a lot of times, very iteratively, and in the end, the model learns how to do over that thing. So for that, what we did is we create this data set of previous attacks of the transactions that we're actually subtracting the funds. But not only, you need to also have like good transactions to be able to differentiate them, right? So you create like this big data set with these hundreds, thousands of attacks and these thousands, tens of thousands of banning transactions. And then you train the model, right? Training the model here, and here is the deep learning model and not the data model. What you do is like you do this iterative process over a certain amount of epochs. I don't know how familiar with machine learning, but this is like standard procedure. You train, you have a loss function, and mostly the loss function, what you are doing is optimizing a function so that the model, what you are telling the model to be true, so these labels of the dataset that we commented before, it gets minimized, and the model has learned what you are actually teaching him. OK, now you have a trained model. With that, you can already defend blockchain. Yeah, sure. You can try, but then since we are like at the extremely simplistic point in time, we have like a very simplistic data model, it's not going to work that well. So what do? You go into evaluating the model, and you take millions of transactions of normal operations of several blockchains, and you evaluate that. And you see that your model is bad. Because at this point, it has not enough information to actually learn whether a transaction is good or bad, right? So then you go back to square one, and it's like, OK, I know that it's bad. How can I improve my data model? So you start thinking, you take a look at your evaluation, you look which transactions you fail a lot, and then maybe you saw that there are transactions where there are several people with profit, and in those ones you were very bad. OK, then you add a new variable to your model data, which is, OK, this transaction actually has 3 people on profit. And then you do again, in the collection data set, you already have a data set from the previous step, but you can use the most representative data points that you have collected during your evaluation, because that's the way in which you can keep improving your model. Like you evaluate it, you see where you fail, you tell to the model, you were wrong here, and the model says, thank you, and it won't do that mistake again. Then you train the model, go again to evaluate the model, it's a little bit better, you see another thing, and then you keep doing this iterative process until eventually you have a model that actually you're happy with the performance, and that it's actually able to detect attacks only using transactions. And that's super nice and beautiful, right? This cycle is something that it's called MLOps, which is the other keyword that I was missing at the beginning. It's like, this is the most keyword in ML after AI probably right now. This is literally DevOps applied to ML. So it's just a way of having like an iterative way of improving your models and monitoring them to make sure that they don't get worse over time, because that's something that can happen, and that you are still finding the stuff. Having this type of MLOps cycles is also extremely useful, because imagine that you are working with some customers, right? And then there is a type of false positive that it appears often. And here often means like once per month, right? But like once per month, you have one false positive with one of your customers, and it's always the same type of transaction. When something particular happens, your model gets confused, and it says that it's an attack, even though it's not. OK, doesn't matter. We have the cycle. We put it into our cycle. The next iteration of the model is not going to be wrong at that point. So it's a model that by itself, it's good. It's already able to detect a lot of attacks. But it's also going to keep learning and learning over time. And it's going to learn over the things that we are actually failing. So it's just getting better and better, and the things that we actually care about. What is the output of the model, right? Because right now, the previous slide was a little bit theoretical and was like, yeah, OK, the output of the model, what is this model actually giving us? Like in the example I was using before of pictures, if we are using computer vision, the output of the model is like, is this picture a cat or a dog? Is it a cat or is it a dog? But here we are trying to evaluate how risky a transaction is, right? So the way that we define them, because this is something that you have to define in the model, and it's something that you need to define when you are defining your loss function and your objective, and this is your end goal. What you want to do in a beautiful world is that every transaction that is an attack is at 1, every transaction that is not an attack is at 0. Of course, that's never going to happen, because there's something in the middle, but that's the goal, right? So what we end up is like with this spectrum, and the model gets good enough when most of the attacks are as close as 1 to possible, and most of the no attacks are as close as possible to 0. Something that is also interesting is that since we are generating this risk score, and this is not only like a single value, right? It gives us like a complete interval of data. We can actually, depending on who is using it, they can decide how risk averse they want to be. Because some people, they want to be like, no, if you are even a little bit concerned that this might be an attack, I want you to stop it. Then you can say like, OK, everything that is over 0.5, go. You are going to obviously have a lot more false positives because, well, that's how things work in automatic systems. But you can make sure that you are not losing anything, because over 0.5, it's very extremely difficult that nothing is found. On the other hand, if you just want to make sure that it's a stop if it's like a very big attack and like the confidence is very high because you prefer losing a little bit of funds instead of annoying your customers, then you just go over 0.8, which is recommended value. That's why it's red. And then you will only stop like attacks that are very obvious attacks. So this is actually very interesting because it allows some configuration, even though it's a little bit esoteric at some point, but you can get like some understanding of how risky a transaction is, and you can decide based on your risk aversion. So now, this was the detection part, right? Like this is like when we were looking at the transaction, what we actually can say about the transaction being an attack or not. But I also promise you that we are actually stopping the attacks and preventing them. How do we do that? I'm going to go very low here. Like, I'm not going to go into a lot of detail because the point of this talk was mostly to talk about the detection and the AI that we are using. We have a workshop today at 3:30 where we are going to go more into detail into this. Otherwise, you can find either Andy or me. We are going to be around and we can explain a little bit better. But the main idea is like this, right? So a user sends a transaction. And the main point is that for users, don't need to know that they are already protected by firewall, right? Like this has to be as easy as, like users need to know that they are a little bit safer, but they don't need to know how it works. It has to be as easy as possible. But it also needs to be very easy for actually protocols or roll-ups that actually want to implement this thing. So I promise you it's very easy, and like we are making it easier every time. We have a couple of different flavors of how this thing is implemented, depending on whether you are a roll-up or whether you are a protocol. It works a little bit differently, but like both of them are very low friction implementation. And once it's set, you can just set your threshold, and any transaction, all transactions are going to get screened, and the transactions that are over a certain threshold are going to be not executed. And it really works like this, right? So a user sends a transaction. It goes normal operation as that user would be. The transaction gets screened at some point, like it gets outgoing a little bit for the firewall. It gets analyzed. We decide a risk score for the transaction based on our machine learning model. Then the transactions that are over the threshold that the user, not the user, like the protocol user actually defined are dropped because they were too risky. And then they get logged. There is a dashboard. They can take a look at it, et cetera. And they can decide, OK, you were wrong here. Your next model shouldn't be wrong in these type of things. And the transactions that have low risk, so below the threshold, they go normally. The user doesn't see it because it's fast. So it's very seamless. And like most of transactions, most of them are never going to see any of these things. So I'm talking also a lot bit theoretically. I want to show you some numbers of how this actually works, right? And like the results that we are having with the model that we are having right now. First of all, like we did some tests on September. September had like around $40 million lost due to attacks. Out of those 40 millions, we detected 99.8% of the transactions that lost this money. So almost all of the attacks that happened were there. Out of 40 millions, we could have defended something like 39.9 million. It's amazing because, again, it's just looking at the transaction. We don't have any context. We don't care how you were founded. We just care what you actually promise that you're going to do. Like, I think this is very important to take home, that it's not about what you have done before. It's exactly what you have already committed to do in the blockchain right now that you are being stopped. So it's not about previous. You can do whatever you want before. What you are promising to do, because it's the transaction that you are sending at this point, it's the thing that might stop your transaction. So when you are showing that you want to steal those funds. Then regarding false positives, at the rollup level, so when we are analyzing all the transactions over a chain, we are having like one false positive around every 150,000 transactions or so, or better. But like, let's go one every 150,000 transactions. This would be, what, 10 false positives in the whole mainnet in a whole day. Like some other chains are like much better than this still. So this is not a lot of transactions. This is like, for example, Arbitrum. This is like almost 500,000 transactions. We had one false positive, which is the one that is in the red part. Like this is the risk score that I showed you before, just like a histogram. It's in logarithmic scale, okay? Like the one on the right is a 1, the one on the left is a 445,000. So if it wasn't logarithmic, we wouldn't see the risk 1. So that's why it's in this way. Then, for example, in base, we also have one that it's at 1, right? Yeah, casually, this was around the block when the Summer Money incident happened. So that's the transaction that was in Summer Money. So the only actual risky transaction that we have, and this is already around 100,000 transactions, is the one that was actually an attack. So this it's something that we could have prevented. And then it works a little bit different when it's for protocols, because like they are more concentrated in the things they are doing, and like direct transactions are like easier to scan and so forth. And here, usually what you can expect is like to have one false positive around every 3 months. But let's be honest, like defending 99.8% of the money for just the pain of once every 3 months having to log out into your dashboard and say like, hey, this was not a false positive, that you know it's going to get improved over time, it's very nice. And this is like an example of one protocol that we are working with. So just for you to know that there are literally nothing even in the yellow and orange zones. So this is for the firewall. This was how we are using AI to actually start stopping malicious transactions. Anything that you want to ask us, like Andy and I are going to be around today. We are going to be around in DEFCON. Find us, speak to us. You can contact us by email, whatever you find. And yep, I hope you liked it.
Thank you very much. I don't think I'll throw coffee at you, but I'll definitely have some questions to ask later. Our next presenter is Tarun from Gauntlet, talking about dynamic restaking security.
Perfect. Thank you. Hey, everyone. Thanks for coming. I know it's early in the morning, and some of us are also jet lagged, so I very much appreciate it. So we're going to talk a little bit about restaking security. I think, obviously, as these networks are going live, there's tons of capital in them. It becomes more paramount to think about what A, a security model is, B, what threat models are, and C, how to model them. I think in this talk, I'm gonna sort of be more high level, but almost all of the results you see or are mentioned are in papers online, and you can find me to find them. So we're gonna kind of talk about 3 things to understand restaking. First, we're going to kind of define restaking in a sort of more combinatorial and algorithmic game theory sense as a matching market. Then we're going to talk about different threat models, how those threat models affect how you should assess risk in these systems. And third, we'll talk about what the notion of the minimum amount of security is that needs to be in these networks. So first, we'll talk about matching markets. So restaking networks are effectively matching markets between validators who are already operating Ethereum, for instance, or Solana in the Jito case, and services. Services are extra new protocol extensions such as rollups, oracles, et cetera, that are trying to utilize the security of from these validators. In classical matching markets, this is sort of one where you're looking at sort of dating preferences, and you can kind of see, hey, the set of edges represents the set of all possible viable matches. In the thing on the left, there's a feasible maximal matching. In the right, there's a contention. So matching markets are sort of everywhere. I think people have won the Nobel Prize for them. But the main difference about matching markets and sort of things like auctions that you see in MEV are you generally have inhomogeneous goods that have some shared property on the supply side. So this in the case of AVSs is validators. So some validators might be running beefy hardware, can run your extra service that needs a bunch of GPUs. Some validators are running on a Raspberry Pi. They can't run all AVSs. So there's some sense in which all of them share the fact that they're running Ethereum consensus, but they all have slightly different properties. A natural place where you see matching markets outside of these types of settings is kidney exchange. And in kidney exchange, you have this notion of supply, like everyone has kidneys, a lot of people can donate them. But there's all these constraints, blood type, size, kind of how old a kidney is, whether it's had dialysis, et cetera, right? So you can kind of think of each validator as a different kidney in this case. I'm sure those with Raspberry Pis are the ones with the worst kidneys, unfortunately. On the demand side, you have services, so that's oracles, coprocessors, GPU networks, et cetera, that are sort of demanding being operated. So one important thing to understand about matching markets versus auctions, you might say, hey, couldn't the validators just run an auction and say, okay, like you service Oracle, like you have to bid for us to run your Oracle light client or side client. One important thing is auctions focus on generally maximizing revenue or maximizing welfare for the buyer and the seller. Matching markets are focused on stability, which basically means when I match validators to services, there should be no one who's unhappy in the sense that they would rather have switched and been matched with someone else. And in crypto, we've seen, especially the last 2 years, the microstructure move from a lot of auctions, so MEV auctions, parachain auctions, things like that, to much more matching-like things like intents and restaking. The natural way to represent matching markets is, of course, via graphs. And the idea is you have a bipartite graph that represents the supply side and the demand side. Those are the two portions of bipartition, where one side is the supply, so the validators, and one side is the demand, the services. One important thing to note is that in most matching markets that are studied outside of crypto, this graph is static, so it doesn't change. So the set of people who could donate a kidney is not changing. And there's usually a central planner. So the central planner chooses the matching. But in decentralized matching markets like restaking, that's just not true. OK, so the first claim I made is restaking is a decentralized matching market. So when we want to analyze the security of matching markets, they're a lot harder to analyze than sort of the classical ones that we know of. One of the reasons is A, permissionless means you can be matched and unmatched at will. B, without a central planner, the only way to construct matches is by correct incentives. And C, you have to actually have an explicit adversarial model. So we'll see some examples of this, but for instance, if I ask you the following question, Ethereum has $1 billion of stake, let's say, hypothetically. What amount of economic security does it actually have, right? You would actually have a hard time answering that. If you said it has 333 million for double spends, that's a valid answer. But that's not really the notion of economic security for these other services. So for an Oracle manipulation might actually cost less because I only have to bid in block building auctions for a certain number of time. And so there's sort of some notion in which the types of attacks you're modeling can define what it means to have a certain dollar amount of economic security. And as you can see, no one on the internet agrees. So maybe we'll take a tiny detour to try to talk about what the notion of economic security is. I think you can exercise left to the reader to go find all the million tweets about people fighting and being inconsistent. So as I said earlier, what does it mean to have $333 million of economic security? So there's sort of a sense in which this concept, of nebulous concept of economic security in an absolute sense is very hard to define. You have to choose what asset you're measuring in. You have to enumerate the attack space. Double spends are not necessarily the only attack anyone cares about in 2024. You have to consider competitive pressures for stake. Why would I lock up my capital if I can get yield elsewhere that's higher? And you also have to think about how much the opportunity cost for capital is of doing an attack, and also how long it takes to execute an attack. But generally, the kind of attack cost is linear in the amount of stake somehow. So you're writing this in formulas. We kind of say the cost of attack is lower bounded by a price, P of T, times the amount of stake, times some notion of compounding or opportunity cost based on how long it takes to execute an attack, times some notion of a minimum threshold of stake needed to execute the attack. So this is sort of just a generic way of saying this is what a lower bound on economic security is within POS for different attacks. What does that look like for restaking? Well, restaking actually has two sort of competing pressures when you try to quantify what its economic security is. The first is participants purchase stake to capture excess yield. So if more people are buying Ethereum to restake, they're actually causing the economic security in dollar terms to go up. So in some sense, you can argue that restaking can improve if a lot of new participants are purchasing. On the other hand, if people get slashed, that reduces the overall network security, right? Because I've basically burnt a bunch of stake that was locked, and now effectively the total amount that can be slashed in the worst case event has gone down. So how would we represent this? It's not so different from the last formula. We have a notion of a stake, that's the capital sigma. We have a notion of a price in numerator terms. We have a notion of how much people increase the value, which is this 1 plus delta term. And then we have a notion of a risk measure, which is how much stake is burnt, what percentage of the stake should I expect in an average case or worst case scenario is slashed. And then I have a notion of a price impact function. So what this is if there is demand for delta times the stake that is there, how much does that actually push the price up and then cause the actual cost of attack to go up? So if we zoom out, one of the reasons for trying to formalize this is you're really trying to measure some notion of cost of attack. Oops, I guess that one was there. So one question is, when is restaking safe? And so one very simple definition is the cost of attack when restaking is present is always higher than the cost without restaking, and that's what this inequality is. If we write that out, we get this formula, and if we write this out, we get a formula that says the risk, the maximum amount of stake that can be slashed has to be as a percentage, so this is from 0 to 1, has to satisfy this type of formula. G is a value greater than 1. And so one important thing to note is that this has this dependence of like the risk, the slashing risk, on the actual price impact of people participating in restaking, which is not great, right? Because from a, say, formal verification standpoint or from a fuzzing standpoint, I can't really check this condition. I can't make this a valid condition that needs to be met. So the natural question is, can we model this without needing the price or staking dynamics? Can we kind of have a static model for what it means for restaking to be secure, and then you can construct formal conditions that you could verify? So to do that, we will have to do some math. So the main object of study within these systems is what is called a restaking graph. A restaking graph consists of 5 components. First is the set of node operators. So these are the validators who are operating the network. That's the set V. Second is the stake. So for each operator, you can think of it as a vertex label for each operator of how much stake they have. Third is the services. So this is the AVSs. So this is your Oracle, this is your coprocessor, this is your DA layer, et cetera. Third is a notion of the maximum profit from corrupting a service. So in this model, you sort of assume there's sort of a maximum honeypot prize that if you were able to corrupt the service, you get to get this amount of reward. So that's what pi is. The fifth component is a corruption threshold. So in, say, a BFT protocol, it might be 1/3, which is the sort of double spend in proof of stake. In the longest chain protocol, it might be 1/2, which is the sort of attack a longest chain protocol. And one important difference between restaking and normal staking, which is extremely crucial to the security model, is that I can use the same stake to validate multiple services. So this node operator, Reentrancy, is actually operating both services, S1 and S2, with the same stake. So they're putting up 100 ETH, they're validating both of those services. If they get slashed by either one of the services, it's as if they got slashed on both services. That's a crucial point that you have to keep in mind when thinking about this. Okay. So now, you might say, hey, is this graph real? Like, are you bullshitting me and like you just wanted to do some math for fun? This is the eigenlayer restaking graph over time. Green are edges being added. The right side is the services, the left side is the operators. Or sorry, am I getting it backwards? Yeah, left side is the operators, sorry, right side is the services. But you can see that this graph is changing as people are adjusting incentives over time. And that, as you saw earlier, affects the security of this system. So how do we formalize, in a sort of formal verification sense, what an attack means? So there are two conditions. First is profitability. Profitability is give me a subset A of services and give me a subset B of validators who are colluding to attack that set of services, and you need the profit to be greater than the slashing penalty. So what this means is the maximum profit I can extract from attacking those services is greater than the amount of stake I lose, right? So that's a positive profit attack. The second thing is feasibility. So what this says is for every service I'm attacking, this cartel, this set of validators, has at least the minimum amount of stake needed. So for instance, if one service is a BFT protocol, the attacking services have at least 1/3 of the stake. In symbols, this is what this looks like, given the variables we saw earlier. On the left-hand side, you see the total profit from attacking the set is greater than the total stake. On the left side, you see the stake held by the cartel at each service is greater than the threshold. So the first place was defined, Appendix B of the Eigenlayer white paper. The second place where it's cleaned up and formalized, which a lot of the results that follow are Durvisel and Roughgarden, this paper from this year. Okay. Note that these are properties you can validate of a live restaking system, right? Because a live restaking system is defined by this graph. This graph is public. All of the data here is registered on Ethereum. If you go look at the Eigenpod contract, you can get all of these numbers on every block. Now, what does an attack look like? So in this graph, each individual service is actually over-collateralized. So service 1, the maximum profit you can get is 4, but there's 6 stake. So if all the stake is slashed, you have at best a -2 profit. And the same for service 2. But if everyone colludes to attack both services simultaneously, it is a positive profit because I can get 8 units of profit and I only have to expend 7 units of stake. And the real reason for this is because the middle node operator is sharing their stake. So by slashing them once, you've slashed them everywhere. So this naturally leads to what's known as a cascading attack. So a cascading attack on a restaking network is, imagine that some fraction of stake is lost. Maybe that's an operator that got DDoSed and is down. Maybe that is an operator who was malicious and sent an invalid block and got slashed. For some reason, their stake has disappeared. Once they've disappeared, what they do is they create a profitable attack. So in this case, the middle operator can attack the first service once the first operator is gone. And once that attack occurs, they've opened up an attack for the second service to be attacked by the last operator. So what this shows is that you can have these sequences of profitable and feasible attacks until you continue to lose stake. And in this case, you've lost 100% of stake. So this says R in the formula we had earlier is 1, which is bad, because that means the restaking network has slashed all the stake of the underlying L1, which is obviously the worst case. This is the proof of stake version of a lending liquidation cascade. So how do we formalize this? So we define a valid attack sequence as a sequence of pairs of sets of services and sets of operators such that each attack, AI, BI, is profitable under the definition we had, and feasible. And we define a quantity, R psi of G, which is very similar to the R earlier we talked about, which is like the percentage of stake that is burnt expected, as the worst case percentage given an attack if I lose psi stake. So imagine the network has a shock and it loses psi stake. Psi could be, say, 10%. Then this says what percentage is the longest cascade attack going to lose. In symbols, it's written like this, just so you can see it's between 0 and 1. So there's no hiding anything there. OK. So this actually helps us answer this question. How much stake do we actually need? How much economic security does our single AVS actually need to be secure? We choose an R psi threshold that we're happy with. So hey, we're willing to tolerate a shock of 10% at most. And if R psi is only 5% given a 10% shock, then we're willing to tolerate that. It lets you have some bounds on how much the worst case attack is. So are we done? Not exactly. So this paper shows that there exists an infinite family of graphs with n validators where the entire graph is slashed, which is very bad. It's actually nice to see in pictures. So in pictures, each of these dots is a validator. Each of the boxes is a service. So we have 6 services. We have the red L-shaped services. So there's 4 of those, each with 3 validators each. We have the blue box services, which have 6 validators. And what you see is first operator is taken out. You move to the right. And then when you go down a row, you see that that opens up an attack against the first service, which opens up attack against the bottom row, which opens up an attack against the other services, and then all the stake is gone. And because this is a tiling, there's an infinite number of them. So the same paper showed sort of maybe a blessing in disguise, which is if you're actually over-collateralized, then you can actually bound this amount of stake you lose. Great, we might be done. However, and sort of you can think of this as like the proof of stake analog of a decentralized stablecoin needs to be over-collateralized to avoid cascading depegs. The problem is this over-collateralization condition, which we won't exactly define, is actually really strong. So it actually says if I have a bunch of services, I may have to have as much stake as the sum of all of the profits over all services. In translation, imagine you have a restaking network that only has 2 services, where one service you can attack and get at most 1 ETH of profit. The other service you can attack and you get 1,000,000 ETH of profit. Under this over-collateralization condition, you need 1,000,001 ETH for the 1 ETH of attack service to be safe, which is obviously ludicrous. At that point, I would just start my own POS network, right? Why would I pay for 1 million ETH to secure 1 ETH of attack profit? So is this a dead end? Of course, I'm giving this talk, so the answer is no. So one thing that this whole model doesn't consider is the incentives, like how much are people being paid, and how do we include that when we think about profitability for an attack? So if we think about how restaking went from 0 to 15 billion, it came out of people paying incentives. It wasn't sort of like a free lunch that people were running validators. And so we actually have to think about each service offering an incentive, either a token incentive or points. So we add one term here, which is this term R, which sort of represents how much each service is paying. And in response to the rewards, we assume the validators aren't sitting ducks. They can adjust where they place their stake. And what this means is validators, after a slashing event in this model, can rebalance. And they can, in some ways, halt these cascades by pure economic incentive, where someone gets slashed. If it was profitable for them, it is profitable for me to join. And so I will join and prevent the cascade, which is what this yellow box is, which is basically after a slashing event, someone from the top row joins the bottom row, prevents cascades. So in this model, we assume the adversary is somewhat weaker in that the adversary has liquidity and cost of attack constraints. And then we assume the node operators are smarter. They can adjust in response to these incentives. And what you show is that basically the maximum cascade length actually decreases as the number of services gets large, and that you can compute this efficiently. So basically what this says is if you have enough rewards, you can actually, and node operators are not idiots, you basically can reduce this cascade risk that we saw earlier. Again, adversaries face costs, node operators are smarter, AVSs pay rewards, you don't have as many of these attacks. So how do we reduce this in practice? So you might say, hey, EigenLayer's live, like how do they actually do this? So they actually proposed a new mechanism called unique stake, which is a notion that every service can say, some fraction of the stake allocated to me is only slashable by me, by my service. Like no one else can slash it. So in all of the cascades you saw, the reason they were bad risks was another service could slash stake delegated to my service, and then I lost economic security. The point of unique stake is I'm able to say, actually, some portion of the stake is only slashable by me. And so each service is able to reserve a percentage of stake, which caps the maximum overlap between services of how much stake is shared. And so it's sort of a trade-off between capital efficiency of these systems versus security. And the key thing is when you have this unique stake, you can actually provide very efficiently verifiable guarantees even before the network is live, some sort of like formal verification guarantees of taking all these constraints I've talked about earlier and verifying them ahead of time. And you sort of have this verifiable collateral requirement. And with that, I think that's it.
Thank you very much. So for our last lecture before the break, we have Hudson from Polygon Labs talking about the 2016 Shanghai attack.
I'm Hudson, and I'm here today to talk about the 2016 Shanghai attacks, a history and a technical deep dive on this. You're going to see some chat logs that have never been released before. You're going to see some insights that may have been muddied at the time from everyone freaking out or just being so long ago. So let's get started. So why am I speaking on this? Who am I? Why am I so handsome? So I worked at the Ethereum Foundation from 2016 to 2021, did a lot of protocol coordination stuff with EIP editing, core dev calls, DevOps security, excuse me, you name it. And now I'm at Polygon Labs after hitting up a few other places like Flashbots and Zcash, making sure that people know about the incredible stuff we're doing with eliminating L2 fragmentation and ZK. So I wanted to do this talk because I think history is important and it provides lessons that get forgotten about over time. I'm going to kill this microphone. So the story's really interesting, and I have an important lesson at the end. There will be an end reveal. All right, so this is when I joined the Ethereum Foundation. Bright, young, full of energy, you know, just so excited. But this was, what, June 2016? And then September 2016 was DevCon 2. So DevCon, yearly Ethereum conference, that's why a lot of us are here this week in Bangkok. Just to put in perspective how things were back then, proof of stake, we were working on it, researching it, we wanted it to happen, but we were far away from answering even the most basic research questions around how to deal with it. The price of ETH was $13. That's going to be really funny when you see how much the attacker spent. That's coming up. We're still using proof of work, like I mentioned. And there were 4 clients that could sync to mainnet. Again, all execution layer clients. We didn't have consensus layer. Thank you. Great service here. Yeah, so the clients were Geth, written in Go, Parity, written in Rust, Ethereum J, written in Java, and then Aleph, aka Ethereum++, the C++ client, which was mainly used for testing. Arguably, Vitalik's OG client Pytherium could kind of sync to mainnet, but not really. That was kind of, we were over that by then. So DevCon 2 was happening in Shanghai. It was going to be a, I think, 2 or 3 day conference. I was co-running it with a number of other people at the Ethereum Foundation under my role of DevOps events and things like that. So it's 3 a.m. and DevCon's going to have their first onstage speech with Vitalik Buterin in about 6 hours, and I get a call. The call comes from a phone that is in the toilet, because I guess in Shanghai, like, we had the phone in the room and the phone in the toilets, and I was so disoriented, I jumped out of bed and ran to the bathroom and picked up the bathroom phone. And George Hallam, who used to be the PR director for the Ethereum Foundation, was on the line and said, "Hey, wake everyone up, we're under attack." So then I do a deep sigh. I had not gotten much sleep anyway. It was a very stressful DevCon operation there. So this is the start of Ethereum being under attack on September 18th. There were some people, this was in Shanghai, China, there were people mainly in the European time zones that had not gone. They couldn't go because of family or things like that. One of those people was Gustav Simonson. He used to be the head of security of the Ethereum Foundation, likely 2014, 2015 till 2016, 2017. And he said, alert, Geth nodes reported running out of memory and crashing on this block. And then Yuta Steiner, who's now, I believe, still the CEO of Parity Technologies, or not Parity, yeah, it might still be Parity Technologies. She was also one of the security people at the Ethereum Foundation. Nick Johnson was just awake for some reason. Nick Johnson's the creator of ENS, but was on the Geth team at the time, having just joined fairly recently in the year before. So they're like, okay, get everyone together. Can we get a hold of everybody? So according to, there's actually a hard fork celebration call that happened. I think it was for like Den Kun or something, where Vitalik recalled this story, and he said that he got a call at like 4 in the morning or 5 in the morning, and it was me just going like, we're under attack, get up and get down to like this weird hallway area. And he just like sighed and then went out there. So I start like, I shouldn't say I start freaking out. I start going quickly and trying to figure out who I can wake up. So the funny stories with this are, we're in different hotels around the Hyatt in Shanghai, which is like one of the main ones and where the conference was at. And like, I didn't know, this was like 2016, so it wasn't like, everyone was on Skype. Like all the logs you're gonna see today are Skype or Gitter. So like you could call on Skype, but people didn't really answer Skype calls after a certain time because they had do not disturb. So anyways, I go down to the registration desk and I'm like, just look frantic. And I'm like, hey, I need to wake up this person, this person, this person. So they give me 2 of the names. Hotel security always just gives you what they want, what you want, if you're just like sounding like fast enough. But one of the names, they said, they're not staying here. And I said, yes, they're staying here. I saw them here. And then I stopped for a second and I said, that's not their real name. they've never used their real name with anyone, have they? So could not find the Anon developer on one of the client teams. That was great. So anyways, let's dig in a little bit to what actually happened. So I can't pronounce that, like Fartnakos, something like that. Some people think it means go home. This is a transaction that went to the attack contract that brought Geth down with memory errors. So we're not sure what that means. To this day, we really don't know who did this or why or things like that. But that's just one of the things that at first really hit Reddit hard because people like used it more back then as like, oh wait, someone's like doing this on purpose. It's not just like a bug in Geth. So one other funny thing that comes up every once in a while is me and Peter will joke about how I woke him up in the middle of the night. So Marius is a core dev with Geth, but he wasn't around in 2016, but Peter was the co-lead of Geth. And so, yeah, like we like to joke on Twitter a lot about the Shanghai attacks because it really was probably, other than the DAO hack, one of the most stressful things to happen within Ethereum core development work. This is a picture, the only one that I'm aware of the core devs and others in the spare room that we just found. We literally just found like a big hallway in the Hyatt and then eventually were allowed to go into this spare room to work. For the people in here, top left is, or was I gonna be left for y'all? Yeah. Top left is Nick Johnson, and then Piper Merriam, Martin Svende, and Peter Szilagyi, yeah. All right, so we're gonna go over the first attack. It's a transaction spam attack about a mispriced opcode, and we're gonna go through the fastest lesson in opcodes ever. All right, you're making a contract. It's Solidity, it's Viper, it's LLL if you're a really cool guy. You compile it down. When you compile it down, it gets into the thing that the EVM code and the Ethereum virtual machine can actually read. That's on the left. That's code generation from what you as a human are typing, human readable, computer readable. Let's go back over to the right. Now we're actually in the EVM. We have this code that we just sent in that's readable by the EVM, and we have a virtual machine that's running it, and the thing that's running the virtual machine, or the runtime process in this case, would be Geth or Parity. Then lower than that's the hardware level. So that's like the base level of like that part. Now we're into like, how do we know what, when we send in a smart contract and it says like 1 + 1 or A + B = C, how do we know like how much gas to allocate? How do we know, like what's gonna happen to this? So code in Ethereum is non-deterministic. And the reason for that is whenever you run A + B = C in your smart contract, every other node on the network has to run that. So you can't have an infinite loop or else it'll just like go forever and all the nodes that are trying to run this are gonna like run out of memory. So you also have opcodes. And the opcodes here on the left are like regular ones. They're really simple to understand, like add, multiply, subtract. And then you have ones that are a little more complicated. The reason that we have these opcodes are to have like things built in that most people can use or extrapolate into bigger and better programs you want to use. We also have dynamic opcodes. These are ones that are like a little bit more complicated. They're things that like may be useful a lot of the time, like doing a SHA-3 hash. I might need to take a word and make it into a one-way unique function. So depending on the word size, depending on a lot of things, you have to get that gas calculation right. And doing that is a very hard problem. That's actually, if you dig very deep into it, what I believe ultimately killed eWASM, which was an early attempt to have an alternative to the EVM built on WASM years and years ago. So looking at this, the gas for an addition, it's 3. Like that's fine, like it's super easy. For SHA-3 and for EXP, it's gonna vary by a lot of different things. And if you misprice it, you can cause a flaw where an attacker can go in and just click SHA-3, 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 SHA-3 in the contract really cheaply, and it just take up a ton of memory in the system. And this doesn't have to do with block gas limits or things like that. There's gonna be a block gas limit regardless of what you're putting in there. What this has to do with is estimating based on what a general purpose computer that is gonna be running this or a general purpose computer running a node is, what can that handle? What can that handle before you're out of memory? So here's the actual attack method. Geth clients were trying to process that block, and it would crash. They could spam the chain, the attacker could, with an ext code hash, opcode to seriously degrade network performance. It was underpriced compared to other IO-intensive operations. So what I mean by that is you have Geth at the time using LevelDB as their underlying database storage layer, and you have Parity using, I believe, RocksDB. So databases at the time weren't, and still to this day for the most part, aren't really maintained well if they're open source, because like they don't get enough funding, et cetera, and they also aren't used to dealing with a system like a blockchain that has to hit it so many times. So when you're doing this and you're like, ext hash code, like it overwhelms the hard drive, it runs out of memory, it crashes. So if it's underpriced, then they're able to do that for like no money and overwhelm the client. There's a memory error, it crashes. But the Parity client, who was running on RocksDB, stayed alive. It like literally saved the network. Here was the temp solution. So I'm sitting in the hallway, and there's like the core devs, and we're all sitting there in a circle, and like I think a few of them, because like you know they were going to a foreign country, didn't even bring their laptops because they didn't think they'd have to deal with something like this. So I had this just piece of shit Toshiba laptop I bought as a backup for DevCon that I gave to like, I think it was Peter or Martin, and they were like trying to sync a node on it over the worst internet you've ever seen at a Hyatt in Shanghai. So like that wasn't working. There were people outside too trying to sync, but it was just really hard to get data. But what we did know was, okay, if they're calling that opcode over and over again, what can we do to stop this now? Parity's keeping up, but for how long? So what we decided to do was lower the target gas limit. And this would be more of lowering the floor of the gas limit specifically. So as we are doing that, there has to be a coordination effort. So I'm leading that part. At the time, I was in contact with every major mining pool in the ecosystem and a lot of major miners. And on top of that, in Shanghai, some of the biggest miners, including F2 Pool and ETH fans, which then turned into Spark Pool, were there in person. They're in Shanghai. They were at DevCon. So we literally just called Zhen from like ETH fans in the middle of the night, and he's just tired as hell and like drives up or rides up to the Hyatt and comes over there, and it's like me, a few Chinese miners, and they're like calling all their other miners, and we send this out to change their setting on their node. The thing with changing the gas, like the max block gas limit, is there is a special formula built in where the network looks at all the miners that are putting out signals, putting out blocks, and they say, what do you want your gas price to be? And if enough of them agree, they lower it 1 over 10/24 gradually over time. So amazingly, within about 5 hours or less, we lowered the gas price to like something incredibly low. It was like 4 million, no, it was less than that. It was like 400,000. It was something like super low. So now when the attacker tried to call that same contract, it wouldn't fit in the block. Like it literally just wouldn't fit in the block. And if they modified it to try to hit that opcode over and over again in a new contract, it wouldn't do as much damage because you're limited by that block gas size and by the contracts you can put in there. It also increased the cache size on these mining nodes. So that's another thing that kind of helped deal with this along the way. So this is the temp solution. So it's September 22nd. It continues. I'm still in Shanghai. DevCon's over. Let's see, I say attention. Multiple reports of Geth failing. Is this an issue? And Parity struggling as well. So here's the second attack method. So the same attacker set up a separate set of contracts. And this was another type of attack. And this one actually did take down some Parity nodes, if I recall. But on the initial denial of service attacks that were happening with the ext code hash, they exploited another flaw where they could cheaply create a large number of empty accounts in state. That might be a little foreign because that no longer can happen. And I'm going to explain in the next slide why. This was done repeatedly using the suicide opcode. Now it's called self-destruct. We don't use that as the original name from the yellow paper. The opcode's ether transfer function poked new accounts into existence over and over again. Even though there was nothing in those accounts, the state kept up with them, which was really weird. So now, bro's making 19 million empty accounts, and so suddenly state bloat's like, and yeah, it was kind of like a, oh wait, are we going to run out of disk space eventually if he keeps doing this? So that's the state bloat attack. So empty account versus non-existent account. I actually forgot about this till the other day. This is one of those things that reminded me when like there's some weird thing in like JavaScript where it's like, why is this equal to 0, but then this does null? Like it's the same kind of thing, so I'm glad we fixed it. An empty account is an account with a 0 balance nonce code. Empty accounts are like the same thing, but the exception is it has a few gas calculations, and they can be easily turned into non-empty accounts by sending an amount of ether to them. So like basically whenever you try to make that account, even if you don't do anything in there, it like costs, number one, computation, but that's actually less important than the actual like memory and storage on disk. So yeah, why can't we have 19 million empty accounts? Let's have an account party. Well, it wastes hard drive space, increases sync time. If you've ever synced a node and looked at a graph, there's gonna be this funny time in 2016 where it's like, and then like it's done. And you'll see why it goes back down in a second. And yeah, it slows down transaction stuff because a lot of our way we do our storage stuff within the client level is through RAM. So we set up 2 hard forks that dealt with these 2 problems. The first one dealt with the problem when it came to like the immediate effects, which was the mispriced opcodes. And then the second one was cleanup. We need to clean up all those, empty accounts. There's no reason to do it. So yeah, the process of writing, testing, and coordinating these EIPs was done actually fairly quickly under the circumstances. Tangerine Whistle was first, and it repriced a lot of opcodes, and there were a few corner cases of other opcodes that we discovered and then patched. And then Spurious Dragon went in and like made it so that if you touched an empty account on chain using a script, and I'm not sure who ran the script, it would go away. So you're basically cleaning up state at that point. The attacker used 300 ether during the attacks, worth an estimated $4,000 at the time, but now is worth $875,000. So fuck you. So who came up with Spurious Dragon and Tangerine Whistle? This has been discussed a little bit on Twitter. This is a Gitter chat that I discovered where we have Paul, who does a lot of the stuff around, at the time, testing. I believe they do a few other research things now at the EF. Christian Wright-Reasoner, obviously. Christian's like, let's name it 150 and 158, which are the EIPs involved. And then Martin is like, Tangerine Whistle, Spurious Dragon, let's make t-shirts. It's an icon. I'm like, what? But like, yeah, no, I'm all over it though. That was pretty cool because, I mean, hard fork 2, the etherning, I don't know who came up with that. I didn't scroll up, but like, that would have been cool as well. So what did we learn? Multi-client blockchain networks are the most resilient. Ethereum didn't stop that entire time. It was under attack, didn't halt. I could always put a transaction in and it would go through. The fact that we had 2 clients, this was like, what, a year after launching, I guess, 2016, about a year and a half. They're both running on the network as an attack crashed one node and the other stayed on. That's the importance of separating your specification from your client. Bitcoin has their specification intrinsically linked to their sole reference client. So I always say, Bitcoin's specification is their reference client. Ethereum's specification is in GitHub, and we make clients. And that's incredibly, incredibly important. So my spicy take is Bitcoin's going down well before Ethereum would go down, purely because they don't have a multi-node setup. For the ones in there, the actuallys, yes, there's like JavaScript and Node implementations of Bitcoin Core. However, there's so few people running that, and also so few people running that with the ability to connect to Stratum miners that like, I don't really think that that's going to do anything if like that were to happen. And I believe that's my last slide. I have time for a question if anyone has one. Oh, yeah.
Cool. So I guess talking about like your last slide, and you're like it's multi-chain client or multi-client chains are more resilient. I guess the question is safety versus liveness, though, because I guess like for this particular example, when the bug was a crash bug, you were able to preserve liveness of the network. But if it was, for instance, a fork bug, would it not be actually less resilient to safety? Because, for instance, if it was a fork bug, then parity might take one chain versus the other one, versus if you're all running one client, then you'd fork together such that.
That's a great question. So it depends on your blockchain. I feel like, at least back then, Bitcoin and Ethereum were really all about like liveness, because it was like decentralized chain, staying alive like the Bee Gees. But at the same time, I do see your point. Forks in Ethereum have a lot of, I guess, culturalness around like manual intervention from the community. So you roll back the chain or whatever that like, and not like the DAO fork, but like you basically have the longest one and then you figure out how to deal with that. So it's kind of a thing where that happened in Bitcoin too. Like Bitcoin had a thing in 2013 where they had a fork because they had a bug in like 0.7 or 0.8 or whatever, and it caused them to split. So all the miners in about an hour got into one room, and they said, okay, this one's the bad one, this one's the good one, we're taking this one. So miners who mined on that fork did not get their rewards. However, the transactions did stay, from what I understand, and I don't know how they did that. Lastly, there's like things like Solana, which I feel like, you know, obviously are very different in terms of what they prioritize compared to Ethereum. But you make a good point. It's what the community wants and what the blockchain is kind of initially or culturally designed for, where that could be a problem. I just trust Ethereum's like resilience as a community and the protocol devs and the processes we've had and the hardening we've done to be able to deal with something like that and maintain liveness. Yeah, sure. Oh yeah, he had one.
Hi. Sorry, maybe mine is actually a question if you can go back. I'm curious about the script that would close those accounts.
Yes.
Can you explain it more?
Yes. Okay, so I think the Ethereum Foundation may have run it. I don't know. But you basically have all those accounts. The hard fork made it so that if you were to send a specially crafted transaction and you said, hi, I'm touching that account, it goes away. So the script itself, I don't know where that script is, and I don't know who did it or who launched it. I'm going to guess the EF because it probably cost a lot of money, or at the time, a good amount of money to like run that through 19 million accounts, like concursively, but yeah. Thank you all so much.
Thank you very much. I was in Ethereum back in 2016, and just incredible to hear the story. So we don't have time for the break, so we're going to move to the next section, and our next moderator is Tomer from Stellar, who's going to present the people. Thank you very much.
Hey, everyone. As you might have noticed, I was not supposed to be a moderator for this session. There was a different Tomer that was supposed to do it. He's not here, so they went for the next available Tomer. That's me. Yeah, we're going to have some amazing sessions. We're going to start with 2 Aave sessions. The first one is Evolving Slow Systems in the Age of Speed. Ernesto?
Light is next. I can see that. Left is back. Light is next. Left is back. Okay. Okay, good.
Okay, hello everybody. So, yeah. I'm Ernesto Boado. I'm the co-founder of BGD Labs, and well, this is the first. It happened to be the first session like of Aave morning, like, because after me there will be like Emilio also like from the Aave side. Like, so today I wanted to talk about well, first maybe I can talk of what is from where I'm coming from, BGD. Like, so yeah, as I say, I'm the co-founder of BGD Labs, and we are like a team contributing to the Aave protocol, like for core development, security, and well, a bit of basically everything on what relates like with the existing Aave protocol, V3, V2, like everything around. And yeah, coming back to the title like of the talk, like the objective today is just to tell a bit shortly how it works Aave inside, like we could call it inside, like and certain details related of how we think about security and yeah, some kind of inside view of this system and its maintenance. So yeah, about the team I already mentioned, like, so we are, well, I will elaborate later, like, but Aave is pretty decentralized in terms of organization, yeah, following a model that hopefully that someday will be similar to Ethereum's. And so our team is called BGD Labs, it's not called Aave, but because we are completely independent, like from the founding team, even if I was part of that founding team, and yeah, we work that way. So, yeah, as an overview, like first I will show what is Aave at the moment. Like then, the core of my talk will be of putting two examples like of how do we move features like of Aave, how do we think about those features, how we evaluate them security-wise, and some other details. And then at the end, we'll talk about the security procedures that we applied on those features and some other things, and how maybe they are a bit different than other systems, or maybe not so different. So, about the title of the talk, yeah, I think that right now, like DeFi reached a point on where everything moves relatively fast in terms of like developments, like if we compare like with early times. So yeah, I think that it helps that the tooling is completely different, like than it was in 2018 or 2020, on where yeah, technical limitations were actually a thing when you wanted to do something, and especially when you wanted to do something safely. So that definitely has helped a lot, like on yeah, Aave and its ecosystem being pretty big nowadays. We have new types of, in what relates more with DeFi, we have new types of assets that are appearing all the time, like, yeah, like it can be liquid staking tokens or restaking tokens and some others. This, yeah, now at least I have the feeling these LSTs have existed forever, like, but I think in 2020 they were still an asset, as an asset class that was growing, and liquid restaking tokens is like 1 year old. So, but in terms of size nowadays they are pretty huge. Then it also helps like for this speed that nowadays like there is factually way more entry points into DeFi than there was back in the days. Back in the days mainly it was Ethereum and some alternative L1s. Now rollups, I think it's pretty clear that they got some boost, like so you get yeah, a lot of like Base, like Arbitrum, like yeah, you can name it, like, but there is like real use cases there, and any users entering even directly to those L2 and not only to Ethereum, and then maybe going to some other place. And well, I mean, the conclusion is that from all the previous, like, new protocols appear like every day. Maybe it looked like slowed down a bit last year, like, but like in practice, there is actually a lot of of new ideas getting created in production, like, and well, yeah, a lot of innovation. So, yeah, the slow part, which is kind of a joke, is Aave, because I think Aave is quite perceived nowadays like as the stable place, like this kind of behemoth. But yeah, maybe it's not so slow, because Aave is in 11 networks at the moment, the V3 protocol with 13 instances. There is also still 3 instances of, this is wrong, there is 3 instances of V2 in 3 networks. Assets there are like, yeah, I put more than 100, but I don't even keep the count at the moment. Aave also has a stable coin. It has like cross-chain messaging system. It has like a governance system based on storage proofs. Like yeah, basically you name it, and probably Aave has like some infrastructure related with something. So yeah, it's a slow system, but it's pretty big. Like so yeah, this number is something that I took yesterday. Today I think it's more or less similar, but yeah, Aave is pretty big, like with some billions in market size. Well, with this and with all the previous infrastructure, of course, stability is very, very important, and something that, especially on my line of contribution and the team I'm part of, like this is kind of the key. Like yeah, we are the technical team that needs to make Aave appear as like seamless and things work like completely well behind the scenes. So something that maybe like people doesn't, I mean, for sure is not so public is like how is the procedure of like adding features to Aave, like how we decide like yeah to add something, to not add it, quite frequently to how do we decide to remove them, like so. In that direction, like one of the things is that we believe pretty hardly like that all the systems should evolve, because it's quite natural. Like yeah, so the idea of pure immutability is is nice, but even like on the base layer, like let's say Ethereum, like well things change over time. That is one of the strengths we think of the Ethereum community. Like so. On Aave, we try to kind of reproduce the same, but like on the smart contracts layer. So at the same time, like obviously, whenever like you add new features, like or any type of change, well, the attack surface on a protocol, on DeFi protocol like Aave, like it increases. Like so, the more you add, the more potential issues that you can have in all senses, but the ones that really matter are security-wise. So something like very, very important is like when you are like the development team of a system like this, is to find a good point of equilibrium, like of this, like, because well, you cannot remain too static, meaning yeah, you put a system out there like and you wait 2 years, like until you probably die. No, you need to move a bit and continuously, but you need to do it with certain order, or as much order as possible. So yeah, I want to just put the examples of two features that we introduced like actually this year, both of them. So because Aave right now like is not, the protocol is Aave V3, but technically like the protocol that everybody uses, that probably some of you at least use in this room, on chain is right now V3.2. So there was yeah, some minor version, then 3.1, 3.2, and some extra coming soon. So yeah, how we do and how we think about those features. So the first one is liquid emotes. I will just explain a bit. Maybe some of you already know what is like the Aave emotes, but Aave V3 introduced like a mechanism which was called emotes, which comes from efficiency mode. And what that means is that like you have listed assets on Aave, but then you could have like each asset could belong to any mode, it was called, which had like higher risk parameters whenever like the assets on that mode were correlated. Like, so the main use case of this, for example, was having ST-ETH, the LST of ETH and ETH on a single mode. So in that case, you could have like quite high risk parameters because they are correlated. Like, so the risk of liquidation is pretty low. And that enables strategies like high leverage or things like that. So what we introduced on Aave V3.2 was what we call liquidity modes. And this is kind of a technicality, but it made quite some difference. Before, like, each asset listed on an Aave pool could only be on any mode. Like, so the moment that you add, let's say, ETH in mode 1, it could not be in any other modes. And this was a limiting factor, even if the normal modes like help Aave to grow a lot. Like this was kind of limiting, like especially during this year, like when what I mentioned before, when new assets appear, like the system was not powerful enough to cover all the use cases. Let's say with LRTs. So what we did, like with these liquidity modes, is to allow that each asset could be in multiple modes, which seems like something pretty trivial, like, but it actually enabled a lot of use cases. So for example, right now there is like an instance in mainnet, which is the Lido V3 pool, which is heavily using like this concept of liquidity modes with subgroups of assets, and each one is for a particular use case. LRTs against LSTs, LSTs against normal assets, stablecoins, you name it. So how do we thought, how did we think, sorry, about the introduction of these liquidity modes? So usually this is kind of, there are some other steps probably, like, but high level, we think this way. So first we think that if the feature makes sense, like, because it's not only about like introducing technical aspects without thinking high level, how much sense it makes. Then we always think on how is the complexity added to Aave, because, well, we are not creating a system from scratch. We are changing the code or something that is like billions size. Like, so the complexity that gets added or not is a deciding factor, basically, even to move a feature or not. And then also we think quite a lot on how difficult and how long will be like the security procedures associated with the feature, which frequently they are different between each other. So in the case of liquidity modes, well, if the feature makes sense, is what I explained before, like it really made a lot of sense because Aave V3 was being limited, like with use cases like liquid restaking tokens against others. So yeah, we needed to do something, and the alternatives were not so good in terms of user experience. Then, how much complexity it added this feature to Aave? Not really so much. Like it really looks like a complete change of paradigm internally, but the reality is that when you go to the details, the changes were not so aggressive. Like, so you could isolate the logic, like the storage affected, like was not so bad. Like, and it was generally a pretty small footprint for the power of the feature itself. And then, the third question on how difficult we estimated the security procedures was that, well, it was pretty review-friendly. That is one of the advantages of Aave, because even released like quite some years ago, Aave is quite modular code base. Like, so sometimes this is not so good, but sometimes like for the reviews, this is extremely good if you follow, like, if you do improvements following the same patterns. Like, so this was the case here. Like, the change was relatively isolated and easily understandable, which also worked like with quite well, like with an idea that we practice. That is, like, we try to introduce like new security partners and firms all the time. So yeah, of course we work with our typical security partners, like the ones that we trust from a long time ago, but also from time to time we try to introduce new people because, well, I mean, you bring fresh ideas and so on, so it makes sense. So yeah, we evaluated this, and that's it. Like, then during this implementation, however, like we always need to think, okay, how powerful we make this feature, how far we go. Like, so yeah, usually it's very important to understand that it's not about being as generalistic as possible. It's about enabling what you want to enable, and even if you know that you can improve certain things, just stopping there. What I mentioned before of like following similar architectural patterns in a system like Aave is very important, because sometimes just by following like the organization, you will not, let's say, shoot yourself like with an unexpected bug. And also thinking very careful about integrations, like, because Aave is, well, I mean, the users integrating is not end users, it's other protocols, like, so we need to be pretty careful with that. Yeah, the other is like another feature which is quite different in nature, is virtual accounting. This was actually before liquid emotes. And what we hear is that like Aave was operating all the time from inception dynamically in terms of checking, let's say, how much available liquidity there is, using balance off of the tokens. And how it works is like at some point, well, I will pass to the typical questions, but at some point we noticed like that there were more and more exploits related with inflation attacks and any type of manipulations related with balances. So we did like some introspection in the team, like in the protocol. We also involved like extra security researchers, like, and then we decided like to implement this virtual accounting. So yeah, when we analyzed like about the complexity added to Aave, like actually was not so much, mainly because it's kind of incremental defense, like, or we call it defense in depth too, meaning that there is not really much you can destroy like by introducing this. The only thing that could cause is like maybe overprotection of the system, but it's, I mean, of course, if you do it wrongly not, but it's not so easy like to actually introduce a very big bug, like because of the nature of the logic itself. And then also, yeah, it was review friendly, like the code footprint was relatively small, I would say, which, but it had like high level implications, like because certain invariants of the system that before they were understood by using balance off, like on certain smart contracts, like it's not anymore. Now they involve like a storage variable, like which will be the virtual balance. And for that reason, this particular feature, we thought that it was good to have a security context too, like because it's, well, quite non-Aave specific. Like, so in this specific case, like having more eyes and fresh eyes, like it could give value. While in certain other Aave features, like having certain expertise on Aave or a lot of expertise on Aave really gives like way more value than coming from scratch. So yeah, the same as with the liquid emotes, still like we did this last question of how far we need to go on this. Like, so yeah, like the main priority here was to make it as non-invasive as possible, the feature. Then evaluating all the effects and like potential consequences that could arise, like because of what I mentioned before, of not being so dynamic anymore, not using balance off, but having internal accounting, and especially like something that is a recurring, let's say, challenge like on Aave, is that every time that we do an upgrade of the code, you have production data, like of thousands and thousands of users, like of capital. So you need to be very, very careful, like whenever you reinitialize that data or whenever you do any type of so-called migrations of data. So in this specific case, obviously, this virtual accounting didn't exist before, but the moment that the upgrade happened, you needed like to just initialize like the whole thing. So yeah, yes, to end, like a small overview of I think that maybe the Aave security procedures are slightly different, and yeah, mainly the ecosystem around Aave more than the procedures. So yeah, I will not repeat, but obviously we do the, let's say, typical stuff like testing, review, formal verification, fuzzing, like yeah, you call it. Probably it was done at some point of the chain in Aave. But I would like to highlight this, which I think is a practical example of something that is not so common. Like, so in Aave, I say like that we have organizational defense. Like, what that means is that, similar as with Ethereum, I think that like the resilience of Ethereum sometimes is because there are so many teams contributing to Ethereum, because there is not really like a voice with full authority, like in the roadmap of Ethereum or like almost any aspect. So yeah, as I say before, like in Aave, we try to achieve the same. Like, so at the moment, Aave is really fully decentralized, controlled by like on-chain governance contracts. Best example is that like, my team like is just engaged with the DAO, like which release certain budget and authorized via a smart contract services agreement, let's say. So this natural consequence is that there are multiple also technical independent entities involved with the development of and the security of the protocol. So yeah, it's of course us. There is I put also Certora, which contributes independently on the security side. Even of obviously we collaborate closely. There is also like Aave Labs, and there are multiple others actually. And then even we have also like independent emergency entities, which can be in the shape of multisigs or so on for emergency functions of a bug is detected and if the system, let's say, needs to be paused. So yeah, this gives quite a lot of value. Another point is like that all the changes of Aave need to happen via the governance or the 99.9% of them, and they are not even created by the technical team of Aave. Like what we do is review those changes, but at the moment there is like I think regular 4 or 5 entities out there. Some of them are not even so technical, which are creating governance proposals for whatever, like listing new assets on Aave, changing parameters, I don't know, proposing new deployments on new networks, like countless things. Like, so yeah, there is some repository where people just does PRs, we review them, then there is even another layer of review by Certora, and then they get voted on chain, and if everything goes well, it gets executed on the Aave system. Yeah, right now we are even like trying to decentralize like the organization on GitHub, which is a bit challenging, but so like the Aave protocol lives in this Aave DAO, and progressively the idea is that multiple contributors like will be having the repositories that they maintain, which is associated with the DAO. So it's kind of everything is property of the DAO, and then you have like the maintainers or stewards of that. And yeah, well, I mean, we maybe treat a bit different like of like the relation with the security experts. Like so, this is more about like our team. But for example, we like quite a lot like to have continuous communication with when we do security reviews. We are not so much into the business of like giving some code to review and coming back at the end. We prefer just to talk quite a lot with the auditor because it's pretty good both for us and for the auditor to get a better understanding. It's true that also like in some cases certain isolation is desired, but we are quite, I mean, we think quite a lot about these topics, like so depending on the feature even maybe we want to have more communication and in some other features not. And yeah, well, we try to put a lot of focus in documentation, which requires like some improvement still. Like, but yeah, we think that one of the problems on the communication between developers and security firms, like, is that well, it's not well explained what the developer is trying to do. Like, so that just creates like a snowball effect on everything else. And yeah, that kind of is an overview. If any question?
Thank you so much, Ernesto. Maybe while Emilio sets up, a quick question from me. So I think Aave is seeing one of the biggest evolutions, which is the first non-EVM deployment of Aave happening. How do you evaluate that type of decision with regards to the framework you presented?
I mean, like, it's slightly more challenge, like, because obviously we have frameworks to evaluate like the EVM deployments by themselves, but those frameworks are unavoidable, like link like to EVM characteristics. Like in the case of the one non-EVM, like this changes a bit, but I think that we can adapt, because at the end of the day, like it's more about having the procedures and the steps well defined, and then if you need to adapt some of the steps, well, I mean, it's just fine. But hopefully it will be, yeah, in the next months, I think there will be Aave in non-EVM, pretty sure. So.
Awesome, thank you so much, Ernesto. And next, we have another Aave session, Approaching Security with Aave V4 with Emilio.
Okay, perfect. Microphone is on. Cool. Great. Nice to see you guys, everyone. I was already here yesterday. I see some familiar faces, so that's pretty cool. Quick introduction. My name is Emilio. I work for Aave Labs as a contributor to the Aave DAO. And we are currently involved as contributors to the DAO to develop like the new version of the Aave protocol. Long story short is that a few months ago, Aave Labs came out with a proposal to implement a new version of the protocol. This new version of the protocol stems from observing how the protocol has been behaving and evolving over the last couple of years. We just saw the great presentation from Ernesto from BGD Labs. They are the main contributors and main maintainers of the Aave protocol, and they have been responsible for some very interesting upgrades of the protocol. They introduced liquid emotes. They will be introducing the umbrella upgrade for revamped tokenomics and like developed around Go. And we have also seen the procedures that are in place within the DAO to make sure that any new feature, any advancement, any upgrade to the protocol goes as smooth as possible and without any risk for the users. And this was also when we started brainstorming about what we could improve with Aave V4. This was also one of the, I would say, one of the topics that we discussed. So what was the process, the thought process behind like the idea of Aave V4? So what we have seen with V3 is that there are quite a few great, I would say, features and great powerful points for Aave V3 that basically make Aave protocol the largest DeFi protocol in terms of TVL. So there are many, actually. I just pointed out like what I believe is relevant to me for this particular presentation. So I can think like of the great capital efficiency of the protocol because the pooled approach of the assets, because of some features that the protocol implements, like emote and most recently liquid emotes introduced by BGD Labs, which allow basically higher capital efficiency whenever you are using assets that are kind of correlated with each other. Because of the pool model, we also have great UX for borrowers because rather than having multiple positions to manage and rebalance, as it could happen, for example, with protocols that have higher capital segregation. In Aave, in general, you can manage everything in one big position, and like collaterals are treated homogeneously, and debt positions as well. So instead of having to move your capital across different positions that are maybe a single collateral, a single borrowed asset, it's much easier to manage from a user perspective. And what are some of the minus of the current implementation that we believe can be improved over the current version of the protocol? So one pretty clear feature that we are missing at the moment is that we are basically unable to price risk efficiently. So one of the main problems with Aave V3 is that we do have quite strict risk management, but the only thing that you can manage there is actually risk exposure. So you can say how much you want to be exposed to a certain asset, but that's actually not enough, because you should be able also to say how much a certain asset should pay for that risk that the protocol is being exposed to, right? So for a collateral, it's not enough to be activated as collateral and to have certain caps that limit exposure, but it should also be possible to say that a certain collateral that brings a different risk profile should be paying a different amount for the liquidity that is provided against that collateral, right? One example is like the CRV situation that we had a few months ago, where there was this large position that like at some point went under the threat of liquidation. And because it was so large, it could have basically posed a risk of insolvency for the protocol. And the ideal course of action for the DAO in that situation would have been to actually rebalance the risk by increasing the capital requirements to borrow against CRV, so that the position is either paying an amount that is equivalent to the borrow capital that is, the amount of the capital that is borrowing, or that borrower is incentivized to leave the system and to reduce the exposure and therefore the risk. It's harder with the current implementation to allow permissionless innovation. One example is that like the current approach that we are having with custom ad hoc markets, where you can basically have markets that are deployed and configured for certain specific use cases. So I'm thinking of the HitterFi market, of the Lido market. Shortly after will be the Ethena market, and so on and so forth. All of those require quite lengthy processes in terms of deployment and in terms of governance requirements, like a variety of proposals, the full governance process, and so on and so forth. It would be better, in my opinion, if there were a way for users to actually, and for entities that actually want to use and want to configure their markets for their own needs, it would be better if they could do them by themselves, and then eventually being endorsed by the Aave DAO and being supported with the risk management and everything else that comes by being endorsed with the DAO. There is a lot of governance work with the current implementation. So besides the deployment of the new markets, we have seen there are a lot of risk parameters change. There are a lot of configurations that are applied all the time. The deployment of the market requires a lot of governance work. And from a strictly security perspective, the Aave V3 code base is really big. So we are talking like 7,000 lines of code. And can we do actually better? Can we optimize it further so to reduce the surface of attack? So all of these are the thoughts that basically brought us proposing the new version of the protocol. I already did some presentations on the topic, so I'm not going to focus on the features because I would be talking for 5 hours. So like, I will be very quick on these features because I want to focus more on the architecture that we are thinking. In terms of features, I already mentioned in the past, like risk premiums, dynamic risk configuration, and fuzzy interest rates. These three are aimed at solving mostly or reducing mostly the impact of these two shortcomings that I mentioned before, inability to price risk appropriately and reduce the governance overhead. So for example, dynamic risk configuration will allow risk managers to create new risk configurations only for the new users without affecting past users, which will basically allow the DAO to offset completely risk management or almost completely risk management without changing the security guarantees of the system. Fuzzy interest rates, which is like a control mechanism that we are implementing right now. And it's with the idea of being able to adapt the base rate and the slope point dynamically of the interest rate curves so that the interest rates can change accordingly to market demand more quickly without requiring governance work. And then the risk premium that I already mentioned before is like giving the ability to basically price the risk of a collateral independently from the others. So these are a subset of the features that kind of cover some of the aspects that I mentioned before. But what I want to focus today is going a bit more in detail on the architecture that we are thinking about and how it will look, hopefully, when the implementation is going to be finished. So part of the work that the DAO does today, I think, is due to the architecture of the Aave protocol. Because of the design of the Aave protocol, the pool design, and like the monolithic approach that we took when we designed Aave V1, V2, V3, it is a bit harder to allow permissionless changes. So, for example, listing an asset requires, again, a governance process with accordingly risk evaluation that is done accordingly, oracle creation, and so on and so forth. Deploying new markets, as I mentioned before, requires a full governance process plus the complexity of trying to bootstrap the market because the market will start from zero liquidity, and to attract users to the market, you will need to find some way to bootstrap liquidity. And risk configuration, like there is no way of changing risk configuration without affecting past users. So every time you try to reduce the liquidation threshold, if you want to offboard an asset, for example, you need to slowly reduce it by 1-2 percentage points to prevent users from getting mass liquidated, and so on and so forth. There are a lot of aspects. So a very general, I already mentioned in previous presentations, a very general abstraction level. We are thinking of separating part of the protocol in a way that we can create a more modular approach. So what I mean by that, if we look at the current Aave protocol implementation, but even the past, that's the part that kind of sparked this idea of modularizing a bit more the architecture. In the protocol, that is a monolithic piece of software where we have this pool contract that basically handles all the user interactions. Of course, internally, there is modularization, so we have split the code in libraries, subcontracts, and so on and so forth. But this modularization is, I would say, top-down, because at the top level of abstraction, you don't see it. You see one piece of software, it is the pool, and then going deeper in the architecture, we'll see the different aspects and different modularization within the code. And we can basically identify two main layers within the Aave protocol code. One is the liquidity management part, and the other part is the borrowing management. So if we think specifically about the liquidity management, and we observe how that part evolved over the 3 iterations of the Aave protocol, we can basically notice that there was essentially no change. So everything that was related to liquidity management, interest rate management, indexes, accounting, and positions management, and so on and so forth, is basically unchanged compared between V1, V2, V3. Most of the changes that we can see happened at the borrowing part, where we kept adding features. So we added the stable rate, we added the credit delegation, we added E-mode, isolation mode, liquidity modes recently, different liquidations mechanisms, and so on and so forth. So from this idea and by noticing this particular aspect of the protocol, we started thinking, OK, why we don't take the liquidity management part out, since it's basically unchanged from the beginning, and then think of it as a component that can live by itself. And then the borrowing part, we generalize it in a way where the liquidity management part doesn't actually know about the borrowing part. This would make things much easier, right? This is also kind of an evolution of one feature that we added in Aave V3 that is called portals. So with portals, the idea initially was to essentially allow other entities of Aave markets, possibly cross-chain, to draw liquidity from the largest Aave markets to bootstrap them onto or to optimize the capital efficiency, right? This vision actually never took traction for a variety of reasons, because when we developed V3, we were thinking that probably L2s would gain much more traction earlier, much earlier than we actually are witnessing. So that reality has not really fully realized yet. And also, like, there were a series of complexity related to bridge, security, and so on and so forth, which I'm not going in detail right now. So when we pair like this idea of portal, which it was basically first attempt to move liquidity out of the markets to optimize the capital efficiency, and the realization that we have a part of the protocol that never changed, essentially, since the beginning, this brought like the realization that actually we can take this part out and start developing it independently, so that then we can build on top of it other modules that actually also work independently, and this will hopefully bring much more simple code, better capital efficiency, and also reduce governance overhead, as we will see later. So we are currently developing for V4 this component that we call Liquidity Hub. The Liquidity Hub basically handles everything that is basic user functions, so supply and withdraw. Handles the accounting, so interest rates accounting, the interest rate strategies, and the liquidity premium. And it's actually completely agnostic to the modules that will draw the liquidity and will extract the liquidity out of the liquidity layer. The liquidity layer doesn't need to know what's going to happen with that liquidity. The only thing that needs to know is that like modules that will build on top will pay the interest that the liquidity hub is actually asking for. So the liquidity hub will have like a generalized accounting for all the modules that we build on top of it, and it will not know what's going to happen with that liquidity. You know? So it can be a borrow module that actually works exactly the same as V3. It can be a module that, I don't know, borrows against RWAs that are held in isolated vaults. Can be a lot of things, as we will see later. So what about the borrowing? It can be completely, if we follow this design, it can be completely abstracted away. So we can take all the features of Aave V3 and implement in a module that works by itself, that doesn't need any knowledge about the inner dynamics of the liquidity hub, except the ABI, so the interface that allows communication with the liquidity hub, and can be tested separately, which is great. Liquidity hub can be mocked, so we can build the liquidity hub and the borrow module in parallel, which is something that we could not do with previous version. And most importantly, we can have a variety of borrow modules, not just one. You know? So that's part of the thought process that is shaping like the form that the Aave V4 is taking. So we call this a hub spoke design. So hub spoke is in general is a very common architecture and the modularized design philosophy that is very common in a variety of industries. Common in transportation, is common in data science, a lot of different fields. And so the idea is that we have this liquidity hub at the center that handles the assets and handles all the accounting. And then we have a variety of spokes. We have spoke number 1, number 2, number n, potentially. These spokes, they draw liquidity from the liquidity hub. They use them in a certain way. They will return it at some point by paying a certain interest plus a premium. That's the idea, okay? And so this generalizes the design that we saw before and opens up to the possibility of having multiple spokes within one liquidity layer. So this is the general flow of operation of how it would work. Users supply liquidity to the liquidity hub. liquidity hub tracks the total liquidity, the usage ratio, the interest rates, and the average premium. The spokes, whenever a user requires borrowing, draw liquidity from the liquidity hub. And liquidity hub keeps track of the total liquidity drawn and eventually the liquidity drawn per spoke so that you can set caps for every spoke eventually to limit the exposure that the liquidity hub gets into a certain spoke. And spokes, whenever they return the liquidity back, they pay the liquidity rate that was accumulated plus a premium. And the premium is decided by the spoke through the risk configuration of the specific spoke. And the spokes can fetch the balance. Spokes have one major requirement. When users borrow liquidity, the major requirement is that there is a proper collateralization ratio that is not violated, otherwise there is risk of insolvency. So the idea is that the spokes can fetch the balances from the liquidity hub to understand the capital allocation of a user, for example, and how much collateral they have, right? So this poses a few challenges. So what we are thinking is, okay, how do we manage multiple spokes fetching balances from one liquidity hub? That can get very, very complicated very quickly. And the reason is that it's really hard to understand when a user supplies liquidity, if, for example, a user is borrowing from a variety of different spokes, to which spoke that collateral is being allocated to, right? So we are thinking of a variety of designs. One design that we are thinking about is the potential of using, for example, a master spoke. So we will have a master spoke, and the master spoke is the only one that is allowed to draw liquidity from the liquidity hub and also use the accounting within the liquidity hub to calculate collateralization factors. And then we have secondary spokes that can be n, an unspecified number, which the only capability they have is basically to draw liquidity and return it. But the collateral and the collateralization ratio needs to be accounted in and stored in a different venue than the liquidity hub. So basically, this would be a fully generalized portal design. This is currently the design that we are evaluating for the liquidity hub and the spoke design, but it's not the only one. The cool part is that thanks to modularization, we already started the liquidity hub, and we have the luxury eventually to decide which design we want to use much further down the line, because we can afford to develop the liquidity hub basically independently from the rest of the protocol. So the secondary spokes, if we go with this design, which is still not 100% guarantee, but is currently the design we are leaning into, the secondary spokes can be anything. They can be isolated collaterals, they can be RWA based, or they can even be other liquidity hubs, which is the cool part that enables a lot of interesting aspects that I will talk about shortly. So if we look at this diagram here, I put like an example that how it could potentially look going forward. So before I explain in detail this diagram, like I want to clarify that one of the features that we are going to implement in V4 is called smart accounts. So we want to give the users the ability to borrow from Aave without actually supplying the collateral into Aave. This was a feature that was requested for a long time. The collateral would be in a separated smart contract. It could be a vault, it could be a safe. We are actually evaluating to build on top of the safe, so you would be able to borrow directly from your safe within the Aave without supplying the collateral first into the liquidity hub. And this was requested for a long time. And the reason why users are requesting it is that either they don't want to take the risk, the liquidity risk, by earning, I don't know, like just a few percentage points of interest, or they cannot, for legal reason, mix their collateral with other assets of unknown origin within the Aave pool. So this would basically help them allow to solve. And then we have isolation mode that we already have in V3, but it will get, with this design, we'll have a completely different approach within Aave V4. So in Aave V3 is implemented as a standalone feature within the monolithic design. So it's a feature with a variety of edge cases. with this approach, actually, isolated asset, they become a separate market. So it's going to be a separate market with a separate liquidity hub with only assets that match the same risk profile. And what we can do is that we basically connect this liquidity hub through a secondary draw module to the main liquidity hub so that the DAO can, for example, give to the isolated assets pool the ability to draw liquidity up to a certain cap from the main liquidity hub. So you have basically the same design that we have today in terms of debt ceiling, but within a separate module, a separate liquidity layer, and a liquidity hub, which also gives the ability to eventually users that want to get exposure to higher yields by supplying directly against isolated asset, they can do so. We cannot have this feature as it is implemented today in Aave V3. So with this design, we can have users going straight to the secondary liquidity hub, for example, and earn a higher interest because like assets that are isolated usually should pay, thanks to premium, a higher interest rate. And also the smart account spoke could, for example, just draw liquidity from the liquidity hub and then keep the collateralization in safe wallets, for example, where custom hooks can be installed to prevent users from moving asset if they are borrowing and so on and so forth. So this particular diagram is interesting because it shows how rather than having a very big and complex monolithic borrow module, with this design we can split them in separate parts and have smaller, easier to test, easier to implement modules that actually interact with one main coordination hub, which is the liquidity hub. So to finish, because I think I don't have any more time, yes. From a security perspective and like ease of implementation perspective, there are a variety of advantages, like Spoke and Liquidity Hub can be implemented separately, which is exactly what's happening at the moment, because we are mocking the features that we expect to have into the borrow module, and we can actually implement the Liquidity Hub by itself, thanks to the completely abstraction that we are building into it. Everything can be mocked, which is something that we could not do before. So we don't really need a fully functional liquidity hub to test the borrow module. We don't really need a fully functional borrow module to test the liquidity hub. That's very cool. And that makes the development much easier because then we can implement, for example, the modules that we saw here, all of three in parallel. We don't need to implement like them as a unique monolithic piece, but we can implement them separately. And in the future, it will be also easier to replace spokes or implement new spokes. So there would be a lot more to talk. I don't know why this is pixelated, but it's, it's good enough. And yeah, there will be a lot more to talk about on this particular topic. It's been very exciting until now. And we hope to have something to show to the DAO and to the rest of the community very soon. That's it. Thank you guys for listening. And if you have questions, I'm happy to answer. Yes.
Thank you very much, Emilio. I'm really excited to see.
Do we have time for questions?
Unfortunately, we don't have time for questions. But
I will be out here answering.
Emilio would be happy to answer questions outside. Thank you so much, Emilio. Next talk is by Igor. It's going to be about the specification and model checking of the ZK Sync governance protocol. Take it away, Igor.
Okay, thanks a lot. Thank you for the introduction and having me here. So what I want to talk about here is specification and model checking of the ZK governance, the ZK governance protocol. That's actually the work by Dennis, colleague of Metro Labs and myself. And I want to say that Dennis wrote a large part of the specification, and I helped him with the choice of proper abstractions, writing the protocol invariants, and model checking experiments. So it doesn't click. Okay. So before we start talking about the specification, let's just have a brief look at what ZK scene governance is about. Basically, in ZK scene governance, we have 4 entities. The largest one is the token assembly that consists of the token holders and the delegates who can propose some contract upgrades. And the other 3 entities have to ensure that these upgrades do not do anything bad, essentially. So the token assembly can propose these upgrade proposals, and the other 3 entities can vote on accepting them or rejecting them. In addition, these entities can also do some kind of emergency upgrade proposals and execute emergency upgrades. And in addition to that, the Security Council can freeze and unfreeze layer 2, which is quite important in this case. So that's ZK scene governance in very brief. There are a lot of happy path scenarios. The simplest one here is that this emergency upgrade board executes the emergency upgrade. Very simple, essentially 1 call, all done. How about more complicated scenarios? Well, shall I click? Okay. So actually, if you come to this protocol as I did, as an external person, how do you find these happy path scenarios? One way is just to talk to the developers, but another way, as I did, is asking the model checker. In this case, I'm just challenging the model checker and tell it, look, it's impossible to find a proposal that has been executed and it was approved by the guardians. And the model checker comes back and says, no, it's not true. Here's a counterexample of 5 states. How does it look like? I'm not going to give you the actual counterexample here, but I'm going to give you this graphical picture that is much nicer. And the counterexample looks like this. You have the Security Council that starts an upgrade, then some time passes, there is this magic period of 72 hours, then the guardians approve this upgrade, another period passes of 800-something hours, and then someone executes this proposal. There are a lot of scenarios like that. It's not just 2 scenarios, right? And for this reason, we want to have this protocol specified and also to have the invariants specified. In this work, I'm using the language called Quint. It's a relatively new language. It's actually quite old because it's backed up by the temporal logic of actions that was proposed by Les Lampert a long time ago, but it's a new syntax that makes it more friendly for the engineers to write and treat properties and the specifications. What I find very useful about Quint is that we have essentially 3 tools here. One of them is a randomized simulator. Think about it as property-based testing, stateful property-based testing, or a simple form of fuzzing, as you can see in Foundry, for instance. And what you see here are these yellow lightnings on the radar. These are basically concrete executions as the simulator tries. It may find bugs, it may miss bugs, as always, right? There is a randomized symbolic executor that covers larger sectors of this radar picture, and it can find more bugs, but it can also miss them. And there is a bounded model checker that covers the whole radar up to some range, and it's not going to miss bugs up to this range, but it can miss bugs up to larger, longer ranges. The tool set requires very minimal setup. It's written in TypeScript, basically in Node.js and VS Code, or maybe Java if you want to run the model checker. So that was way too fast. Let's talk about protocol specification. Basically, how do we go from the Solidity code to the specification written in Quint or any other language, actually? Where's the catch here? So Quint or TLA+, they are not tuned to Solidity. They are not tuned to Ethereum virtual machine. They have no idea about blockchains. These are general specification languages. It's kind of a bad thing because you cannot use the standard primitives. There are no standard primitives like this. But it's also a feature. It's very easy to add additional reasoning capabilities to your specification. So at a very high level, what we have here, we have the protocol specified as a state machine. These circles are basically states of the EVM, and the arrows are the transitions between the states. These transitions correspond to transactions, or what we call actions. And you have this computation tree that progressively changes the states. What's important here that actions may have non-determinism, which corresponds to choice of different transactions and choice of different inputs. So, okay. Since I told you that there is no built-in EVM state, we have to model it. How do we model it? In the case of this protocol, we just add all the necessary features that are required in this protocol. For instance, we add the block timestamp, because it's important here. We add the states of all the contracts we are modeling here. In addition to that, we add the abstract states of L2, only the information we need from L2. And we add some history variables because we use these history variables in the invariants. So it's very simple, it's just a record, no magic. How do we specify the contracts? Again, there is no solidity. So a contract for us is just a record that has fields that basically correspond to the fields in the contract. There is no constructors, so we define an operator, which is basically a function from the arguments to the result. And the result can be OK, which gives you the state of the next state of the contract, the new state of the contract, or it gives you an error with an error message. So that's basically how we construct the contracts. How do we specify the behavior? Again, nothing complicated. We just have pure functional definitions here, which take as the input a state of the EVM plus the states of the contract, as you have seen. It takes, the definition takes the input parameters. It does some computations, no side effects, no exceptions, just straightforward functional computation, if you like. And it either returns an error again with an error message, or it returns OK with a new state. And basically, we capture the behavior of the smart contracts by doing these functional specifications. So once we have done with the behavior of individual functions, we combine them into actions. And the difference between operators and actions is that actions can contain non-determinism. So non-determinism means we can pick input data non-deterministically. You see there on top the choice of sender from the set of all senders. So just pick non-deterministically. Then we execute some operators, which are purely functional, as I told you. Once we have executed them, if everything is OK, we update the state variables, our state machine progresses. That's one of the actions. We have many of them. And again, we basically say that a single step of the state machine is a non-deterministic choice of different steps. Who makes this choice? We don't know, right? But that's your state machine. So that's basically the protocol specifications. There are a lot of definitions like that. There are a lot of actions like that. I would say probably 40 actions or something like that. How do we specify the invariants? This is a bit more interesting because here we don't have any solidity code. We have only English, right? How do we go from English to this specification? For instance, this is one of the requirements we have got from the developers, which is saying unfreeze may be called from any address after the freezing period has been reached. How do we specify it? Actually, in Quint, we can just write a state invariant, which basically says that if the current state satisfies these conditions, that the block timestamp is greater than this freezing period, and the current freeze status is in freeze, a soft freeze or hard freeze, then we can execute this functional operator, and it should return us OK. Since there are no side effects, we just execute it and check the status. Very simple. That's a state invariant. We can check it in any state of the EVM, and that's it, right? So that's a very simple invariant. We have plenty of those. There are also more complex invariants. For instance, this is one of the requirements from the governance procedures that are actually written in an actual document, right? Once frozen, an emergency upgrade may be executed in order to remove the freeze and or initiate a subsequent freeze. How do you specify that? There are some formal methods people in the room, they would tell me it's temporal logic. But I'm not going to use temporal logic here. Actually, we can specify this stuff as a state invariant. Again, what we do, we go over all possible parameters here. We execute some operators. We check some preconditions here. And then we do something interesting. We can actually execute one of these functions, check that it was OK. And then, based on the state this function has compute, like EVM3 here, we can execute other functions, compute new states. But since it's all free of side effects, we can actually compare alternative futures. We can say that from EVM3, you could go to EVM4 and execute soft freeze, and it should be OK. Or from EVM3, we could go to EVM5, execute a hard freeze, and it should be also OK. This is very interesting. I have never seen anything like that before, actually. Can talk about alternative futures inside the state invariance. So that's a very neat modeling trick if you want to reason about things like that. And basically, we don't use any temporal logic here, which is a bit surprising. So by applying these tricks, we basically specify a lot of invariants from the governance procedures. We have like 45 invariants. Some of them are more complex, some of them are simple, and so on and so forth. So how do we check these invariants? I told you that there are 3 different techniques. What's the difference? Basically, if you look at the actions, if you look at this step, and if you look at the definitions of each actions, you will notice that there are 2 key constructs here. One of them is called any, and that's basically saying I choose one of the actions non-deterministically. That's what we call control non-determinism. And another construct is this non-det, new timestamp, blah, 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 one-off. One-off is data non-determinism. Basically, either you choose an action or you choose a piece of data. Both are non-deterministic. How do we resolve this non-determinism? And the difference between these 3 tools that we have is that they resolve this non-determinism differently, in 3 different ways. So when we are talking about the randomized simulator, it picks everything at random. It picks actions at random. It picks data at random. Very easy, very simple to understand, maybe not so powerful. When we talk about randomized symbolic execution, it picks actions at random, or transactions if you like, and it offloads the task of picking the right inputs to the SMT solver, to Z3. And this is done in the model checker called topology. And the third way, we actually offload the task of choosing the proper actions and choosing the proper inputs to the SMT solver completely. That basically gives us the bounded model checker, which analyzes computations up to some bound. So these are 3 different tools. Actually, the 2 tools below are the same tool, just implementing different exploration techniques. And what I want to stress here is basically we are not doing complete verification with these 3 tools. What we do somehow progressively more complex and more expensive analysis. We start with a randomized simulation, which is essentially cheap. It probably doesn't have this good bug coverage. Then we go to randomized symbolic execution. It's more expensive, but it gives you a bit better bug coverage. Then we go to bounded model checking. It's in some sense exhaustive because it analyzes all executions up to certain depths, but it can miss long executions. And in the very top, you have this golden grail of formal verification. We are not kind of trying to achieve that, but we are trying to analyze the bugs to find bugs faster. And this somehow resonates with this recent talk by Mike Dodds of Galois, where he says we should try to make our favorite formal verification methods cheaper and move them to the left. That's how you can move them to the left, basically. OK, So that's basically about the techniques. And now I want to give you some ideas of how long it takes to check all of these invariants. So for instance, is it here or there? Keep clicking it. So for instance, when we check one of these invariants, we have specified, we run 100,000 randomized runs up to 30 transactions each. And it just takes 3 hours. It's actually not a lot, right? It's very fast in some sense. We could run 1 million random runs, and it would take, well, 30 hours, I would say, 1 day. Would we find all bugs? We'll find a lot of bugs, actually. Not in this case, but in other cases, we would find some bugs. Will we find all bugs? Actually not. When we run the randomized symbolic execution, it takes longer, even for 1,000 symbolic runs, up to 30 transactions. It may uncover more bugs. And in our activity of writing the specification and the invariants, we actually found a lot of bugs in the specification itself and in the invariants we're writing. And finally, bounded model checker, it's kind of slow, right? It takes 5 days to analyze all runs up to 9 transactions. But it's all runs, even though it's slow. And this figure gives you an idea, basically, when we ran bounded model checker up to 6 transactions, it was run for half a day. Not so slow. But actually, it has uncovered 4 problems in the invariants. Luckily, these were not problems in the protocol itself. They were problems in how we wrote the invariants. But it still has found some bugs, which actually surprised me, because we did a lot of randomized stuff. We did a lot of randomized symbolic execution. We did a lot of randomized simulation. And still, the bounded model checker has found some issues. Then we ran the bounded model checker up to 9 transactions. Some of these experiments even timed out. It took 10 days, really a lot, right? And it has found no further issues. So we're kind of convinced it should work, more or less, right? So there are some kind of questions of how you do more advanced modeling. If you want to check it, I'll give you the link to the slides. I don't have time to discuss it. One thing that I want to stress also, that there were other code audits done in parallel to this work, and there were some submissions saying this issue can happen or that issue can happen. What we could do, we could first of all reproduce these issues in the protocol, and after fixing the protocol, we can check that these issues are gone, which is quite useful if you have a protocol specification and the invariants. And writing a new invariant once you have written like 40 of them is not even hard. OK, so that basically finishes my talk. If I can go to the last slide. Basically, that's the summary. What I want to stress here is that understanding the protocol is essential. It's not only about the low-level problems like overflows, or some problems calling a strange address, which is, of course, important, but also understanding the logic of your protocol is important. And we believe that protocol specifications help you to write invariants, because looking at the code, it's a bit hard to write invariants. Also, I want to stress that we should use all the tools available, like randomized simulation. I was kind of skeptical coming from formal verification. I was like, it's randomized, it finds nothing. Sometimes it finds bugs very fast, but sometimes it misses bugs. So we have to use different tools that have different strengths. Of course, this work doesn't replace code audits. There were some code audits done in parallel, and they focus on different things. Finally, if you want to check all these things, here's a QR code. You can check my website. We have a blog post that summarizes all this experience. You can read it in detail, and you can check the tools we were using. Thanks a lot. That finishes my talk.
Thank you so much, Igor. We have time for one question for the audience.
There is a question.
The lady in the back.
Thank you for that talk. What scenarios would ZK Sync freeze the protocol for?
What's that? I couldn't hear it.
What scenarios would there be that would cause ZK Sync to call the freeze? Could you hear that?
Well, I mean, that's basically the Security Council can invoke freeze. And there were like different ways you could do freeze. You could do this soft freeze, hard freeze. And there were also some issues when basically where you could do, well, you could do hard freeze and without executing emergency upgrade, you can unfreeze and do hard freeze again. For instance, there were scenarios like that we have seen. And they were basically fixed, they were basically found in parallel audits. I cannot claim they were found by us, right? But we could reproduce them. Yeah.
Okay, thank you so much, Igor. And for the next talk, we're gonna have Andrew tell us why Web3 security is embarrassing. Andrew, tell us how you really feel about Web3 security.
Okay, cool. Yes, I will really tell you how I feel about this. This is my talk. Web3 security is embarrassing, and in very small text that you can't really see. While we can and must do better. So a little disclaimer at the beginning. I really love security. Like I go to a lot of security things. I always hear people who are like, oh, I enjoy bouldering and cooking, doing other things. I don't. In my free time, I also enjoy security. So I do security at work, and then I also do security for fun. I also love drama. It's great. That's why I work in crypto. I will definitely be able to convince you why you should watch Survivor if you do risk assessment. And I also love ranting. So that's likely what you'll get here. OK, so who am I? The alias that I usually use is Andrew Mohawk. You'll never figure that out, why I picked that. It's because I'm very creative. No, I picked it when I was very young, and now I have to deal with it. So my background is I worked at Biterva for 10 years. We built Multigo. Then I did incident response at BitMEX. I set up incident response and detection response at Robinhood. Then I was a head of security at Uniswap, and now I'm at Privy. And big shout out to Privy for letting me do this talk after a month. They're an embedded wallet company, and my talk is about to rage about wallets. So that's really nice of them. Also, I'm part of the Black Hat Review Board, and I've been part of SEAL for a while now. OK, so it'll be a short rant in 4 parts. It's short because this is the longest slot we have. If there was a 2-hour slot, I would fill that up. So start with Web3. It's obviously Web 2+1. I'm really good at maths. That's how I figured that out. If you take like the traditional Web 2 stuff, our connectivity, the things that we add on that are like really functional here are it's inherently more financial, right? Everyone is using it to do things with assets that have value. It obviously has a much higher return on investment for attackers. And then there isn't really a safety net of providers like we see in traditional Web 2, like especially in fintech. So you have a user that directly interacts with a chain or with crypto, rather than saying, oh, it goes to a bank. You know, if my mom takes her card and she tries to draw all her money out in an ATM, the ATM is going to be like, whoa, you should go to the bank. But if she tries it in crypto, just kidding, she won't, then it will allow her to do it. It's obviously digital, so there's 24-hour coverage. And whatever you do, you have irreversible actions. So the first part is we are genuinely failing our users. Like it is security's job to keep everyone safe, to make sure that people make safe choices. And we are losing to, I don't know if you can see that on the slide, we're losing to ransomware. There are more funds being lost from phishing than there are from ransomware. How can we lose to that? That is always in the news. That's terrible. Then also we have 314 million lost in phishing in the first half of 2024. These numbers are crazy, so we should all feel embarrassed. Then also drainers are really cheap and easy to find. You can go on Telegram, there's hundreds of them. This one is like $600 for fully featured drainer. You don't actually need to understand crypto at all. So they will help you set it up. They will teach you to go through Cloudflare. They will tell you how to deploy it. They have automation that will help you. And they also have redundancy. So every now and then they get banned from Telegram or the channel gets banned. And they very quickly could communicate with all the people who have made purchases and get them into a new channel. I mean, that's a lot better than most crypto companies that I know. Sorry. The App Store is also rife with fake apps. So it's really difficult for us to get our real apps in there. And I think this was the part where I was like, wow, we're really losing. So when I was at Uniswap, there was like a fake Uniswap app that was in the store. And I was like, well, I've got some free time. I'll take it apart. I got the IPA, decrypted it, reversed it. And inside that IPA was just a web view. And it opened up, and there was just this big text at the top that said, enter seed phrase. And then there was a big block. It was a text area. That was it. And then there was a button that said submit. I was like, this person did not even skin this. Like, this isn't pink. There's no logo. Like, I'm losing to someone who literally went through like an HTML tutorial a few days ago. And, you know, they're making millions of dollars. So, a bit upsetting. Then also, obviously, we have dependency issues. You know, more recently with the Lottie files, but also, like, we see it regularly on NPM. We had the Ledger Connect thing. But this is something that we don't see in Web 2. Like, when was the last time Robinhood served up malware from their core site? Or any financial place? I can't even remember the last time that happened. Also, I'm not getting into smart contracts. There's lots of attention to that. A lot of your auditors, you're great at this. Also, every single workshop at DeFi Security Summit is about either smart contracts or EVM, except for one. So a lot of coverage there. It's also outside of the scope of this talk. And if you're old like me, then this is a layer 8 talk. Also really good at graphic design. So I've carefully crafted this that it's going to get worse. OK, so we'll start at the top, your dApps. So dApps, obviously the crypto applications, they're the pivotal point between the users and their wallets and the providers and underlying crypto. Okay? You have a responsibility to your users. If you build something, you should know that users are going to put their life savings into it. Right? You need to at least turn on logs. I've been in way too many incidents now where we'll get there, we'll be like, oh, something bad has happened. I also love incidents because it's drama. Something bad has happened. I'll be like, oh, great. Let's get the logs. Let's have a look. No logs. I'll be like, can we turn them on now? Unfortunately, time doesn't work that way, so you cannot. Also, if your application does really well, huge application, DPRK are going to try and cause some trouble, steal all your funds, that sort of stuff. So it's really important that we help our users, right? Because you're a super high value attack vector. And I think one of the core things that we always see is that we need to do Web 2 before Web 3, right? We don't have to speed run all of the Web 2 security problems. Like, they have solved some things. We should just take those and move on from there. And then our goal should be that if we're building things, we should be trying to help users make safer choices that are easier and that they want to make. Like, you don't want to tell them, hey, if you need to sign something, go to the roof, have your EM shield on, make sure you type in your password into your ledger. Every single time you need to go to OpenSea and say, oh, I'm signing in. Like, that would be ridiculous, right? Sure, it is more secure, but it's unusable. And I think a good example of where it has been usable is like the YubiKeys and passkeys. And also, I'm a WebAuthn maxi, so if you don't believe in that, come find me, I will convince you. Then the other thing is also like it's not externally facing only, right? If you are a group of engineers, even a small team that's running something, please just get a password manager and either use YubiKeys or passkeys. Like, that will cut out 80% of the risk that we see. And it's really important. Like, you're taking care of people's funds. You should do this. Then, of course, you need to secure your code. You write code, let's secure it. So if you have the money, get an audit of it, okay? We see places with like 7 smart contract audits and 0 front-end audits. It's really important that if you're going to let users interact with your things, you should audit all of it, right? If you don't have the money, you can also use something, well, I guess even if you do have the money, you should do this anyway. You can go to the frameworks, right? Frameworks is great, has a lot of like the foundational things that you'll need. You can see there, I got it at the corner, repository hardening, cloud provider hardening. These are things that you want to do anyway. Then I'm going to go on again about this. Please turn on logging. So if you're looking at like your risk assessment, you're going to say, what are the things that are going to totally wreck my company? Those are the things that I'm going to try solve first. And then you're going to say, like, what are the things that will totally wreck all my users? I'm going to try solve those. But actually what you should do is at the beginning, turn on all the logs, right? Make sure that you have logs of everything that happens. Just put it in a database. It doesn't really matter. And then you can try and solve those things that are very critical. Because in the event that something does happen, you want to be able to say, like, OK, I can see what happened, I understand it, and I can provide like a fix so this doesn't happen again, right? So I think that's really important. Then obviously you want to do the secret code and dependency scanning. Okay? You can do this for free. There is no reason that you shouldn't have this on by default. All of these things will integrate with GitHub or whatever your CI/CD is, and you can use the free versions. If you're making something that's open source, all of them are free. So Trufflehog will find your secrets, and it'll find it where you committed that key, and then you were like, oops, and then you write a commit over it, and then you're like, great, no one can see it. Everyone will find it. You just run Trufflehog, you'll get it. I found one in a very large NFT project last week. They can use socket.dev. They do the dependency scanning for JavaScript things. Really good. They'll be like, hey, this package suddenly has network access, or this package suddenly has new authors. You can also use Sneak Code for scanning code. So they'll be like, oh, there's a vulnerability in the code that you developed. This is how you should fix it. Then the last thing is plan for when and not if. So have a big red button that says, I'm disabling everything, right? Have a plan that says, like, oh, if our front end is compromised and the CTO is on a plane, we don't wait for him to land. We can still be like, hey, we're turning this off, right? Practice rotating credentials, because so many of the attacks we see are people who have like left the company, had those credentials from when they worked there, and somehow leaked them, right? You should just be able to rotate credentials always, and we see a lot of these. Okay, then also you should promote good engineering and security culture. So if you're building a DApp, and this is one of my favorite mottos that we have at Privy, is all engineering is security engineering, right? Whatever you are building, users will use, it will have a financial impact, especially if you're obviously building financial applications. Okay, now we'll talk a little bit about providers. There we go. So security is kind of like an arms race. Okay, everything is hackable. There's nothing that's unhackable. If you give me enough time and money, I'll break in. You just need to make that bar, higher. What we want to do all the time is like make it more difficult for attackers. I don't want to see them make it a text box next year. But one of the things that's really difficult is to try and get providers to change, right? Because usually you don't have a choice. If you want to have DDoS protection, you can't use anything but Cloudflare, basically, right? They provide the best service. So you're probably going to use it. But the only time that you're going to get a provider to make any changes that you want or to add anything to their roadmap is during renewal season. Okay? So if you're a company and you buy from a provider, just wait till it's renewal time and then be like, hey, what are you doing about all those Web3 phishing sites? So that's the best time. Please, if you have that, do that. Okay, as part of Seal, myself and Sam built this block list. It's like a MetaMask block list that we update automatically by scanning for stuff, so we can try and catch drainers ahead of time. And now it's Sam and others and a tiny bit of me. And that you'll see like when you get the red window that says like, oh, a deceptive site. So what I did was I went to look at all the domains and all the things that we've put in there, and I said, okay, well, who is hosting this? Where are these registered? So we have like some stats about it. There's like 226,000. 173 still have Whois data, and 127 you can still get to. Like you can browse to those things still, which isn't great. Also, it's very difficult to do 220,000 Whois requests, and my girlfriend will be very angry if I get a house ban from the internet again. So I reached out to some people. They hooked me up with Whois XML, who were super nice, and they were like, send me a CSV that's 200 megs, and I will send you back the Whois information, which is really cool. So then I built some scripts. I mean, just kidding. Claude built some scripts. I ran those scripts, so I have a lot of job safety. And here's what you'll see. So this one is the most important one. I basically have this whole section so I can have this slide. Cloudflare hosts 68% of all phishing sites that we have seen. Everything that we've seen for like known bad, they host more than half of it. And someone brought up like, oh, well, maybe Cloudflare does more than half of the internet. It's like, okay. But in their Q3 report from last year, they said they do 16% of the internet. So while they only do 16% of the internet, they are hosting 68% of these malicious domains. And there again, Cloudflare, please reach out to them if you use them during your renewal time. Ask them what they're doing. They also have a way that you can submit, but you can only submit one domain at a time. And I'm going to tell you that if I have to submit 128,000 domains, I will kill the computer before then. OK, registrars, kind of the same thing. They're a little bit more diverse, and I have the data if anyone wants it afterwards. Twitter, they're going to give away your account. 100%, if you are worried about this, you should be planned for it already. Follow the SEAL guide to set up Twitter, but at some stage, know that that is outside of your control. They almost made a really great thing where they said we could disable links and replies, which I think would have made the biggest difference in crypto to anything I could ever do, but they decided against it. AT&T and Verizon, these places suck. They're doing our SIM swap protection really badly. They've been forced by the government to do something, and they've done the bare minimum. So adding a note to my account that says, hey, if this person phones to have a SIM swap, ask them if their dog's name is Sandy, and if I say yes, then great, do the SIM swap. That's not any protection, so that's really annoying. And if you are worried about this, move to Google Fi. It's basically the only choice you have. Your SIM is locked behind your Google account, and your Google account can be locked behind hardware tokens or passkeys, so you don't have to worry about SIM swap. OK, now my favorite section. Ooh, we're running out of time. Wallets. Wallets are obviously like evolving rapidly. I'm going to be mostly talking about the extensions. And they take like, I guess the complexity of the underlying crypto, they make it easier for us to understand, right? They have great UI and UX. They have cute animations and sound and colors, and it's really easy to onboard to crypto with it. Unfortunately, they don't have the same guarantees, right? Because you can't say like, oh, I send all my money away, and someone says, whoa, is that what you want to do? Like, do you have to go into the bank to check that? No. Obviously, that's what we want. We want to be in control, but we lose some of these guarantees. OK, so then I was thinking about wallets, and I was like, well, what does a wallet know? If I use it, it's on my computer, it knows where I am right now. It knows my IP address, it knows my time zone, all of that stuff. It knows where I connect to, because I've clicked connect, and the wallet was like, hey, do you want to connect? Right? It knows where I connected to before, because I used the same thing. So it knows this. Right? It also knows who I send funds to. So if I send funds to andrewmohawk.eth, you're all welcome to do that. That's no problem. It will remember that. OK? And I understand there's like a spoofing thing. I put a little star there. And they also know what you usually do. So they know like, oh, after 5 p.m., you go to pump.fun and just buy every meme. So these are the problems that I have with wallets. The first one is lookalike addresses. So this is an attack where an attacker will see that you've sent money to some, or sent assets to some other account. They'll pre-generate a public key that looks similar to that. So like the first 4 and the last 4 digits are the same. And then they will make it seem like you sent money to that address. Then when you go to send money again, send assets again, you'll click on the last one. That's the malicious one. OK, you've sent all your funds away. I spoke to someone yesterday who was like, this has happened to me this week. In this list, you can see that the very bottom one is the rocket pool transaction that they did. And then all the ones above that are just malicious actors trying to get their cash. Most of the wallets, in terms of protection, will give you a pop-up that says, hey, you've never sent to this address before. OK? The odds of you finding an address with just the same first 4 and last 4 are 1 in 18 quadrillion. I promise, wallets, you can just block that. Just don't let that happen. You have all the information. And if you hit those odds, I will buy you a hat. OK? I will buy you a hat for every time you get that. Then we have similar URLs. Like, let's say you were like, ooh, I like Unichain. I went to unichain.org. The wallet knows where you're connected to. It knows what you've done. If I connect to unichain.top, it should be like, hey, this is pretty close to something you connected to before, but it's not the same. Like, maybe we shouldn't let you do dangerous actions or things that are sensitive. Right? And you can solve these problems pretty easily. This is well documented in Web 2. We have lots of stuff like the Liebenstein distance to see how close they are together. We can have a list of known good domains. We can do an SSD patch against good domains and say, like, hey, this site looks very similar to one that we usually connect to. That's worrying. We can also look at domain age. So if the domain is 1 day old, just don't let the user connect to it. It's crazy. Then we also expect people to be crypto native, which is kind of like the equivalent of when security people used to tell everyone that they need to check the headers of the email. I promise you, if anyone checks the headers of every email, I will also buy you a hat. Apparently, this is my go-to now. I'll buy hats. But if you look at that, like, no one is going to understand what is happening there. Even if you have it as text that's put out the forward, it says, get my money and a recipient address. You can guess what that does, but like, how are you possibly going to understand that? Then understanding the permit 2, and approval flows. I promise you my mom is never going to figure this out. There is like a huge page. It explains it really well. It's really nice, but there's no way my mom will figure that out. If you love your mom, I love my mom, then you wouldn't let her go on Twitter with MetaMask right now, right? You know that she's going to get wrecked. There are loads of like scams. It's super easy without that, without any training. That will be the first crypto experience that someone has, is losing all their funds. What I really want is this thing called mom mode. This has come up before, where it's a safe mode where I can say, hey, here are all the dApps that I approve that are good. I want these to be the only places that you can connect to. Okay, because if you have that, then I know, well, my mom's probably going to lose her money on shitcoins, but at least she didn't get scammed, and I won't be embarrassed. Okay, because that's my job, so that would be bad. Wallets don't warn users when things are unexpected, so if you are draining a wallet, you have to do multiple transactions, like you need to do an approval, and then you move the funds. You have to do it for each asset type. There are some intricacies there, but wallets never warn you. They're never like, hey, all your USDC just left. Do you want to do something about this? Maybe we can have like a backup plan of this. Seed phrases. These are terrible. We suck at remembering passwords. We suck at keeping things safe. This is just a combination of two things that we're bad at. For seed phrases, there are alternatives. So this is the one slide I got to put the company in, so that's great. See us support them. If you use something like Privy or some of the other embedded wallets, then you can sign in with things that you know before. Like Google, Twitter, you can use a passkey, so you can just sign in with your passkey and get it every time. You don't need to send a seed phrase across. And the other one I really like is how Uniswap handles from your mobile wallet to the extension. When you install the extension, you can scan a QR code. It will then do an OTP, and it will verify that you're on the same LAN. So you have to be at home, you know? If an attacker is in your house, like you've got other things to worry about. But at least here, like we have a good way that I didn't have to copy a seed phrase, put it somewhere, and copy it again. Okay, loads of improvements. Whoa, I'm way out of time. So WebAuthn and passkeys, it's phish-proof authentication. We've got to have this. Like we can solve phishing. There is a solution to it. Allow listing mom mode. I love this. High net worth individuals, like we see people who get drained for millions and millions of dollars. But if I'm a high net individual and I go to a site, for some reason I have millions of dollars in this scenario, that would be great. If I go to a site and it wants me to interact, then why don't you just spin up a new wallet for me? It takes no time. I will pay the $2 extra so that I know that the rest of my assets are not at risk. I don't see a lot of emergency buttons like revoke all, or I want to move all my assets, I feel unsafe about it. And then rethinking the approval flow. So UX people are incredible. They're super good at what they do. Let them do it. And then, of course, clear signing. People need to understand what they're doing. I know tons of wallets already do this, and you're the best. I love you long time. OK. Security. This is my last one. Ooh, I have 18 seconds. It'll be fine. Security folks need empathy. So I think that a lot of the time I see that real people get scammed, and people are punching down. Like, don't do this. This is really hurting the industry. People are going to, feel ashamed, feel guilty. They're not going to want to say, oh, this is what happened to me. Without that information, we can't make security better, right? This is something in a thread that was part of. Someone said, you know what's sad is I know a victim. They sold their house for a scam. And then another person said, well, you know what's more sad is that I warned the project 7 days ago. I promise you, you warning the project 7 days ago is not more sad than someone losing their house. Then also security folks should dog food. Like security advice is difficult. But if you want to give out security advice, I expect that you are doing the same things. If you say, oh, you want to put your phone, you think everyone should put their phone in lockdown mode, run your phone in lockdown mode. Not everything works. I promise you, my phone has the worst rendering of all websites you've ever seen. So understand what the difficulties are. Like, do you have a hardware wallet? Do you sign every transaction? If we're giving out suggestions, you have to be able to run this yourself. And also being able to run it yourself means that we can work on good and workable solutions, because you need to be able to use it as well. Oh, OK. Security folks should also support people. So call out good security work. If you see something that's good, be like, hey, this rocks. You're awesome. I love this. Like, we don't only need to be like, wow, these people suck. Then also share your knowledge. So people are very hesitant to share their knowledge. They know a huge amount about something, and they'll be like, oof, but if I share it, then people will steal my credit and the place that I can be in. I promise you that one blog post will not steal all your knowledge, and then you will lift up other people, and you have a chance of like expanding it. Then also you can submit a bug without getting paid $1 million. Okay, so that's the end. Let's make crypto safe enough for Andrew's mom. That would be great. Thank you.
Thank you so much, Andrew. I think we do have time for like one question. Anyone?
Why don't Cloudflare take down those domains? Oh, no, someone does have a question. I was going to ask. It's fine.
Really love your comments on asking all the developer and the DApp like enable locks. But one thing I do want to add as a comment is that based on our experience, very often people didn't pay attention to protect their locks and also didn't pay attention about what to put in the locks. So that actually are some of the vulnerability or security risks we have found before. So we really want to hear your suggestion of how people should pay more attention protecting their locks. Thank you.
Cool. I mean, I think that if you're looking at like the extension wallet side or the application side, then I think the main thing is that there's a huge push in the industry that we need to get out features fast. People need to deploy stuff as quick as they can. We don't spend enough time being like, okay, how does this work? Do we have unit tests for everything that makes sense? And I think that calling out like, hey, here are some things that cost other companies in similar positions this much money in losses, like, is why you should spend extra time. But mostly I think that it's just a time thing. Discussing with the dev team I find is really good. I'll be like, all right, you're all criminals now. Tell me how you're going to break in. They know the code better than I will ever know the code. So a lot of that stuff really helps, I think, like, normalizing that. Cool.
Thank you so much, Andrew. Thank you all for being part of this session. Thank you for our esteemed speakers, and thank you, Muli, for making my dream of becoming a moderator in DSS a reality. Happy lunch. Yeah, the Tomo from Centora. Oh. Yeah. There's a lot of us. Where I come from.
Oh, okay. So is his interview on the stage? Yeah. Okay, so 12:30. I'm gonna be really brief. Okay, so your interview's on the stage. All the interviews are.
Oh, the interviews have.
I saw
We are about to start our first after-lunch session. I hope people start flowing in, and hopefully everybody also had a coffee after lunch, because this is going to be very interesting sessions that I hope everybody going to understand. Very powerful testing technique going to be explained by Nat. It's called invariant focused code bases. So, Nat, stage is yours.
All right, hey everyone, I'm Nat. Just a little bit about me. I'm an independent security researcher. I spent 4 years at Trail of Bits. I joined as a junior, and then I did a bunch of secure code review. I did a lot of invariant testing, and I did a lot of kind of like fuzzing. Before that, I was doing blockchain development as well as teaching for blockchain. So the focus of today is primarily going to be kind of discussing the practices of secure code review. And this is kind of I think there's a lot of overlap between code review and invariant development, which I want to touch on here. So a while ago, I was talking to one of my friends about just the process of doing a secure code review, and we sort of settled on the fact that trying to figure out what developers intended to do tends to take up the most amount of time within a secure code review. And the quicker you can understand what the developer intended, the more fun the code review, and usually the more complex bugs you'll find. I think that's also similar for invariant development, because the faster you understand the code base, the better invariants you come up with, and the better or the higher quality your fuzz tests are. So I want to start off with kind of a disclaimer that this isn't going to be like 10 minutes of like, here are all the things that you need to know about unit tests, fuzzing, and like formal verification. I don't think that's effective. I think given infinite amount of time, ideally you would implement everything. There's trade-offs to everything, and the purpose of this talk is not to debate which one is better. So to start off, I've been getting a lot of questions on just what an invariant is, and at the end of the day, it's very broad, it's very high level. It's essentially just a property that needs to hold true on a code base. So again, very broad. It can be access control related. It can be how functions are expected to work and not work together. It can be data structure related. And so it's kind of hard to provide very strategic guidance on how exactly to find invariants. And so this talk is mainly going to be kind of tips and tricks on building invariant-driven code bases such that from developers and for security researchers, we have an easier time. And one last disclaimer is your invariants are never going to be 100% complete. I've been on engagements that have been very long, up to 12 weeks, and even then, the list of invariants that I came up with, or the process, still wasn't complete in any sense of the word. This talk will not be either, and I could probably go on for hours on end related to how to figure out invariants, how to find them. So this is just kind of an initial starting point. So from a developer side, I think one of the most time-consuming pieces or practices as a security researcher is looking at a code base, reading a function, and then realizing, oh, that function doesn't do at all what the function intended to do. It said one thing, and then you actually look at what the function does, and it's completely different. From a developer perspective, if you do create accurate function names, it helps invariant development in like the process to make that way easier, and especially to adequately communicate what the function is doing. The other thing is if you can adequately name your functions, then you can more easily determine what the relationship between different functions are. And then you can also have an easier time to essentially figure out how functions are related. Generally, if you have like one function that uses multiple helpers, having those at least close together visually helps a lot. This is kind of repetitive from my talk 2 days ago, but documenting everything in terms of assumptions, because any wrong assumption can result in unidentified or unexpected behavior, which is very likely going to result in a bug. From an invariant development perspective, though, this ends up being way more useful than I think people realize, because you can essentially read the documentation, and anything that is different between the documentation and the code is something to look at and something to report. The next thing is just to comment all the expected data validation of the system. Ironically, I've actually found some bugs while looking at a code base, pseudocoding the data validation that the system is currently implementing it, and then sharing it with the developer. And then they're like, oh no, that clause is missing some specific access control or some specific check. And I think it goes a long way to commenting all expected data validation, because then you can more easily determine what the function is expected to do. And then my last one is kind of the relationship between developers and security researchers. So I think there's, each party brings something slightly different to the table. Devs, I think, bring how users are expected to use the system, what is expected, kind of the functionally, how users are supposed to interact with it. Security researchers bring a different understanding of security risks, protocols, different things that maybe other protocols got wrong. And I think invariant development becomes way easier when you take advantage of the fact that developers know or should know how their system works. So that can be async, that can be through calls, but making the time to talk with developers on what is expected can also go a long way to understanding the system. I'm going to keep this kind of shorter. Helpful practices for developers. It's really easy to identify when a code base is built with invariance in mind, because it's much easier to know like when state changes. It's really easy to know how to get tests up, because you can just look at the code base and you already know it from reading it. If you do end up practicing tests or writing tests while coding, you're kind of forced to think about invariance by default when you're coding. Obviously, I think, and probably something that's been talked about for the last couple of days, is maximizing test coverage, if it works. Gives you an idea of what might be missing coverage, what might have more coverage, and give you an idea of what to focus on, and explore automated tools. The tooling is going to help security researchers, because then you can leave the tools to find all the low-hanging fruit, and leave the security researchers to find all the fun stuff, and hopefully the automated tools as well. For security researchers, I think thinking in an invariant-focused way is a lot harder than we realize, because we're not used to taking a step back from the code base. We're too used to going into the weeds and seeing how the deposit function works, how the withdrawal function works, and not necessarily the in-depth of, or the higher level view of what is expected. I found it useful to just pick a code base, try to find some invariance on it, try to bounce ideas and see whether you may not find the same invariants, and your invariants are likely are not going to be correct in the beginning. But it's a very useful practice to start thinking about invariants in this way, because you don't need to set up a fuzzer, or you don't need to set up a prover in order to test those invariants. You can start identifying them and then doing your code review with invariants in mind. And I will emphasize to just take a step back and make sure that you get a bird's eye view. All right, so that was pretty quick. I left some time for questions, so I guess we have a few minutes.
Hello.
Hey, so a lot of good stuff in that talk. One thing you said that I particularly liked is putting code, functions near each other when they're related. How would you advise developers to balance that against common coding practices that would be applied to large code bases, like, well, we put all the public functions up here, all the internal functions down here, and there can be benefits to that kind of uniformity as well. So, how would you advise people to find balance?
Yeah, honestly, it's really challenging, because I would say personally I found if the depth, if it's a relatively, there's not that many helper calls, then I find it just easier to read in the same function. But obviously if there's many different helper functions, kind of putting that into different contracts. Honestly, I would say the thing that I found that helps is just cloning the repo, and then having say a split screen in VS Code, either side by side or I guess up to 4 quadrants, and seeing how hard is it to jump between the main function and its helper functions, so that you can kind of see visually which one I guess is the clearest in terms of its links.
Okay, any more questions? We are meanwhile preparing for a panel. If no more questions for the crowd, we will thank Nat for presenting. And we're going to start a panel moderated by Rajiv about Web 2 versus Web 3. What's the difference? Is it a rebranding of an old paradigm, or there's actually something new there? So I invite Mehdi, Pablo, Peter, and Anto to get on stage, I guess. And I guess I'm to you, Rajiv. What? I have this.
All right. Good afternoon. So looks like people are trickling in after a good lunch. So hopefully we'll keep this interesting and interactive. At least definitely want to have the audience ask the panel questions. I don't think the people here need introductions. They've been giving talks, multiple talks and multiple panels. But we'll do a quick round of intros. I'll kickstart it. I'm Rajiv. I've been a security researcher my whole life, founder of Securium, one of the organizers of DSS, and really trying to get the community rolling. And this is a topic that's really close to my heart because I've been doing security for a long time. So we could have renamed this panel multiple ways, but what we really want to talk about is what are we doing with Web3 security? Right? Are we really trying to reinvent the wheel? Or as Andrew said it, we shouldn't be speed running all the things that went wrong with Web 2 in the Web 3 space. So that's really the goal for this. Let's look at sort of all the historical things, what went right, what went wrong, can we learn something, or should we really restart that? But before that, quick round of introductions by all the panelists here.
Okay, I'll start. I am Pablo Sabatella, Pablito.eth.
I'm a SEAL 911 contributor. I founded Obsec, where we do operational security audits and trainings for Web3 companies. And I have the Blockchain Security Series podcast. And well, operational security is my stuff. I enjoy hacking people more than systems. That's my stuff.
Hi, I'm Andrew. I did the talk 2 sessions ago. I previously worked at BitMEX, my crypto experience, and then Robinhood, and then Uniswap, and now I'm at Privy doing embedded wallets. I like all factors of security, and mostly my goals are just not to be embarrassed a lot of the time, not to look really dumb in front of my other security friends. So that's my motivation for doing security.
Amazing. So I'm Anto. I work as a principal security engineer at EigenLayer. Previously, in my Web2 job, I've done hardware security, mobile security, Android, that kind of thing. And I got into Coinbase, so that was my first crypto job. Did Base, and now EigenLayer. So security has always been my thing. Love breaking things and trying to fix as much as I can.
Hey everyone, Mehdi, co-founder and director of Sigma Prime. We're a blockchain security and research firm doing a whole bunch of security stuff across the entire Web3 stack. We're also the founders and maintainers of Lighthouse, Ethereum consensus client, responsible for 1/3 of the Ethereum network today. My background is also in Web2 security. I've done a bunch of pen testing, web app security assessments, and so on, red team engineering, social engineering, and whatnot. So yeah, Web2 security is a concept that's also really, really close to my heart, and keen to dive into this.
Hey everyone, I'm Peter Kaczerginski. I'm at Coinbase Units or X team. I'm also the editor of the Blockchain Threat Intelligence newsletter. I had a lot of Web2 experience in the past, anywhere from malware reversing, exploit writing, red teaming, blue teaming, just kind of keep on hopping security jobs. So Web2 is fun, but Web3 is even more fun.
Fantastic. So, I mean, as you heard, right, so we've fantastic set of panelists who've been around way further back than Web3. So that's really the motivation for this panel. But before we kick things off, right, just some fun historical facts for those of us who are new to sort of Web3 security, or even for those who've been around for Web2. A lot of these things are not new, right? Fact 1, the first message that was sent on ARPANET, right, the predecessor of the internet, the first message that was sent from UCLA, the university in Los Angeles, to Stanford, SRI, yeah, we see some hand pumping. So that crashed the machine on the other end, right? So there was actually a memory, it was a buffer overflow. It was a memory corruption. So they tried to remote log in, and the story is that, yeah, you can look up Wikipedia. They started typing LO, and before it got to G, the machine on the other end crashed. The bit rate they expected was way smaller. They had a 10-character, 10-byte memory buffer allocated, but that didn't really fit, right? So the details you can look up. So this was ARPANET, right? I mean, this is, 1969, I think. Wow. But of course, security goes way before that, right? I mean, ciphers, cryptographic ciphers have existed since the Greek and Roman and Indian civilizations. And social engineering, I mean, Pablo talked about it. I mean, that's existed as long as humans evolved, right? So this is sort of not new, while it may seem like that. Specifically when it comes to security, right? Some of you may have heard of the Salzer and Schroeder principles. So this, look it up. So this was in the US, 1975, set of, I think, 10 principles, really captures things like least privilege, common mechanism, user experience, so separation of privileges. We talk about multisigs. A lot of that has been sort of talked about, captured, formalized in a different context, right? Obviously, they didn't have ledgers back then. Now, blockchains. The reason we talk about blockchains consensus security is the Byzantine fault tolerance, Byzantine generals problem, right? Was formalized in the context of distributed systems in 1978. So things have existed in the blockchain space, in the Web2 space, in the Web1 space, so for a long time, right? But just want to sort of kick things off, sort of level set ourselves and the audience with how do you guys think about what is sort of Web3 security versus Web2 security? Do you sort of compartmentalize it, or is it one big thing? Anyone? Would like to hear all of you.
I can kick it
Yeah.
off. I guess I look at Web3 security as kind of like a subdomain of a larger security field. Like it's a domain-specific thing and domain-specific knowledge. We have very unique challenges, right? We have to think about everything is decentralized, wide open to everyone. You can't submit a secret to someone without everyone knowing about it. But it's almost like I think it's a misnomer to say that Web3 security is this special thing and it exists in isolation and we have to forget about everything else that exists. No, it's another domain. It's a lot of fun, but we also have to remember all the different lessons that we learned since, I guess, the 69, not to send messages that crash things. We still send messages that crash blockchains, and we have to learn from that as well.
Yeah, kudos to both of you in your talks for sharing with people that Web3 systems are typically deployed on Web2 systems, right? And I'm sick of seeing people get popped because of poor security hygiene that's got nothing to do with on-chain activity and solidity and the EVM. We don't have to reinvent the wheel. People have come up with great set of standards that we should all be following. I walk around in the conference and I see a lot of people leaving their workstations, their laptops, unmonitored and unlocked in a security conference. Like that's.
Wait, I have a problem with this.
Yeah.
Okay.
Hit me.
I'm a lot of controversial topics all the time, right?
Yeah.
How many attacks have ever happened from someone leaving their laptop unlocked?
Heaps.
I don't believe that there's any of the big attacks are left from someone's machine unlocked.
Well, that doesn't mean that we shouldn't prevent that from
No,
happening,
I agree,
right?
but I think that security people focus too much on that one.
No, that's one example of. So back to your original point of being aware of some of the limitations of our space. I think a lot of people think that we're amongst friends here.
Look at me when you
I
say
don't
that.
think so.
That's
I like
very
you,
boring.
Andrew. We're friends, but this is like.
Just don't leave the machines open, please.
Yeah, this is a prime conference for anyone wanting to potentially attack founders, right? Yeah. And backdoor laptops. Those laptops will potentially be deploying sensitive smart contracts, sensitive systems, and protocols in the future. So, yeah. So that's one example. One of my teammates said that he even found an unlocked phone in the bathroom today. So yeah, I think we can do better. I'm not saying that like this will automatically lead to compromises of Web3 protocols, but the bar is so low at the moment that we should all be working towards raising it. And yeah, it's a lot of people think that, oh, I've gotten 10 audits, I have a bug bounty program on Immunify, so my protocol is safe, but not really.
Yeah. I think we see a lot of smart contract attacks early on, and now we have gotten to the point where protocols are getting audits and it's difficult to exploit. Maybe not difficult, but it's a higher bar to exploit protocols. So attackers would probably want to go for the low-lying fruits, right? So Web 2, like if you do not have your Web 2 security down, you do not have to be exploited on the smart contracts. You could be exploited in the UI. So the recent attack, people saw something in the UI and they signed that, but they never verified it on their ledger devices. That is a very Web 2 attack. It has been going on like remote code executions. So we are seeing more Web 2 attacks than Web 3 attacks because hopefully we got our Solidity smart contract security right. Now attackers will go on to the next thing, which is Web 2. So
I think we've also seen that in Web 2. So previously there were like loads of server-side attacks. Like people would attack IS5 for days and days because you could just get it to drop shells all the time. And now that security has improved, like people have moved like further up the stack or closer to real people. But I don't really differentiate between the two. Like I don't really have a differentiate between Web 2 and Web 3 security. Like it's all security. It's slightly different. There are some like some differences in how it's used, but the same would be like if someone was using a completely esoteric language, or there was some other way that we deploy things. I think that the nice thing with Web3 coming in is that we finally have a chance to change some of the Web 2 things. So if you look at Web 2 companies, like everyone is very stuck in how we do security. Like there is basically a hard and fast rule, but coming into our space, like we have a chance to make a difference. So like if you wanted to be like, I'm gonna flash the machines every single day before you get to work, there is no Web 2 company that is gonna go for that. But I think that you have an option with people in the space being like, like more fresh and dynamic, like they're okay with trying new things. And that's really why I like it. I think that especially if you work in AppSec, like you have a chance to make a significant difference in what we do and like have a cool way to do it.
Yeah. I think that, well, as you have already said, there's no Web3 without Web2, and I think that we shouldn't make too much of a difference. But I think that the key thing with Web3 is that it's much profitable and cheaper for threat actors than going and, I don't know, stealing credit cards database and then doing stuff with the credit cards. So I think it's a matter of incentives, first of all. And then I think that a very big issue that we have is that, I don't know, banking industry has regulations and they tell them you have to do this, and that, and they do it. And in the crypto industry, there's no regulation. Everybody does whatever they think that they should be doing, but we have no processes, no standards, no nothing. There are some things that are being created around that now, and I think that's pretty important. But anyways, we are realizing that that's important because funds are getting stolen like in the hundreds of millions. So when that happens, we say, okay, we have to make a change here. And another thing that I think that it's very important is that lots of Web 2 attacks that are on DeFi protocols, for example, I don't know, taking over a domain or a Twitter account, affect users and not the protocol itself. And sometimes protocols then don't reimburse users or whatever. So some of them don't care too much about their users. I think that should change. And that's why they say, okay, no, our contracts are okay. If there's a phishing campaign, that's not that's not our responsibility, let's say. I think it is. But I think that it's mainly a thing of incentives. And due to that, we are paying more attention to that.
All great points. I mean, I didn't think we would disagree that Web3 or Web2 security is not important. It's a bit of an echo chamber, right? I mean, in this room and amongst ourselves. Yeah. So it's really to get the word out, right? So good. Glad we agree that this is critical. But we do see that, I mean, we do have Anto sort of representing the protocol side of things, right? And so maybe just a simple question. I mean, you did agree that Web2 security is critical as well, so that's good. But we do see that when when we say Web3 security, I think my guess, we haven't done a poll, the first word that comes to people's heads is audit, right? And that is smart contract audit. Yep. Andrew talked about it, Peter talked about it, I mean, all of you agree with that. So protocols don't have a budget, right, for whatever reasons, to get a Web2, to get an infra audit or any of the other things. Why is that, and what needs to change to make that happen? I mean, protocols pay $1 million, I mean, depending on how big your TVL is, right? Couple of tens of thousands, hundreds of thousands goes up. What do you think? Maybe Anto, you can sort of give the protocol perspective and we can all chime in. What is that mindset and what can we do to change that mindset? Oh, did I say Andrew? I mean,
I can do this from the time. So
we let Anto sort of take the spotlight.
First victim. Okay. Yeah. So protocols do spend a lot of money on audits. We get like the audits from the top security firms, and we do not have unlimited budget, unfortunately, right? I would like to get audits from all the security vendors that I've met here. I think you're all amazing, but we have limited money to spend on these audits. So we have to, unfortunately, pick a criteria and go with who's the right audit firm for the specific audit that we are doing. So if we do anything with beacon chain, which we do, we would like someone who has experience with like a light client or like a consensus client, because they really do write that code, right? So we definitely pick our auditors based on what is it that is being audited. But security doesn't stop there. There is a lot more you can do. Like we do get infra audits. We do get Web 2 audits. I'm an AppSec guy who became a crypto guy, so I understand how important it is. But there are stacks that you do not control. Like for example, you have a X account, right? Like a Twitter account, right? You can do everything right, but you do not control that platform. It's not a blockchain. You have a username and password in a database.
Yeah.
You probably know what can go wrong with something like that.
Right.
And that does go wrong a lot,
right,
especially in crypto because the incentives are so high. But what can you do as a protocol to prevent that? Unfortunately, not a lot. You can follow all the best practices, and I'm sure like we all have contributed to all the best practices doc here. Right. But there is no guarantees that even if you follow all the best practices, you won't be popped.
I see Peter has.
I just wanted to point out, like I'm sitting here and watching you talk about the audits and how we have to invest, hundreds of thousands of dollars and millions of dollars. Can we just recognize just how much time we spend as protocols thinking about security? What do you think is going on in the Web 2 world? How much do you think a typical Web 2 company spends on their security budget? And how much time do they think they worry about this cool mobile app they're about to dump on everyone that's going to collect everyone's credit card numbers and passwords and social security numbers? How much money do you think they spend on whatever security audits? I just want to point out just how far ahead we are and just how much more paranoid we are as a Web3 industry, as a DeFi industry, just worrying about those things. That said, we have no choice but to worry about those things because once the money's gone, it's gone. And one thought that I had is we still have to worry about audits. We still have to invest in that. And if you saw my talk, I'm all about like, oh, you have to build your security programs. Just teach your entire team to be a security team. Every single member of your team has some kind of security role. Like, I don't care if you're a marketing person. Well, now you're responsible for social media security, and you're supposed to hunt down the phishing scams. If you're a dev, obviously worry about smart contract code. But if you're an infra person, freak out about your cloud infrastructure. So dividing up responsibilities may be able to alleviate like some of the fear and just all the load that we have as a DeFi industry and a typical DeFi project, which has like 5 people on it.
Great points. So I'm sure we can talk about so many topics that you guys have talked about, right? Private key management, all the things from the Web 2 space and the Web 3 space, right? But just sort of to start dialing up the heat a bit, right?
Here we go.
So anyone, should we move slow, break nothing? Or should we move fast, break something? Or in other words, should we treat Web3 security like hardware security? I know there's a school of thought here that believes that. We had talks from Aave as well on that. Or should it really be along the lines of Web 2 software security, right? Where move fast or you break, update, upgrade, life goes on.
Okay.
Who wants to take that?
Maybe
there are a whole bunch of
Yeah. So there is the need for security versus the need for product market fit, right? Right. Like we can move really slow, but your competitor might just go all out, and there is always that first mover advantage, which is a very real thing, and so you cannot just sit back, chill. Even if you look at hardware security, sure, they go slow, and they still have bugs. Yeah. Like how many microcode updates have you applied to your Intel processor? Very slow process, right? Even Apple M1 chips, they have bugs that can never be fixed. So moving slow doesn't mean you don't have bugs. You still have bugs. I think you should design your protocol to localize your failures. So the whole thing doesn't blow up, but like localized failures. So you can move fast, still have localized failures, which is, I believe, more of a practical approach than, of course, you should do your audits and all that. Don't be irresponsible with that. But you have to also understand that you have to ship. Yeah.
Cool.
Can I ask a question just following this?
Please.
How about capping deployments? That's something that I've seen some of our clients do when they don't have the time to perform all the due diligence that they want to perform before going live. They could potentially cap user deposits at, like, let's just say a few $100s worth of assets. Would that be a good strategy in your opinion?
Yeah, localized failures, right? That is exactly like capping deployments.
Guarded launch, few tokens, have a certain TPL.
Exactly.
Incremental stuff.
Yeah.
I think there's like when we're talking about like fast or slow, a lot of people see like security as a blocker for deploying things. And I think that as like security practitioners, everyone needs to realize, like, one, you will never be a good engineer. Like, I can make any engineer a good security person, but going the other way is very difficult. And then also, you know, normal devs are paid on like the features that they release, things that they get. They're not paid on how secure their code is or how well they did in an audit. So every time that you stop them and be like, hey, you need to do all these things and make it slower, like, you're literally taking from them. So you need to have a lot of empathy, I think, to be like, okay, we can find like a middle ground. I think that like empowering the development team, you know, is a good idea. And the base metric is like people will reach out to security. I think that's how you know like your security is making a difference.
Cool. All right. So I have a few of these. Yeah.
Just one more thing. You can also do other things, right? Like you can still move fast as long as you think of like compensating controls. So for example, you deploy your contract really, really fast and you're scared that you may get hacked. But if you build some kind of functionality that can allow you to respond to incidents either automatically or at least fast enough, you can kind of mitigate or control how many funds you're going to lose in case of a hack. So if you have a system that can just pause the protocol right away, just the second you see the funds start moving or one of your vaults is getting compromised, you can kind of speed up the process maybe a little bit. If you have like a faster incident response program built in, you can kind of speed things up a little bit. So it's a game, it's a balancing game that you're always playing. Like how much do I invest before the deploy versus like how many controls I can build after deploy. And that can allow you to maybe take slightly more risk than you normally would.
Yeah. Absolutely. I mean, so that's a great segue to the next question. Right?
I want to come back to, because I forgot to add something to your question before regarding budget. And what I have found, because I offer these operational security trainings and audits, is that it's not a matter of budget, but something that I see is, you know, this concept of security by obscurity. Many companies have a very shitty OPSEC, but even with that, they say, no, we don't want you to audit our computers or our phones. Or for example, devs hate to be told to have to install something in their computer or to be told that you have to do this in this way, in this way. They don't want to be told. It's very difficult to convince them to do it. In the end, we can do it most of the time, but it's very difficult. And then the other thing of, no, I don't want you to know how we have our setup, right? And the reality is that you can get to know how they do it anyways without them telling you, but they have this idea that we have known for years that doesn't work, of security by obscurity. No, I won't tell you what software we use, which are our wallets, if I have Windows or Mac or Android or Ledger or Trezor, or how I have configured my Twitter, if I have a YubiKey or a Titan. And they think that doing that is far more secure. Like, no, we don't want you to know anything. If you audit us, you will know our setup and you will be able to hack us.
Right. So this is literally sort of speed running the Web 2 thing, right? Oh, we don't want to reveal anything, right? You may attack us, the whole, So this is a great segue. So there's a lot of attack surface to cover, right? I mean, Web 2, Web 3, you know, add them up, Web 5, I don't know. But obviously we are constrained, right? Time bound, budget bound, awareness bound, all those things. So if you were to pick, I mean, the question is, what's the weakest link in Web3 security today? You think it's software? Sorry?
It's phishing.
Humans.
Phishing, okay.
Yeah.
So software, hardware, you're working with wallets, right? Or is it really people, wetware?
So I think that
just maybe we
I
can
want
go
Pablo
around.
to answer that.
Huh? Yeah.
You literally had to talk about that.
Yeah.
I think the number one is social engineering mixed with phishing and with malware. That's number one, I think.
So people.
Yeah, people.
Yeah, Andrew.
I mean, I definitely think it's people as well. I think that it's you know, things like, oh, people were like, oh, we'll do phishing training, but the data says that phishing training doesn't work. Spend that money on buying YubiKeys, you solve this problem. Like, it is a solvable problem that we somehow have still, which is very frustrating.
Yeah, I love that because things like passkeys is actually better than phishing training.
Yep.
You know, like a decent solution.
Yeah.
And I think we need to do that for wallets too. How many people understand what is a private key? Like you know, it's a very niche thing to understand.
Or should they even need to understand?
Exactly,
right?
exactly.
It's
right?
even
Like,
in the name, private key.
Yeah.
Private. They should be private.
yeah.
Right?
But
oh, yeah.
Yeah, you know, people write their passwords on a sticky note and they put it on their computer, right? Yeah, so this is like difficult for them to write down the full private key. You know what I mean? They shouldn't be doing that. Like, we can name them whatever, but just having a user custody a private key, do that whole ledger thing, is probably not the way we'll get mass adoption. We probably need something familiar UX, like account abstraction, right? And then with things like passkeys, maybe the phishing will go away. Web2 has been trying to solve phishing forever. And ever since they invented browsers, we've been trying to solve it. And it's been like, what, 30 years or something now?
Yeah. It just seems like it's much worse in Web3 somehow.
Yeah, because there is money involved, right? Yeah. So.
Yeah, no, I can't disagree. I think humans are always going to be the weakest link of the chain, as Pablo pointed out. But I also strongly agree with Andrew. I think it also highlights failures of the security industry. I think we should all thrive and aim to provide tools that are inherently safe for users to actually interact with. And we've done the shittiest job at that, I think, as an industry over the past 10 years that we've been doing this stuff. Yeah, your talk, Andrew, is just, I was just watching you and be like, amen, please, everyone, hear this. Yeah, but I think humans are always going to be the weakest link. I like a quote from Morelian from Optimism, who said, you should design your processes so that even if you hired 49% of DPKR agents, you're still, resilient to actual attacks. Because, I don't know if you have plans to talk about this particular topic, but it's certainly a thing, right? Like we're all being actively targeted by that particular threat agent, and yeah, you will most likely hire one of them. Within the long run, you'll fall for that. So it's about tweaking your processes so that even if you do hire some of those malicious actors, you are not effectively going to get popped to the extent where your users are going to lose their life savings.
So we need an honest majority, right? BFT at the dev level really is what
I guess. Yeah, it's a complicated topic, but I think Optimism for once, they've set up some set of guidelines that are perhaps worth sharing and following.
And one thing to add with that is that apart from saying, okay, I have a North Korean guy working at my company, I don't know it, I think that we should always know, even with companies that have more than 30 people, that any normal dev can, I am convinced of that, many people don't, any day can turn evil, as Peter was saying in his talk the other day. We say, no, but we know these guys, we screen and we talked with them. You never know. Yeah. You never know.
People are people.
And that can happen.
Totally.
So
it's the same as people who have an issue with, they're like, oh, SIM swapping. The people who are doing the SIM swapping are terrible. So that person earns zero money compared to you, and someone was like, here's your entire year's salary, all you need to do is click a button, they're going to do it.
Yep.
Like, it would be insane for them not to make that choice. And I think that that's what you need a budget for. Like
spicy take.
Yeah.
Wait, that was.
All right.
I have spicy takes. That wasn't it.
That's good. That's good. The food was spicy. I think the panel should be spicy.
Exactly.
Yeah. It's not too spicy. We all know. The human factor is always there.
Yeah.
So we're running out of time, but I think we've talked about the past and sort of touched the present. We can go on, but want to sort of talk about the future as well, right? So if I can request you guys to bring out sort of your crystal balls and look into at least next year. You know, Peter does the state of DeFi every year. So how do you guys think Web3 security will be when we, let's say, reconvene for DSS 2025? Will we still have the same, you know, 6 guys talking about the same things from 20 years ago, people, software, hardware, you know, or is it a sort of a more optimistic future? I mean, 1 year is a long time in the crypto industry, right?
I think the future is optimistic. We'll still be talking about,
really?
I hope we're still talking about
no.
the human factor is always going to be there. We'll still be talking about this. But there's so much interesting tech that is coming out, which is unique to our industry, where we can do so many more things that we just cannot do in Web 2. For example, I'm watching, every time there's a hack, I immediately see MEV bots just swarm the attacker. You know, the attacker drained 1 volt, and then you have these automated MEV bots basically like draining everything, and then saying, like, it's all happening on chain. They're saying, oops, sorry, we hacked your project by accident. Here's your money back. I imagine 5, I don't know how many years from now, probably a lot sooner, we're going to have a degree of incident response automation, which is simply not possible in the Web 2 world, because everything exposed, everyone can see all the transactions, mempools. I'm not sure where you're going to stick that automation. It could be just in public or private mempools, sequencers, bridges, whatever. There's such an amazing opportunity to build something that will hack back the attackers even before they have a chance to execute their attack. I'm actually seeing those bots come in and steal the money from the attackers before they even have a chance to do what they need to do. And that happens on more than 1 occasions. So that's showing me the future that we can do even better than Web 2 world. On the user side, there are also opportunities. Look, we have wallets where we did not have any user protections just a year ago. We did not have any monitoring just a couple years ago. Look how far we moved forward as the industry. So it's hard not to be optimistic when you see transaction simulations coming in. We're still lost $460 million or something like that. So those transaction simulations, obviously not simulating everything they should be, but this is year 1. So I hope that in 5 years we get smarter. Our approaches to user security will also get just as good. So we'll be able to catch more stuff. So things are dark, but they got a lot brighter this year. And I think as we go year after year, we'll focus on maybe problems we can't even anticipate today.
I think, as I always say, that it's a matter of incentives. And there are 2 things that we are doing very good that are changing the incentives for third actors. First thing is creating standards and procedures. For example, the frameworks that is created by Mata, like having a guide on these are the things that you have to do. Well, Mata and a couple more from SEAL. And so no, yeah, it's there, and if you want to do it, it's there, and we know it works. So that's for a thing. So we will make it more expensive for a third actor to attack someone. And the other thing that I think it's very important is that now third actors are being followed, right? We have the people like Taylor Monahan or SackXPT or many that are following the money, freezing the money, making it more difficult for them. So I think that will help a lot. Those both things will make it far less profitable, and that will help.
Yeah. One thing I also see is sequencer level commitments. So if you are an app like Uniswap, right, you have an invariant. You do a lot of invariant testing before you deploy. But maybe you haven't thought of like a specific edge case, right? So what if you can enforce invariants at the sequencer level, right? So in Web 2, we have firewalls. Why can't we have like Web 3 firewalls, which aren't like censoring, but enforce these commitments? And we can have decentralized sequencing. And this would give us even better guarantees in production. And if we are to get all the consumers on board, I think we need that level of assurance. And I think we'll see a lot of that, at least on L2s and L3s. L1 is tough, but it can be done. Yeah.
I think we're running out of time, so.
Okay, I think it'll be just as bad next year.
All right.
I think that there's going to be a lot more abstraction in terms of users' accounts, in terms of the chains. Everyone, well, a lot of the L2s are using the op stack, and I think that as we abstract further, the lower levels can focus more on security, and hopefully it will bridge up. But I don't think in 1 year we will have any difference to what we have today.
All right, we don't have the same panel next year then. Cool. So I think we're out of time. I don't know if you have time for maybe one quick question, but all the panelists are going to be around for the rest of the day, hopefully. We have a question from Mata. Oh.
So the Microsoft DSCA framework was deprecated in December 22, but it left in place a lot of really good guidance around guardrails for hierarchical administration of systems. Have you seen similar guardrails put in place for human and non-human identities between identity providers and security systems in the tier 0 space flowing downwards? Don't all answer at once.
I haven't yet.
Yeah.
No, I'm saying no.
I don't think so.
No, I don't think so.
Everyone is very focused on their code audits and smart contract audits. This stuff is way beyond. We should be thinking about that. We should get there, but maybe we should distribute that the Microsoft article and report to everyone.
All right. Thank you, gentlemen. I think that's all the time we have. So.
So I'm inviting Luis from Halborn on the stage to present on the topic of breaking the Rust-based blockchains. So Luis. All right, Louis, stage is yours.
Okay. Hello, guys. After flying over 32 hours, being squeezed in a tiny airplane seat, it's a pleasure for me to being able to stand up in front of you and talk about a topic that I really enjoy, after wine, of course, that is Web3 security. So let me introduce myself. My name is Luis Quispe Gonzalez. I work at Halborn, a company specialized in Web3 security. I have been hacking for around 13 years, different technologies, web, mobile, ATM, Swift, you name it. And the last 4 of them focusing on Web3 security. So right now I'm working with DeFi projects, cryptography, layer 1, layer 2, a solution, etc. Off the record, I'm a wine lover, so if you enjoy this talk, you can invite me a glass of wine or a bottle, you decide. So today we are going to see 2 things mainly. The first one is how a Rust-based blockchain works. And the second one is some very interesting vulnerabilities my team and me have found over this time. Okay, before starting this intro, would like to know how many of you are Web3 security researchers or are dedicated to security? Please raise your hand. Oh, a lot. So, and from you, how many of you have audited before a blockchain? Oh, a lot of experts in the room, cool. So what happens? Most of the Web3 security auditors are used to audit smart contracts, most of the time. But what happens when appears a blockchain? And many words comes to our mind: validator, full node, consensus, execution, VM. So how to hack this kind of technology? Every time something new comes to my home, so I remember this anonymous philosopher on Twitter. If I'm building a house, I would spend half of the time looking at YouTube videos. And to be honest, sadly, there are not YouTube videos on how to hack a blockchain. Maybe soon. So first, we are going to understand how a blockchain works through a transaction lifecycle. You know that in security, we most of the time use very common names like Alice and Bob, right? But we are going to change that. This is old school. Let me introduce you Ayesa. Actually, Ayesa is a real person. She's here among us. If you find her, say hello to her. She doesn't buy anymore. Okay, so Ayesa loves money, and she's a very smart investor. So she decided to add his coin to pool liquidity. So what she thinks is that after some time passes, she will be able to claim some reward. And the time passes, and she tries to claim the reward. What happened behind scenes? So first, we have Ayesa with his client, in this case, a wallet, and the wallet tries to build a transaction. Let's name it transaction 14. Why 14? Because before that transaction, she executed 13 transactions successfully. So if we take a closer look to transaction 14, we are going to see a raw data, we are going to see a public key, and a signature. Obviously, the signature is so nobody can impersonate her. If we take a closer look at the raw data, we are going to see different fields like Ayesa's address, we're going to see the payload, so basically what she wants to try to carry out. We're going to see some gas-related data, etc. And now, the client, I mean the wallet, send a transaction to a full node. Here comes a new actor, full node. So to understand, full node, it's the typical name it received from different blockchains. In some specific one, like Casper, for example, the name is non-validator node, and so on. But what a full node does, basically this full node needs to have a copy of the blockchain inside it. Could be a full copy or could be a prune version of the blockchain. And number two, any one of us can run a full node. We just need a computer and we can have a copy of the blockchain there. Then we also have a component called mempool. So mempool basically is a temporary storage. Could be in memory, could be on disk, but the idea is that in this mempool, all the unconfirmed transactions wait until they are confirmed in a later phase. Something to say here is before a transaction is added to the mempool, there are some basic checks that need to be met. For example, syntax, for example, balance, fee check, etc. Okay, we have so a full node with a mempool. Now, you have to know that a full node also works as a relayer, and it sends information to a validator. Very interesting here, a validator also has its own copy of the blockchain. And as the name suggests, validators validates and add blocks to the blockchain. Important to know that not everyone can be a validator. You need to invest a lot of coins, you need to stake that coins, and if you do things correctly, you're going to earn some rewards, but if you don't do it, your stake coins are going to be slashed. Obviously, validator has its own mempool. So again, full node sends a transaction to the validator, validator adds the transaction to its own mempool. Now, what happens? This architecture is very common in many of the blockchain, but some blockchain, for example, Aptos, have a different schema. Full node doesn't communicate directly to the validator, but sends the transaction to a validator full node, and this validator full node sends a transaction to the validator at the end. So it varies a little, but at the end, the information comes from full node to validator. So what else? Here, important to understand. One of the validators received the transaction, but not all of them. So using a sharing mempool protocol, validator 1, the one who received the transaction, send the transaction and exchange the transaction with other validators. So at the end, transaction 14, remember transaction 14, is in the mempool of all the validators participating in this blockchain. Now, time for a new component called consensus. So consensus, every blockchain has its own version of consensus. For example, Aptos has Aptos BFT and so on. What happens with consensus? In every round, the validators need to decide who's going to be the leader in that round. So they agree in which one of them is going to be the leader, and the leader will be selected with different criteria depending on the consensus mechanism that it applies. Something interesting, the leader is going to change every round. Again, will depend on the consensus mechanism. So now let's imagine that the leader is validator X. So validator X is going to take the transactions that are in its own mempool and will coordinate with other validators to understand what is the order of the transactions in a block. And this point is very important. Why? Because at the end, order matters. It's like attending a conference. It's not the same that you, in a typical scenario, you buy the ticket and then you attend the conference. Vice versa doesn't work. You cannot attend a conference and then after saying goodbye, paying the ticket. So it's the same for the transactions. Now, after consensus component, each one of the validators, remember that at this point, each one of the validators have some transactions and they will try to execute those transactions. So let's see at validator X, the information goes from consensus to execution layer. And this layer execution is gonna make a transaction ordering. But wait, Luis, didn't you say that consensus also ordered the transaction? Why execution is ordering again? Good question, Luis. What happens is that execution layer is going to respect consensus order. However, we'll try to apply some optimization. For example, if two transactions are going to affect different resources, they can, for example, execute in parallel. Also important to mention that execution layer is going to be the orchestrator. Who is going to be the slave is going to be the virtual machine layer. Virtual machine layer is going to actually execute the code. I mean, run the bytecode from the smart contracts. Also, it's going to apply some rules, for example, ownership. And also, and very important, this part is very important, it will update the blockchain in a simulate way. At this point, no blockchain has been updated. It's a simulation. Remember that word, simulation. Obviously, depending on the blockchain, we will have different virtual machine layer. For example, Aptos use Move VM, Casper use WebAssembly VM, and so on. Now, virtual machine will give the results to the execution. An execution will append transactions in a Merkle tree. We have seen a lot of time, we have heard about different times about Merkle tree. How it works? Well, each one of the blockchain have its own version of Merkle tree, but let's see a simple example. So imagine that this transaction A until transaction E, are the successful transaction of this block. So we are going to have a hash for each one of the transactions. We are going to take every pair of hash, we are going to concatenate them, and we are going to create new hashes, and so on, until we reach the last that is called Merkle root. This Merkle root is going to be added to the header of the block. This is in general a Merkle tree. Now, After generating the Merkle tree for the block header, you can wonder why do you need that, that hash. It's a way to find very easy if a transaction was present in a block or not. But after that, here very important, the validator is going to generate a new hash called root hash. You remember that some moments ago I mentioned a simulation, a draft blockchain? Okay, that draft blockchain, this execution layer are going to generate a root hash or hashes. And it will depend, because if we talk, for example, about Aptos, Aptos will generate only one root hash. On the other hand, for example, Casper will generate one root hash for each shard. Shard basically is a slide of a blockchain. Sui also will generate root hashes for each resource that is affected. So at the end, once the execution layer generates those root hashes, send information, and it's going to be using different Merkle tree, and it's going to send that information to consensus layer. And consensus layer are going to talk with other consensus in other validators to understand if after each validator have executed its own transaction, they reach to the same root hashes, root hash or root hashes. If that's the case, consensus sends a signal to execution layer, and execution updates the blockchain state. Some moments ago, we are talking about a draft, a simulation, and now we are talking about a real modification of the blockchain state. And finally, it's going to be stored permanently in the storage layer. That's how it works. Now, that's everything that happens behind scenes. And finally, you can see that Ayesa, now he has 25 coins after claiming her reward, and those coins are reduced from the contract. Very easy. That's the happy part. Now, let's see from security perspective. What happens? Ayesa can be malicious. Her client can be malicious. The full node, remember, any one of us can run a full node, can also be malicious. Also, some validators can be malicious. So the last frontier to protect the security of a blockchain relies on protecting the security of the different components of a validator. So let's see. So I'm going to show you some real-world vulnerabilities we have found. The first one of them, by the way, a caution of war. All these vulnerabilities have been found in real-life projects. All of them have already been patched, so they don't apply anymore, just in case you want to know. The first one is related to the project called Sui, and the component affected is the execution layer, and how we found it? Through manual review. So talking about this, you know that every time you send a transaction, you have to pay a fee. Could be a fee for computation, could be a fee for storage, and so on. So what happened? And most of the time in this kind of blockchain, consensus validators reach to a consensus about what is going to be the fee for storage and for computation. So in theory, nobody other than the validators can change those parameters. Actually, if we see the code, we see that we have different kinds of transactions, and one of them is called change epoch, and it's a system transaction. So nobody else, any external party, is supposed to call this transaction. And if we see the function on how to verify the transaction, we are going to see that the verify function calls another one called addSender blah, blah, blah function. If we take a closer look to that function, we are going to see that here we have a verification. If the transaction has already been verified, just continue. Don't do anything. No, makes sense. But if the transaction is a system transaction, also don't do anything. Just continue. So if we take a closer look about is system transaction function that you see here, we are going to see that this function verifies. This transaction is change epoch, yes or no? If it's yes, don't do anything. So apparently, we cannot bypass that, or can we? So if we see the definition of the transaction, we are going to see that there are two kinds of transactions. One of them is a single transaction, a classical transaction, and the other one is a batch transaction. So basically, in a batch transaction, we create a vector of single transaction, and we can send it. So how to attack it? Very easy. We create a single transaction, and we put that transaction inside a vector, and we create a batch transaction with only one transaction with change epoch. And we apply it, and as a result, we are going to successfully execute that transaction to change the epoch. Very easy. We can, for example, put a 0 fee for storage and 0 fee for computation. So free transaction for everyone. The second attack applies to a Rust-based rollup, and this is regarding the gas fees. So what happened? In this case, we have the affected component is mempool, and also we have found this vulnerability through manual review. So if we see here in the submit transaction, this function adds a transaction to a mempool. But before adding to a mempool, do some verification. So for example, it verifies if the sequence numbers, the number I mentioned some moments ago, transaction 14, remember, that's the sequence number. If the sequence number is less than the current sequence number, so through an error message. In this case, the error message is sequence number to all. Why does it happen? Because mempool is the first frontier. We don't want to use resources from the validator unless we have validated something else in the mempool. However, in this validation, we don't see anything about higher number sequences. So if, for example, right now, the sequence number is 10, what happens if I create a transaction with a sequence number 11, 12, 100, 1000? At some point, it makes sense that the sequence number is higher than the current one, but not too much. So what is going to happen? Let's see. Here we have a test when we have two kinds of transactions that are invalid. The first one, I'm going to try to transfer more coins from Alice to someone else. Because we are trying to transfer more coins than she has, the transaction is going to fail. And as expected, even if a transaction fails, it's gonna cost you some fees, right? That's the expected behavior. In the second scenario, we are going to send 1,000 transactions using a high sequence number. Is it going to cost to the attacker any fee or not? So in the first scenario, you can see that the initial balance is 100,000 after sending only one transaction. When Alice doesn't have enough balance, some fees will be reduced from the total balance. This is test number one. However, in the test number two, you will see that even sending 1,000 transactions, our balance is going to keep the same. So no fees is expended. So why this is bad for a validator? Because remember, after adding to the mempool, it's going to send at some point to the execution layer. And every time a validator uses its own resources to compute something or to storage something, it costs money. So if you're able to send transactions and it doesn't cost you anything, attackers can start spamming with transactions to the validator. At the end, it could create a denial of service situation. And the last one, inadequate deserialization, it again affects SUI to the mempool component. It was found through fuzzing. So very quickly, what is SERD? SERD is a library for serialization, deserialization in Rust. It's very popular. We have more than 800,000 people using it. OK, this is the structure of a transaction. Here we have the data, the raw data, and the signature. And look at this. This is the happy path. Client have this structure of a transaction, and validator, well, it sends to the validator, and validator has the same structure of the transaction. So everything happens correctly. I'm going to pass this. You see that in this tab, we have the validator. I'm going to run the validator here, and you will see that it continues working. This is the validator. And in the other tab, we have the client. We are going to send this transaction, and it's a published transaction. It's like deploying a contract. It's going to work without any problem. OK, finish correctly, generates a certificate. And if we go back to the validator, everything works as expected. Continues working. So happy path. Doesn't happen. Nothing happened. Second scenario, errors that can be handled. So client now, instead of sending an structure with the expected fields, we are going to add one more field. We are going to put any name, for example, other stuff. with value equals to false. We are going to send that through tonic to the validator. And remember, the validator doesn't expect the other stuff field. So what is going to happen? Let's see. We're gonna run again the validator. This is a validator, and on the other tab we have the client. So we send it, and appears an error message. This error message is in the client, but if we go back to the validator continues working as expected. Okay, if we see the error message, we're going to see that we try to debug that, and we're going to see this. I think doesn't look big enough, but this is macros. And you know that debugging macros is a nightmare. But we have some tools like cargo expand, and at the end, after debugging, we are able to see that the error was raised because the number of the transaction was not found. So we have only 5 different kind of transactions. Okay, it's okay. The validator found it. Finally, we have the same scenario, but instead of putting true, false, we put true. What is going to happen? Let's see. I'm going to go faster. We are going to generate, we're going to make it, the validator work again. We're going to send it from the client, we're going to deploy the same contract and generates an error message. But if we see the validator stopped working. So we DOS the validator with only 1 transaction. How many validators are in a blockchain? 20, 100. With 100 transactions, we are able to DOS an entire blockchain, and nothing works. Finally, I'm going to go to the last slide. Some tips. If you can use this mental model of blockchain, it's going to be very useful for this kind of blockchain or others. The best combination is doing manual review, do some fuzzing, and formal verification if it applies. Consider the security of third-party libraries, like in this case, like CERD, and please deep a lot in how Rust works. I'm talking about concurrency, I'm talking about macros, I'm talking about FFI, etc. And finally, remember that Rust some particular macros to panic the program. So be careful with those. And that's it. Thanks a lot.
Thank you, Louis. Yeah. Unfortunately, we don't have time for questions, but going into what you just mentioned, the best combination is a formal verification. I'm inviting Denisa from Intmax. From Intmax. It's going to tell us how they verify Intmax 2. Okay.
Yeah, hello, can you hear me? Thanks. Hi, so I'm Denisa. Is this working? Okay. Yeah, let me present myself a bit. So I am with Nethermind, not with Intmax, but we work with Intmax. So I'm a consensus researcher at Nethermind. I'm also an associate professor at the University of Bucharest, where I teach formal verification and functional programming. And that's my corner if you want to check it out. So yeah. Well, okay. So today, as I said, I'm gonna speak about Intmax 2 and what we did at Nethermind with the wonderful team behind Intmax, which is actually we formally verified their white paper. But so I will touch a bit on the formalization, which is we are wrapping it up. But I would like to focus more on trying to sell you Intmax and show you what a cool solution it is. And the protocol is extremely beautiful, and their white paper is just beautiful piece of mathematics, so I invite you all to look at it. So now if you, should I be closer to it? Yeah, okay. So now, what is Inmax? What can it do? It's I think probably if you try to put it in a box, you can think of it as a based Validium rollup, but it is a scaling solution for Ethereum, and let's leave it as is, which has amazing performance. So they are claiming 5 bytes on chain, and I will try to convince you of this. The beauty part from a consensus researcher, and I will be without job probably, is that it is stateless and permissionless, so that we don't need an underlying consensus protocol. It just has to rely on the consensus protocol on DL1. I will not touch today much on the privacy using ZK proof, so I will just show the easy flow, the simplest version of the protocol, and I will just show at the end that you can use ZK proofs. Now, it is by nature censorship resistant, and it is among the fewest protocols I've seen that by design it is censorship resistant, and I will try to prove this. For the moment, they say with the current block size on Ethereum, they have a limit of 7,500 transactions per second, but there is a very nice twist here, because actually a transaction is just a batch of transactions in which a single sender can send as many transactions or tokens to a lot of other participants, right? So I will try to convince you of all these points and why they are valid. Now, at Nethermind, we have a very strong team on formal verification, and you have Julian there, who is the head of formal verification. So for all the technical questions, you can go to Julian. So we are, as I said, we are formally verifying their white paper, and we are doing this in Lean 4. So the code actually mimics and mirrors the white paper, and here you can have, for example, when we show that the balance is, like we will manage to compute that, is monotonic in the first argument. The formalization will be open source, and we are wrapping it up, so it will be available soon. And the white paper will contain references to the formalization. And for the moment, we have around 3.3K of lines of Lean. But now, let's dive a bit into the protocol and see which are the key insights that lead to this nice scaling solution, right? So first of all, if you look at payments, it's true you don't need underlying consensus, and it's necessary to make available on DL1 only a commitment to a set of transactions and to the set of senders who have signed the commitment. And the nice part is that they delegate the DA aspect of the protocol on the user side. So it will be the responsibility of the users to compute the balance of their accounts, to compute to keep track of how much money they spend, how much money they received. Now, the only part in which you have to check that everything is sound is like when you have to do a withdrawal, and you have to compute that from scratch, and I will try to show you how you do this. Okay, I think I will just be more efficient and stay here. Okay, so Inmax is, as I said, it's a permissionless block building that can be performed in parallel, and it matters only the order in which they will be, the blocks, they will be stored in, on the L1 contract. But know that here, a block is not in the sense of a traditional blockchain, because it doesn't really have to refer to the previous block and so on. It's just a storage on the L1. Now, the block builders, and this is important to understand, is that they don't need to verify the validity of the transaction. So it's stateless. And you don't need to coordinate the builders. You don't need to pick a leader for building a block. So now users, they have 3 actions. They can deposit, they can transfer, and they can withdraw. It's a payment solution. Now, for deposits, an L1 user will just send funds to an L2 address on the rollup contract on the underlying L1, which is going to be Ethereum. And that's stored in the contract storage. Now, the transfer is the interesting piece of the design, and it has two phases. So first of all, senders, they have to pick an aggregator. Anyone can be an aggregator. There can be several aggregators. You can, and probably they're gonna use relayers in order to make sure that you don't have a malicious aggregator that can postpone posting your transactions and so on. So let's say we pick an aggregator that we trust, and the senders will start to send a bunch of transactions, meaning that is just a function. Everything is a function. They send, they announce to how many participants, how many tokens they want to send. They send this information to the aggregator. The aggregator creates a Merkle tree, sends the proof of inclusion to the user, to the sender. The sender checks it. Classically, it signs, send it back. The aggregator collects a bunch of valid signatures, aggregate them, and post this information on the L1, right? Now, the other part that is missing is the fact that, so this is just me explaining that you have to have a transaction batch. Now, the other part, the phase 2 of the transfer protocol, is that the senders have to send to each recipient a proof that they actually sent the transaction, right? So each sender will send the Merkle proof that they receive from the aggregator to the recipient that they have in mind, plus with previously proofs that he had at that point. And that's done directly, not via the L1 contract, nothing, right? Now, the withdrawals are quite simple, but there is a twist to it, because in order to withdraw, you have to, even if I want to withdraw my own funds from the rollup, I have to engage first in the transfer protocol, in which I will send the transaction, the amount I want to withdraw. I will send it to an L1 account, and that will be posted on a transfer block. And then I can use the proof that I built and give it to and send it from an L1 account using this proof that I have, send it to the rollup contract, and you do the withdrawal. So as I said, when you transfer the block, the L1 contract doesn't automatically send the funds to the L1. You have to go through the transfer protocol before, and after that you can do it. You can trigger. But in order to trigger the withdrawal, you have to go through the transfer protocol. Now, what we are formally verifying is their security, well, the safety property, saying that the rollup contract is secure if every withdrawal is fulfilled, it succeeds. So, and we show that, okay, you have to have a trust assumption at the point. So breaking the security result is like either you collapse the hash function or you break the binding property of the underlying authenticated dictionary. Now let's look at the protocol, right? Everyone can be an aggregator. You can be your own aggregator. It may be a bit more expensive for you, but you can do it. So you don't need escape hedges for this protocol. By design, you have it. So everyone can be an aggregator. Therefore, you have censorship resistant, modulo the censorship resistant on the underlying L1. Now, the rollup contract, as I was trying to show in the pictures, manages deposits, transfers, and withdrawals, right? And for each type of the user action, you have 3 different kinds. We call them blocks, but as I said, they don't have to rely to address the previous block and so on. So the rollup state is just a list of 3 kinds of entities, which can be deposit blocks, transfer blocks, and withdrawals. Now, in order to convince you of the 5 bytes on chain, let's look at the transfer block, which is put on the storage contract, which this is the biggest part. And it actually contains an L1 address of the aggregator, so 20 bytes. This extra data string is used for security reasons, such that you don't have, such that the aggregator will not postpone on posting your block. Then you have the authenticated dictionary, the senders who actually signed it, and an aggregated signature. And if you do the arithmetics, at which I'm very bad, you would obtain this information. But now notice that here, you rely on the size of how many senders you have, not on how many transactions you send. And this comes from 96 because you use BSL signatures. And now you can add compression. I will not go too much into details. You can add compression using a relayer contract. And if you, with the current version of the block size on L1, you get this number, right? And if it will increase, if you will have more space on the L1 blocks, you can reach this point, which is even more than how much Visa transactions you can support at the moment. But now what I want to get into is the magic behind the protocol. Because it seems, okay, but what happens with double spending? Who is doing the verification? A lot of paranoia can come up here, right? So the magic trick is a balance function, which uses a very nice algebraic structure called lattice ordered abelian groups. And you have to use this balance function when users have compute their balances or when you have to do, when the rollup has to do a withdrawal. Now, if you don't know what lattice ordered groups are, it's no problem. There are some algebraic structures that they are used in fuzzy logic, for example. Basically, you have a group such that you can do, you can add your tokens, but then you also have a lattice order such that you can compare tokens between them. But it doesn't have to be totally ordered. So you can have uncomparable tokens, and you don't care about that, right? And there are scenarios in which you can think. And then usually in a group, you have positive con and negative con. So obviously the balance of accounts, they always have to live on the positive con of the group. Now, the balance function and why does it work is the fact that you have to split the information between two parties. You can have the list, the history of the rollup. You can have all the blocks that have been added to the rollup contract, but without having a proof from a user side, you can't retrieve the state of the accounts, the balances of the accounts. So you need two pieces of information. You need a proof that comes from the user, and you need the history of the rollup that is on the L1 contract rollup, right? And a state will just compute this B here are just functions which says, okay, which is the, how many tokens each account has. And you have to compute this value, right? And in order to do this, you have to split it in two parts. First of all, you have to, if you have a proof, but you don't know anything about it, you can have partial information there, it can be rubbish, you don't know. And then you have the list of the history, right? So first of all, you have to extract a list of partial transactions from these two information. And after this list of transactions, you just apply a state transition function and you compute the balances. This is not optimal, but there is a version in which this can be faster, but I will not go into that here. But the trick is, because you are in a scenario in which you have partial information, the best thing you can do is just compute a lower bound of the balances, actually. And you reason against that, and you make sure that you don't withdraw more than this lower bound. So let's look at an example, right? Here, B0, it's a deposit block, and let's suppose Alice deposits 11 tokens in the rollup. Now, we have two transfer blocks, the yellow one in which Alice sends 7 tokens to Bob, right? So she will go through this transfer protocol, and she will get a proof from the aggregator. Let's call it P1. Now, let's construct a different transfer in which Alice now wants to send 3 tokens to Charles. So she will take a different proof from the aggregator, P2, and Bob will send 7 tokens to an L1 account. He's preparing to do a withdrawal. So that's P3. Now, if you look at their wallets, which are these proofs that they have to keep up with, Alice will will merge the two proofs, P1 and P2. Charles will do the same, while Bob will have the P1 received from Alice, and the P3 he receives from the aggregator. And now if you unfold this one, I know this is quite heavy, you don't have to go through all of it, but what I want to show is that, for example, if Alice will send her wallet to the rollup contract and wants to compute the balances of all accounts against the history that happened, this part here comes from the deposit. This part here comes from the second block in which she sends 7 tokens. And all of this part here comes from the last block in which she showed that, okay, I send 3 tokens to C, but in that block, B appears as well as a sender. But Alice has no information about the proof that Bob received. So we compute this as a partial transaction. We don't know anything what happened. We don't know what Bob did there. Alice doesn't know, and she shouldn't know, right? So we put this as bottom. It's like undefined. We don't know anything. And then when you start to compute the balance function, okay, it does naturally. So this is the this is the value of every account. And okay, for example, here we are expecting that, okay, here after computing the 3 transactions, Alice has 1, Bob has 7, and Charles has 3, right? And this is the source account, which is like the almighty account that is used for the rollup contract. But now, when you try to reason about the partial transactions of which you don't have enough information, and they don't know what Bob did, they will say, okay, I set the account of Bob to 0, and I will reason about this. And depending on how many blocks and how many entanglement you have in your blocks, you will get this part, right? Now, if you look at the information Bob has at this point, and you try to compute the transactions that come up there, so remember Bob had P1 and P3, right? So Bob receives 7 tokens from Alice, but then on the second transfer block, Bob has no idea what Alice did at that point, right? So here we have 2 partial transactions on what Alice could have done, right? But Bob knows, like, I want to send to this L1 account 7 tokens. I want to do a withdrawal. And you reason about this. And now the tricky part is, like, how is the double spending happening, right? And know that the withdrawal step ensures that the user cannot double spend the withdrawal, to withdraw the same funds twice or to overspend. And this is the very nice part of the mathematical behind the paper. And let's twist a bit the scenario. And let's imagine that at the end, Bob wants to send 9 tokens. Initially, he had just 0. Let's suppose he wants to withdraw 9 tokens, right? He wants to send to an L1 account 9 tokens, which obviously he doesn't have at this moment. And what happens if we go back and we do the same process, we compute the same balances, and at the end, the protocol at this point will just set the account of Bob to 0, but actually, because they use lattice order groups, they are taking the minimum available between the account. All the time, they reason about the lower bound, the minimum of the values that are possible to move. So it will take the infimum between what Bob had in his account and how much he wants to send. And all the double spendings are set like this. The protocol, this magic balance function, will set everything, will not allow you to overspend more than you want. And everything is just doing meets in lattices. And that's very beautiful. And there is a very nice part, because here it allows a partial transaction, right? It withdraws just 7 tokens because it is what he had in the balance, right? The protocol is so general that you can twist it, and playing with the balance function, you can obtain whatever design you want for your protocol. So I invite you to look at the white paper, look at our formalization, and see the beauty of the protocol. Now, obviously what I presented here, and I said from the beginning, for sure this design, the simplified design, lacks privacy, because by the proofs they receive, the users can see the accounts of other users, and that's not okay. But you can use ZK proofs for this, and that's fine, and nothing bad will happen. And then it's not super efficient because balance proofs are large and are expensive to compute on chain, and they have a very neat way of solving this problem. But I just wanted to show, to go to the lattice orders and show you how you can handle this. Okay, and please reach out to us if you have further questions. Thank you.
Thank you, Denisa. I think before we go for a break, we have time for a question. No questions? Okay, good. Thank you, Denisa.
Thank you.
And with that, we're concluding the session and have, I think, 15-minute break, 14? Yeah, better if you be there already in 10 minutes. So, thank you, everybody.
good. How about you?
Exhausting, but I'm doing it.
Yeah, you're doing it. 2 talks in a row.
Yeah. I had a workshop in the morning too.
3 talks in a row.
Yeah. And I have to go for a panel right after this.
Oh my gosh.
Yeah, that's
how
like
are
a
you doing
spear bit thing.
Oh gosh.
I don't know, I'm just doing it. I don't even know how I'm doing it.
I'm impressed.
And this is just day 1. Tomorrow we are hosting the World Computer Day.
Yeah.
So
more talks.
please come.
I will. More talks then.
Yeah. There'll be something going on. Someone is missing. Let's go. Okay, I've got to go talk.
Yeah, we're good.
It's at 3:10. Yeah, I guess you can like say something and hopefully people will reply.
Yeah, sounds good.
Should they put this up on the screen?
Yeah, that's a good point. We have the...
All right, we're starting Anto's Securing Crypto Economic Systems.
All right, we'll give it a minute, so let's people start trickling in, and yeah, let's get into it. All right, so my name is Ando Joseph. I work for this protocol, EigenLayer. I work at EigenLabs, the creator of EigenLayer, the protocol. I am a security researcher there. So what is EigenLayer? EigenLayer is a protocol built on Ethereum that introduced the concept of restaking. So we have since gone past just restaking, and what we do currently is shared security. So you can provide security and bootstrap networks built on this shared security. We call it programmable trust, and I will dive into what that is. One of the core problems EigenLayer is solving is bootstrapping decentralized infrastructure. So if you're a new L1, you know that it's really hard for you to get stakers, operators, and get them all to like run your software, right? So this problem has been solved by EigenLayer. So before we dive into restaking, we should understand what is staking, Ethereum staking, right? So a very high level of what Ethereum staking is, it looks something like this. You deposit 32 ETH into a deposit contract, it's pending for a while, and you run your validator, it verifies the blocks, and then your ETH becomes active on the beacon chain. If you follow all the rules, you get rewards for it. If you break any rules, you get slashed for it. So what is restaking? Restaking allows stakers who have already staked on the beacon chain to use that same ETH that is available on the beacon chain to secure additional networks. So how can we do that, right? We want you to set the withdrawal credential of your validator to a smart contract. And we have the smart contract called the EigenPod, which, so as a validator, you would set your validator's withdrawal credential to the smart contract. So we are able to slash for any actions that you may have carried out while you were validating any of these additional networks. So for example, if you are a bridge and you made a commitment to do a certain task, but you didn't, then when you withdraw from the beacon chain, your ETH would end up on the smart contract, and then we can slash for that particular amount, and then you will be able to withdraw the rest. So that is how restaking works. it is also capital efficient, right? When you bootstrap net new networks, you are splitting up capital. So if you want to like run your own L1, you have to have a certain amount of economic security backing it. But when you talk about the concept of shared security, with EigenLayer, you are sharing all that economic security among your AVSs. I'll dive into what those are. But you can see that it is a much better system, pooled security versus monolithic. So these are the 4 components of an EigenLayer marketplace. We have the consumers, which could be the roll-up users. We have the stakers who deposit funds to us, so that's really what economic security is. And we have the AVS developers, so something like a prover network, you could call that an AVS. And operators who runs these AVS, so something like Coinbase Cloud. So we have experienced good TVL growth. And these are some of the operators with different capabilities that are currently on EigenLayer. So if you have like a proven network, you can pick the operators with GPUs. If you are running a TE network, you can pick the operators with those capabilities. And yeah, this category just keeps growing, right? This is just a screen cap of like what we have right now. And we have about 18 of those on mainnet, 40 on testnet, and 100 plus in development right now. So a very high-level overview of what the protocol is before we dive into the exciting bits, which is slashing, which is a pre-release on DevNet right now. And we are very excited to share that architecture with y'all. So 30,000-foot overview. Stakers deposit their tokens onto a smart contract. Stakers delegate that capital to operators who would run this software, the off-chain software. So just like how Rocket Pool or Lido would work, you delegate your capital to an operator, and the operator runs the validator for you. So just like that, the staker delegates the capital to an operator, and operator runs the software. Now, there is a slashing contract. So what is a slashing contract, right? Imagine you are a bridge, and a bridge validator has to follow certain rules. So a slashing contract enforces those rules. So you can think of it as how Ethereum works, right? Ethereum has certain rules, like do not double sign a block. That is a rule that is enforced by the Ethereum clients. If you do, you get slashed. So just like that, you can write smart contracts that is a slashing smart contract, which verifies if you have committed a fault or not. If these faults are cryptographically verifiable, then it is easy to like write a smart contract. And you can use like fraud proofs, you can use CK proofs, like you can use many mechanisms, like even a Merkle proof to prove something. So it's completely up to the AVS how they design it, but we obviously want the slashing contract to be really secure. So please get all your audits when you write something like that. Okay, so we talk about programmable trust, right? So what is programmable trust? The amount staked, we call it economic trust. The geographic diversity, we call it the decentralized trust. And a lot of Ethereum validators also opt into running these AVSs. So they can make commitments like, when I get to propose my next block, I will include this specific transaction. And you can verify that on chain. So that is the Ethereum trust. So what can you do with programmable trust, right? You can build apps with commitments. So what are apps with commitments? The OG Bitcoin, there is a commitment. Only 21 million Bitcoins ever, right? And What is a commitment from Uniswap? Find the fair market price. And what is it from Aave? The lenders assures the lenders that borrowers were never under-collateralized. So we have Uniswap, Bitcoin, Aave, Polymarket, all of that today. And these are the technologies that underpin the services. But can we create an Uber competitor that makes a commitment like, I will never take more than 5% take rate? Can we do that today with what we have? This is really where apps with commitments can make a difference. So we have this analogy. We call ourselves the verifiable commitment cloud, and you can see why we are doing it. So at the staker, operator, and developer level, you can make certain commitments like we will not censor, we will not double sign. And these are at that AVS level, and then you can have app level commitments depending on the app that you're trying to build, right? So if you're Uniswap, I make an app level commitment to make sure I always have fair ordering and finality. And so you can see how it applies for Aave and Polymarket, right? Now, to have apps with commitments, you need a carrot and a stick. The carrot is the rewards. The stick is slashing. So we have rewards on mainnet already. So I will not be going into that. But what we don't have right now is slashing. So I'm really, really excited to say that we have slashing pre-release on DevNet today. So if you scan the QR code, you can find the GitHub repository, which is a pre-release. Things are going to change. But if you are excited, this is pre-audit. Things are going to change, but we are excited to put it out there. Play with it. And slashing is a two-part release. So the first one that we have on the DevNet is where the malicious operator's delegated stake is slashed and burnt. So the stake is burnt. And the V2, the malicious operator's delegated stake is slashed and sent to the harmed parties. So you can think of it as insurance. So we have a term here called StakeSure. That is the white paper that we put out, which talks about the insurance model on EigenLayer. So if you're interested, just Google that, and you'll find a nice white paper out there. So some key concepts with slashing. We introduced this term called operator sets. So operator sets is a grouping of operators who have been delegated ETH. So when I say ETH, it could be like any token because we accept any arbitrary ERC20s now. So when you see ETH, it could be like anything else. So who have been delegated these tokens by the stakers and are assigned certain tasks by AVS. So what are tasks, right? So imagine you are a prover network and you want to generate a ZK proof. So you can assume that it is a task, and this is a task that an AVS have to respond to. So operators run these AVSs, and the task is to generate a ZK proof for this data that is provided to you. So tasks are dispersed to these operator sets. And we have this concept called total stake. The total amount of ETH delegated to an operator is the total stake of that operator. And an operator set's total stake is the sum of all the operators' total stakes. So as a staker, I might choose to delegate to a solo operator, like solo staker, right? But you may choose to delegate it to the operator that is run by Coinbase or something. So the total stake that is delegated to an operator, right? That is really what we are talking about here. And unique stake. This is what is very different from our previous slashing model. operators allocate a percentage of their ETH or any token that an operator set is permitted to slash. So this unit of ETH can only be slashed by a single operator set at any given time. So you can be assured that multiple parties do not have claim to the same ETH. So you have like unique rights to slash a certain amount of ETH. So that is a guarantee that the protocol gives you with this new slashing model. And we call that unique stake. So this is what operator sets look like. You can see a staker has 300 ETH, and they have delegated 100 ETH each to like 3 operators, and they all run AVS1. And you can see that AVS1 has multiple operator sets, and operator 1 only has the operator set 1. Operator 2 and operator 3 is opted into both the operator set 1 and operator set 2. And you can see that some tasks are only allocated to operator set 1, and you can see certain tasks are only allocated to operator set 2. So B and C, task B and C is allocated only to like operator set 2. So this is a nice way of AVSs can have multiple operator sets with varying levels of total stake and unique stake. So it is very versatile, and you can use it depending on the task at hand. So total stake, right? So this is an operator 1 with the 100 ETH staked. So this is an example operator allocation of unique stake. An operator can allocate less than 100% of their stake. You can see that the operator allocates like 50% of their stake to AVS4 on operator set 5, and AVS3 gets 30% of their ETH, which is operator set 4, and operator set 3 gets 5%, and operator set 1 gets 0. So what that means is that an operator can run multiple AVSs, and out of all the stake that is delegated to an operator, they can choose to split the percent allocated to the operator sets, and that stake is uniquely attributable to that operator set. And as you can see here, this is how unique stake works. A unique stake is the amount of stake that is uniquely slashable by an operator set. So this is a combination of the previous slide and the slide after. You can see that AVSs have multiple operator sets, and there is unique stake allocated to operator sets. And you can use a combination of total stake and unique stake because they have different properties, right? Total stake is just like the sum. Like you can see that the total stake is a total amount of ETH delegated to an operator. And the unique stake is the amount of stake that you have unique rights to slash. So if you wanted to, for your AVS, you can choose a rule like I need 50% consensus on both total stake and unique stake. So these things have good properties. So total stake raises the amount that is required to attack your AVS, and unique stake also burns attackers' funds because that stake is uniquely attributable and slashable by an operator set. So by making a decision to like maybe have a 50% consensus on total stake and unique stake, you raise the bar for attack and you increase the damage to the attacker. So you can read a lot more about the slashing model in this blog post. So you can just scan the QR code if you are interested. So this is our new and improved slashing model. I know someone was trying to scan the QR code. Sorry about that. Got it. OK, so this is the new and improved slashing model. What is good here, right? The greater control over slashing risk, and you have guaranteed slashable stake. There is no more a need for a common veto committee, and you have permissionless onboarding of AVSs. And what are the risks and mitigations, right? So we have crypto economic attacks, AVSs with not enough security budget. Imagine your security provider pausing for an upgrade. What happens to the security of an AVS, right? So these are interesting things to talk about. We have this concept of an allocation delay within the protocol. This allows stakers to react before the stake becomes slashable in a new AVS, and this protects against malicious operators. We also have a deallocation delay, which prevents withdrawing stake immediately after malicious actions, so the stake remains slashable during this window. And it is one of the most important things. The cost of crime should be bigger, right? So if you do not have crypto economic safety, you will get attacked. And we will have insurance in the next upgrade. So it's fun to think about all the things that can go wrong when you have heard of insurance fraud in the real world, right? So this protocol becomes a lot more complex and interesting once you have insurance. And we cannot forget about Web 2 security. So we have docs. If you are an AVS developer, if you are an operator, please follow these best practices. And that's pretty much it. I have a lot more slides, but we are out of time. I'll be over there, so if you have any questions, I'll be taking those. And thank you so much.
All right, our next talk is going to be from Iron Blocks. It's about firewalling decentralized protocols by Aave.
Excellent. It works. Hey everyone, I'm Asaf from Iron Blocks, co-founder and CTO, and also from Venn. And we are going to talk about the Venn, the first Venn network, the first decentralized firewall for dApps and for chains. I'm also a former co-creator of Bencore, if you remember, since 2017. Faced the first DeFi hack that happened on 2018. Then we could block and saved more than $350 million, the biggest hack at that moment. And for the last 8 years, researcher and Web3 security architecture. And what the talk is about, we are going to talk about the missing block by our point of view in the Web3 security, the concept of on-chain firewall and security networks, and the test that we conducted for the security network. So just a little bit about the evolution of security in Web3. In the left side, we see the vulnerability zone. This is all the wide area that the exploiters can use to exploit protocols. In 2015, 2016, we didn't have a standard for security. 2017, the audits becomes a standard, and then the vulnerability zone becomes an error, but we still have a lot of hacks happening. 2021, the boom of DeFi, we have still a lot of value added to the blockchain, but a lot of hacks also. But when we have more tools like fuzzing, formal verifications, and more automated tools like static analysis, then the vulnerability zone becomes narrower. And in 2023, last year, something like that, we're starting to have a monitoring and incident response tooling as a standard for protocols. We see a lot of protocols taking these measures to reduce the damage to their protocols. And as we see it, 2025 and onwards going to be the on-chain firewall, the decentralized firewalls that are actually going to prevent hacks from happening to these protocols. And this is the state, the life cycle of a protocol when it's deploying to the blockchain. Of course, we have the build, the test, deploy, and then maintain. In each phase, we have the primary tools that are used to protect that phase, the build and the test. The audits and the formal verification and fuzzing and so on are used primarily for the build and the test phases. And we have front running, back running, as incident response, as monitoring in the state of after the deployment and the maintenance. And of course, we have immediate incident response and late incident response. Immediate incident response means that moving the funds and the liquidity from the exchanges, and later incident response is trying to track the funds and to get back some of them, maybe negotiate with the attackers. And we see that in very specific window, which is still open for the attackers to exploit, it still has no measures to prevent that. It's after the smart contract is deployed and until the hack actually change the state on chain. This is where we still have a window which is not protected. And a little bit about the lifecycle of an exploit, funding of the address that's going to perform the exploit, preparation, deploying a smart contract that is going to help with that, execution, and of course running away and hide. All of that can happen in one transaction, one atomic transaction, and can be from a private mempool. So the assumption that we take that it's going to surprise us and happen just like that in one moment, in one transaction. And we want to fill the gap that we saw previously, the gap, this window that the exploiters can take advantage of and block it from him the option to change the state. So what is on-chain firewall? On-chain firewall is some middleware, we call it a middleware, that's actually implemented inside the smart contracts of the protocol. It's a very simple one. It just add modifiers, for example, to the functions with the hooks before pre-execution hooks and post-execution hook. And each one of the hooks goes to the firewall and runs the policies. Each policy defines specific checks that are going to run, and the protocol can decide what logic it wants to use with that policies. If he wants to use that policy and that policy to work together, or that policy to work together, and so on. And this way, it can perform each kind of logic it wants to, for each kind of transaction. So each call that goes to the firewall will go to that, and it can decide which function it wants to enforce that on them and which or not. But we have still limitations in that approach also. We have a very limited context with the call function. We have only the parameters that the call got. We have the general global parameters that we have with the transaction, but we don't have the trace that we got before that. We don't have general data that we need, and so on and so on. So we're limited with the data that we have on-chain. We also have another limitation, which is very important. It's that if a detection system sits entirely on-chain, then the attacker can see that and, of course, try to bypass that, to think of a way how to go around that logic, and also to fork the chain to his computer and run as much as test as he wants. We can't, and the DApp can't know about it anything. And when he finds a way to slip in, then he, again, will surprise us and surprise the protocol. So it's a very critical limitation. And a lot of the detection logic is not feasible to sit on-chain. For example, AI models, or if we need some data that sits outside the chain, or if we need another states of a lot of other smart contracts on-chain, then it will cost a lot to the user, and some of that we just can't do on-chain. And this is where we combine off-chain capabilities with on-chain enforcement. So on the off-chain components, and we see here a more decentralized approach that we take, that each security logic connects to other security logics and sign their own voting about if the transaction is okay or not. So the transaction will go first to security validation with all of other operators checking with their own logic if the transaction is okay. Then it will go on-chain, or then it will go to the sequencer of the chain if the chain decides to implement it in the chain level, or any RPC that can implement it also. This is how the node itself, the off-chain part, actually works. The transaction goes into the inspection flow. Then it can use for the assessment external detectors. It can connect any detector, any logic. Every operator on the network can add their own logic, use other logics to check the transaction. He also sends the transaction to the other operators that sign their vote, and then aggregate all of that together with his own signature. We're using BLS for that, and sending the transaction. We will see that in this case, it will send the result to the user that sent the transaction in the beginning. And if it's connected to the sequencer, it will just go to the sequencer. This is how it looks on the client side. On the web application side, the user sends the transaction data, getting back a secured payload, actually the approval payload with his transaction data connected together. And then he signed all of that together and send it to the blockchain. If he wants to send it through a private mempool or through a regular node, he can do whatever he likes. And we can see here that the user, when he sends the transaction, it works just like estimate gas. When a user wants to send transaction to the blockchain, it first send to the node the transaction data. The node does estimate gas, tell him if he has enough balance, if the transaction is not reverting. return the transaction to the user sign it and send it to the node, so it works exactly the same. The user sends the transaction data to the security network and then gets the transaction that it needs to sign. We conducted a test that it's kind of a POC, but more of a proving before go to production POC. We took something like 22 months of Ethereum, and in the future it's going to be a lot more months, and not just Ethereum, but also other chains. We took 22 months of Ethereum since January 2023 to September 2024. It has something like 60 or 70x inside the time frame. And the goals that we have for that test is to see that we actually can do prevention, which is the first one, most important thing. We need to keep the user experience. If it's totally disruption the user experience, then we didn't do nothing because no one would use it. And of course, decentralization. It must stay decentralized. And without that ethos in our test and in this system and approach, no one will use it. So let's start with what everything means. Prevention means that the false negatives, and false negative means when a malicious transactions comes to the network, we need to detect and decide that this is a malicious transaction. If we miss that, then the transaction will slip away. So the false negatives means that a malicious transaction comes and we didn't recognize that. So false negatives needs to be, for this test that we conducted, less than 10%. We don't think that at the beginning all the acts will be prevented, but most of them we try to prevent. User experience achieved by false positive means by false positives and response time. False positives mean that if a legitimate transaction goes to the network approve that and let it continue as usual and not blocking that. So false positives needs to be below 1%. And response time needs to be below 500 milliseconds, so the user won't feel any difference when he's trying to send a transaction. And decentralization achieved by multiple actors, that each one of them will run a different logic and vote by himself and so on. And modularity. The modularity is very important. The protocol should be able to decide which logic he wants to add to his firewall. He needs to decide if he wants to, he needs to be able to define if the firewall is working now or not working now. Or not working now, it's very important. Just a small introduction about what the hacks are, what the variety of hacks that this system needs to detect and protect from. So we have, of course, protocol logics like calculations that are going wrong, or something in the formula that it's not right and cause someone to take advantage of that. Price oracle attacks. Infrastructure means like something that happened in the front end of the application and cause the protocol to be hacked. Access control and codebug like reentrancy and so on. A lot of things that the system needs to detect. And this is the result that we got from our test that we conducted. False negatives below 5%. All of that is going to be public, by the way. It's not just in our closed system. You will see all the tests and all the results, and everything can be tested by anyone, everywhere. False negatives below 5%. False positives way below 1%. It's 0.004% of false positives, which is very low, and response time below 200 milliseconds. Most of the time, way below 200 milliseconds. So we actually achieved all of the things that we wanted to achieve, and we will talk about the decentralization also in a moment. So we proved that most of the exploits are preventable. With not just notify about the hack after it happened, and not just responding to what happened and reducing the damage. We can prevent the damage in most of the cases. The minimum interruption to the user experience, very important. In most of the cases, it will be totally transparent to the users. You won't even notice that there is a firewall behind that. Protocol integration, which is also very important, is very smooth. We have automated tools, CLIs, and everything that help him in a few seconds to implement the firewall and add it to its protocol and decentralization. We have a lot of security operators working with us to secure the network, top firms, top security audits firms, and top monitoring firms, and so on, that work together to create a decentralized network to protect the protocols. And that's it. Feel free to ask anything, and jump to the, of course, to the website, and we have a playground over there, and you can see all the documentation there.
Hi, I wonder, do you think there's any prospect for using this to detect transactions from drainers?
Well, I didn't hear.
Do you think there's any potential to use this to detect transactions not from exploits but from drainers?
Yeah, so we did that to demonstrate exploits for protocols. Some of the transactions there are actually phishing campaigns. So we also added them to the detection system and to detect them. So it's also against drainers. And any logic that the security operators can provide to their operators to detect phishing, we have chain patrol over here, for example, to detect phishing campaigns and so on, are also provided to the security network, and the protocols and the users can use that to protect themselves. Any more questions? Excellent.
All right, thank you for the talk. All right, next up we have a talk from DDoB about smart contracts for embedding from Markella.
Okay. Okay.
The talk doesn't actually start until 4.
Oh.
Yanis was asking, maybe we should start at 4. So like if people want to tune into your talk, they can follow the schedule.
Sure. Yeah, we can wait. Should I go sit and like?
I think you can hang out on stage. It's up to you, really. I just kind of hung out.
Okay, sure. Is the mic? So should we inform?
Yeah, I can.
Okay.
All right, this talk doesn't actually start until 4 p.m. So we're just going to take a short, like, 5-minute break and then start this talk at 1600.
No problem.
Smart Contracts to Embedding by Markella from DDob.
Hello, everyone. Do I sound okay, or do I have to speak louder? Good, okay. So today I'll be talking about smart contract to embeddings. What is that? Why do that? And how we did it, in case you're interested. So first, I want to start with this code from Jens Markdakis, DDob. You may know him as my boss. It was from DSS actually last year, and it goes something like, Web3 is a perfect playground for security tooling. It's the only opportunity one ever gets to have all the code open, all the state, all the past executions permanently recorded. And I wanted to include that because that is true, and it's a unique feature of the Web3 domain. Like, you have literally everything that's happening open, and if you know how to use that effectively, all the real-time data, you can do some pretty incredible security tooling. But that is also true for machine learning. You have all this information, all this data, and that's the perfect conditions to do machine learning applications. That's the main thing machine learning researchers are looking for, and it's the same not to use that in this domain. So I'll start with a little bit of background, so you all don't think I'm speaking Greek, but I'll try to keep it high level so you don't have to understand everything I'm talking about, and don't worry, there won't be any math. So the main thing I'll be discussing today is how to do similarity, smart contract similarity. We won't be talking about any other applications, so that's the reason we're talking about embeddings. The good thing about embeddings is that you can use them for similarity. So if you have two code snippets, and you can create some good embeddings out of those code snippets, and you get the distance between those vectors, that's a good metric for similarity. That, of course, depends on the quality of your embeddings. You may ask, why do I care about similarity? That's a good question. I'm sure you can think of other applications as well. But let's say you have a vulnerable contract with a specific code pattern, and you want to find similar ones. You may want to find similar contracts from a specific hacker, identify other MEV bots, and so on. This is an overview of what we'll talk about today. So first of all, I'd like to say that LLMs, I know LLMs and blockchains, a bunch of buzzwords, but they're useful. That's why they're buzzwords. So there's a lot of embedded knowledge in pre-trained LLMs. So if you could take something out of this talk, is that you can do a lot of applications with very little effort, and that's a good thing. The second thing is that you need to do it correctly in order to get results. So one very important thing is to adjust, for example, your input to match what a model may have been trained on. Otherwise, you're not going to get much out of it. And finally, OK, you get all those embeddings or whatever, and you may want to find, for example, which have the smallest distance. Don't do it brute force. Don't do all of the calculations. That's going to take forever. Use something like an approximate closest neighbors algorithm. And the good news is that you can probably get this for free. So TLDR, embeddings, high level, is just a way to represent data as a vector of numbers, as a list of numbers. That's code in our case, but it can be pictures, can be whatever. The simplest form of embeddings, you may all have heard of it, is one-hot vectors. So let's say we have 15 bits. Whenever one bit is 1, that's a different entity, that's a different thing. But as you can tell, that's not a great embedding. Good embeddings have to be semantically meaningful. What that means is, for example, if we use the example of word embeddings, that's a classic example in word2vec and glove, where if you get the vector for king and you add the vector for woman, you get the vector for queen. That means that embeddings have this feature that they embed relationships within those numbers. They may not always be linear like this, but that's the idea. Finally, it means that similar entities will be closer in the vector space. So for example, if you take the distance between king and queen, that will be smaller than the distance between king and rat, for example. Next, you should know that not all embeddings, good embeddings are learned. That's a different slide. So what that means is that you need to do training to get good embeddings. There's no magic algorithm that's going to give that to you. You need the statistical properties of a big corpus. As it's a special code in the NLP word, you shall know a word by the company it keeps. That means that words that appear in similar contexts will have similar meaning. So, however, not all embeddings are created equal. So we were speaking so far about word embeddings. So if you were to embed those two words, those words in those two sentences, I went to the bank to deposit money, and I went to the river bank. You will get the same embedding for the word bank, but it is clear that in those two sentences, it has a very different meaning. So what we want are contextualized embeddings. So that's where transformers and LLMs that you've all heard of come into play. High-level transformers have the attention mechanism. That's probably what you've heard about them. And the high-level idea is that it gives you access to all of the input. It gives you context. So if you get the embedding of a word from a transformer, it will have the meaning of the sentence kind of embedded into it. For example, in BERT, that's one of the initial transformer models, if you do the classic training task of mask language, which is you mask part of the input or a word of the input, and you tell the model to guess what that word is, the embeddings that the transformer creates internally for its word will be forced to learn the contextual information of the sentence. So that's how you get contextualized embeddings. You may be wondering why I'm talking about word embeddings. Well, if we treat code as a set of words, that's what we want to do. So we have a set of embeddings. How do we embed the whole sentence, for example? One way to do that, it was with the BERT model, for example. What they did was add an extra token in the beginning of a sentence, which then later the embedding of the model will get trained on a sentiment analysis task. So is the sentence positive or negative? What that achieves is that it teaches kind of the model to encode in this embedding the meaning of the whole sentence. So in a way, that's how we get our first sentence embedding. That's not the best way to do that. That's just an initial approach. A better way to do that is with Siamese networks. Siamese networks is just, you take the same model twice, you embed two sentences that you know are similar, you take the embedding of those sentences, and then you calculate the distance of those two, and use the distance in the loss function. What that means is that the model learns how to minimize the distance. So similar sentences will have more similar embeddings. And no, we didn't choose Siamese networks because of Thailand. So what are some of the challenges in creating smart contracts, creating embeddings out of smart contracts? Well, first of all, there are too many of them. So you have to keep that in mind. Just in Ethereum, there are tens of thousands of contracts deployed every day, in total to the millions of thousands of contracts. So your search has to be quick, and your embedding creation also has to be quick. Another problem is that we don't have source. maybe that's not entirely accurate. We have source for about 60% of contracts, but still a 40% is left without source. So doing similarity on the source code is not very reliable. And most interesting applications like malicious contracts or maybe MEV bots, whatever, don't really have an incentive to publicize their source. So there's even more reason to do so. Some other challenges are on-chain data, which are bytecode in its assembly code, is too low level, so it won't have very intricate information about the contract we want to embed. We have to take into account that if we're using LLMs, they have a specified size, so you can use very big inputs anyway. And finally, even though we do have a lot of data available, we don't have a lot of labeled data. That takes a lot of manual effort. So we either have to use out-of-the-box approaches from other domains, which means pre-trained models, or we have to creatively use what data we do have. OK, so then what are some of the things that we can do? Well, first of all, the compiled code is a good middle ground approach. It only depends on on-chain data, on bytecode. It retrieves high-level information like array operations, function calls, loops, if-else statements, stuff like that. And it looks like other object-oriented languages. So you may take advantage of models that are already trained on code. Another thing, another revelation we had is that a public function of a smart contract can be considered as a sentence of the contract. So it encapsulates a part of the functionality of a smart contract. So you can use that as your building block to do similarity. And if you combine that with a tree-shaking algorithm, which just means include underneath all of the private function calls, the function definitions of the private function calls of the public function, you have all of the information that's encoded in that function. A for-free approach is to use that as your input for a sentence encoder. That's going to give you a pretty good embedding because it has been trained to produce that. It may not be the best, like if you do a more fine-tuned approach, if you have, for example, a data set of pairs or whatever, that's going to be much better. But for example, in this case, because the code is transformed to something that the model has seen something similar before, so high-level code, which most LLMs have been trained on some extent during their initial training, are going to be able to benefit from transfer learning, which is when a model is able to perform well on a task that it hasn't been trained on, but is similar. Another idea, what if we use some of the data that we do have available in the blockchain? So one thing that we do know is that public functions are associated with a function selector. What that is just a hash of the function signature. That function selector is then used in a function selector piece of code, in the bytecode, which uses that hash to call the appropriate public function. In that way, you can build a data set of public function selectors and names, and then reverse engineer the names for contracts that don't even have verified source. That allowed us, at least, to build a labeled data set of decompiled code and name of this function in this decompiled code. As you can imagine, having the name of a function tells you a lot about a function. If I tell you these two functions have the same name, you're going to guess they do similar things. So we thought, well, what if you train an LLM to predict what the name of a public function is going to be based on the decompiled code, which already has a lot of information about it. And then use the internal state of that LLM as an embedding. Turns out that is a pretty good sentence encoding, as in public function. And the reason I mentioned earlier the CLS pooling is because it's kind of the similar intuition. It's asking the model to distill all this information to a descriptive function name. Finally, how you're going to actually run that. So you have all your code, you create all the embeddings, and you want to run a query. How do you do that? Well, don't use classic indexing. Like indexing algorithms for classic databases are not meant to be used on vectors. Use a vector store. The reason vector stores are better is because embeddings can be seen as nodes in a space, and the distance between those nodes are the edges of those nodes anyway. So you kind of create a graph that enables vector stores to use graph type of searches to do, for example, approximate nearest neighbor, and find closest embeddings much quicker than just doing all the distances with all the embeddings in your dataset. Also, the good news is that whatever database you're using right now already supports some kind of vector extension. All the major ones do anyway. And if you're building something from the ground up, you can maybe consider using a vector-focused database, which these are some of the examples, but there are many more. So we did this. How did it work? We deployed it September this year. We support most major chains that have EVM bytecode, and you can query any public function, and you can get results in, on average, less than 3 seconds. That's like the worst case I've seen. Funny story, this past fall, on our company retreat, a few weeks or something after we deployed our feature, we had the chance to use it in real life. When we discovered the vulnerability, fun story, we were doing a competition amongst our company for whoever finds a bug will win a PS5. We ended up finding the bedrock vulnerability, which, as you might have heard, was an infinite mint vulnerability. And that meant that 75 millions in dollars were at stake. The code that had this vulnerability was deployed on 8 different chains, and at least in one of those chains, the code wasn't even verified. That enabled us to try our tool in real time to find all the deployed code and ensure there weren't any other forks or pieces of code that used similar logic and had the similar vulnerability in the wild. If you want to try it, it is live now on our app, on our site, app.deobf.com. If you go on any contract, on any public function, we have a little button that says Find Similar. And if you click that, you will get something like this that shows you the similar functions and the addresses. And let us know if you have any feedback. Sorry, there's the last one. Almost forgot about that. So what we talked about today, there's a lot of information encoded in pre-trained LLMs, so take advantage of that. It's free. Representation matters. You have to think about what your input to your model looks like. And finally, don't use brute force to do your comparisons. There are much better things that are for free to use. And that is all. I think I'm a bit early. Yeah.
All right, any questions?
So
Thanks for your talk. Can you use this to, let's say you find a bug, you define it in some way, and then you can try to find a similar type of bug in different chains? Is this what you're doing?
So that's a good question, and that's actually a feature that I would like us to implement at some point. It wouldn't be hard. It would just be, you would have to submit that code. And it would be the same as doing a query as we have it right now, but at this point, no, we don't have that. You can find similar code with already deployed code. Our site is also a block explorer, so you can go to any deployed contract. So you can only use it on deployed contracts at this point.
Right, but like, if I find a piece of code and let's say it has a bug and I want to find similar code, I can do that?
Yeah, you can use the find similar. We support it on public functions. And if there is a public function that has a similar coding pattern, that's kind of a clone, I guess, of this function, there's a good chance you will find it.
And it queries?
Yeah, I've actually used it.
It queries like the blockchains you support now, and maybe you're going to add support, or which blockchains does it query?
So at this point, I think I don't remember all of the EVM-based chains we support. You can go on our site and see and check. We definitely have Ethereum, Binance, and Optimism. Right now, the feature doesn't work cross-chain, but that's a feature that's coming soon.
Okay, thank you.
You said the database is available. Is it open source? Can we download it?
It's not ours. Most databases have extensions that are free, yeah. And if you have an open source database, the extension is also open source. I don't know if asked.
Hey, thank you for the talk. I was wondering if you tried embedding not only the code snippet, but also maybe an LLM-based, like LLM-generated summary of the code, because I don't know how LLMs work with code instead of like natural language.
Yeah, that could be a good idea. Then there's a question of if an LLM could create a good summary of the code, maybe it can create a good embedding for the code. So it depends on the kind of code you will use. If it's something that model has been trained on, maybe it will do well. But they seem kind of like similar tasks, what you're explaining. So if you can do one thing well, I don't see why it wouldn't be able to do the other one as well.
And yeah, last one. You said you fine-tuned a model. Is that like compared to using OpenAI embedding model? Is there a super good advantage, or like is it like a slightly better?
Well, we don't use we have used OpenAI, ChatGPT. That's on projects, I think. It creates a summary, but we didn't use it for this. It's not super cost effective. And also, yeah, you can do a lot more things with your own model. You can create more lightweight models. You can do all sorts of things. So it's, I'd say, preferable to using that. But of course, it has its applications as well.
All right, I think that's all for questions then. I think there's a short break now, and the talks are going to start again at 4:40.
Thank you.
welcome everyone to this almost, I think it's a final session. It's nice that you're all still here. This is going to be a round of short lightning talks, 10 minutes each. And I'm going to be one of the speakers. First, for you, there's Shahar talking about obfuscation in drainers, or a specific drainer, I guess. Good luck.
All right, thanks. Yeah, we're going to be talking about deobfuscation of the agent drainer. We got 20 slides to go over in 10 minutes. So good luck to us all. I'm Shahar. I've been doing security for the past 15 years, past 3 years at Fireblocks, where I lead the product security team. We protect 200 million wallets for our 2,000 customers worldwide. And before we jump in, I also want to give a shout out to Matan from my team, whose work has been the backbone of a lot of this presentation. So hopefully you've heard about the engine drainer, but if you haven't, it's one of the most notorious drainer kits out there. It's been responsible for major losses, over $20 million for hundreds of thousands of victims. And it also recently merged with its rival. So it's just became stronger and more complex. So when you look at that, it's pretty obvious it's an ever-evolving, persistent threat in this industry. So we should study it. But when you want to study the code, you see that obfuscation is holding you back. And this is what made us jump into this research and understand how it's working and how we can remove it. So what's obfuscation? Obfuscation essentially is turning this piece of code into something that's really complex to understand, to read, and to get to the bottom line of. Why would you do that? From a malware developer perspective, from an attacker's perspective, you want to slow down, you want to get resilience for your malware. So you want to make reverse engineering hard, you want to slow down researchers, you want to limit detection capabilities, you want to drain wallets at scale, you want to make profit. Side note, there are some legitimate use cases for obfuscation, like protecting your IP rights. It's not all bad, but this case, it's really bad, and we want to tackle it. So why deobfuscate? Well, the exact opposite. We want to make reverse engineering and debugging really easy. We want to boost researchers. We want to make our detections better. We want to protect wallets at scale, and we want to present at DSS. So in terms of goals for our research, we have 3 goals here. We want to be able to understand the code. So we want to be achieving clarity, removing all the obfuscations, and have the code easy to read. But that's not enough. We want to be able to also execute and debug the code, because we do not believe in just static analysis. And finally, we want to leverage open source wherever possible, because we don't have to recreate and reinvent the wheel. So I'll start with the shout-outs of projects that have been important for our work. Couple first, Unminify and WebCrack are doing an amazing job with removing some of the obfuscation. We had to build on top of that, and I'll expand on this in a second. So Unminify removes the minification of JavaScript code, and WebCrack does some of the deobfuscation, removes some of the anti-debugging mechanisms. Lastly, Babel is an amazing framework to work with JavaScript code. You can think about this as a parser for JavaScript, so we don't have to write the entire thing ourselves. So jumping in. Looking at the Angel JavaScript kit, we see like any malware loader, the first stage is just loading a payload. It was minified code, meaning it had almost 1.5 million characters in one line. So we had to run it through Unminify, and when we ran it through Unminify, we got this. In the yellow box, you can see the encoded payload. This is essentially compressed with XZ and then encoded in base 64. When it's sent, this is what it does. So we did the reverse. We decoded and then decompressed, and we got this. So this is, as you can see, it's a lot of code, and you can maybe spot some computation going on, which is a good sign for obfuscation and unpacking going on, and you'd be correct. After unpacking, we see a code that's obfuscated with obfuscator.io, which is a very common JavaScript obfuscation website. It's protecting the core logic, so we want to go and break it. We tried a couple projects. We saw that Webcrack did a way better job in terms of keeping the code debuggable, so we can actually use it, which is one of our goals here. So we chose it, and we got into this. This is a code snippet out of 208,000 line of codes that we have. And Webcrack helped, but we can still see some funny struct and some indirect relations between different parts of the code. Specifically, we're going to identify 3 players here, which we're going to beat one by one. Call them E, D, and W. Okay, you can see on the green box where E is being defined, is being called and defined on top, and with D also some kind of indirect call to another function. So first thing we did, which allowed us to remove and remove E from the equation, was to use Babel, transform the code into AST, an abstract syntax tree, which essentially, again, parsing JavaScript, looking at the code in a logical way. You can think about this as sort of a smart find and replace. So whenever we see a mention, we can just replace it with the direct code or the direct string and have the code way easier to understand. Now, this is still, the end goal would be a clear, easy to understand JavaScript code, and this is not it yet, right? We can still see some funny things going on, some numbers, and the next target is D, okay? You can easily see that strings are missing, right? Like within JavaScript code, references to structs, references to JSON objects are dealt by strings, and that's missing here. So we realized this is a string mapping, essentially, and we tried to reverse engineer it. Now, that was hard. So instead, we did some pre-processing and then realized it may be easier to just run it. So we created a standalone version of that function and ran it through on a sandbox environment, as you should do with all malicious code. We ran it through the entire code and used the unpacking function to remove that complexity. You can see this is now way better, way easier to understand, but we still haven't gotten to our bottom line, which is to get code that is as clear as if you wrote it yourself. But we are getting there. And so the final round was to get both readability, perfect readability, and executability. We did run a round of AST simplification after the string fetching, which was like on dynamic execution. And finally, in order to debug it, we had another round, final round of Webcrack, which removed all the anti-debugging features that were present on the engine runner, which allows us to get to this code. Which meaning after a few weeks of work or 9 minutes of presenting, we got to realize this is actually just closes the pop-up, which is amazing. Which kind of shows you the benefit of obfuscating the code from an attacker's perspective, right? We had to work really hard to get to a function that really doesn't do anything important. But once we solved that, we solved everything. And now we can inspect the code, we can debug it while it's being run and while it's being trying to drain us. So because this is a research presentation, summary and future work, so we achieved executability and readability of the code like we wanted to. And if you want to dive in, I recommend first you'd look at Angel X, which is the latest version of the agent drainer. A good starting point is Blockhead's research, which is up on their blog. And also the on-chain command and control mechanism that Angel uses, which leverages smart contract storage in a cool way. Really recommend it to dive in. And that's it. Thank you for coming and listening. You can find us on Twitter and in person.
All right, thanks for your talk. Unfortunately, we don't have time for questions. I'm sure he'll be around. Next up, we have Chaim, and he'll be talking about a similar topic that we had a panel discussion on earlier today, namely the Web 2 to Web 3 transition, what the difference is, and yeah, good luck.
All right. Thank you. Hi, everyone. I'm Chaim Krasniker. I'm Chief Information Security Officer at Starkware. I've been working there for the past 2 years, also in Web3 for the past 2 years. I'm here to talk about challenges I had as a security officer and also as a security professional in Web2 coming to Web3. And the biggest challenge, I hope, will be to make this in 10 minutes or less, so good luck. About myself, I've been working 2 decades in cybersecurity. Started as a researcher, a malware analyst, and then later exploitation, mobile, web. Later on, manager of security engineering and research team. I like to keep hands-on and solve complex problems. That's one of the reasons I wanted to choose blockchain and Web3, and I'm very excited that I have done it. But when I came to Starkware and Web3, nothing prepared me for Web3 security mayhem. So many attack vectors, interesting assets to protect, and from Web 2, from Web 3, and I'll share a little bit about the threat actors, the threats, and what I think can be good for security leaders in protecting Web 3 and DeFi. So let's talk a little bit about Web 2 threat actors. The first, we have the script kiddies. They open command line, you know, and they think they are hackers. So these are not really a threat for us. This is one example, but we have also bug bounty hunters. Sometimes they can be also black hats, white hats. Usually issues that related are reported and being paid for. Sometimes they are deciding to do also be malicious. Next, we can have an example of an activist group like the Anonymous team, usually doing DDoS in Web 2, as far as I have seen. And essentially, I wanted to mention the insider threat in Web 2, which can be devastating up to an extent. When it comes to Web 3 attacks or threat actors, the malicious insider, the same one from before, has much more incentive because this is multi-million dollars and it can do a lot of damage, right? Compromise private keys, for example, when you have access to the company. Sometimes even worse project that can do rug pulls, like it can be related to a malicious insider or executives, or the entire project is malicious in order to pump and trick users, essentially stealing money. So this is another big problem we have in the industry. We have also the APT groups, organized crime, that are not behind nation state, that also decides to deal with crypto, which we need to deal with. And lastly, the most threatening threat is the nation state hackers like DPRK, Lazarus Group, which can be very, very, and have done a lot of damage. So my point is that Web3 threats are much more targeted and focused. They are behind social engineering mastermind. Sometimes they can, for example, have lateral movement. They hack a Twitter account or a Telegram account, and then they reach out to people that they know, trying to install or download something. Some recently even been hired as IT or dev, which is devastating because they can cause a lot of damage inside. They are highly skilled. They are usually patients, and most of them know how to mix and demix very quickly, thus allowing them to do money laundering. We talked a little bit about Web 2 hacks, and this is also a problem in Web 3 because Web 2 hacks are easy leverage into a key compromise. For example, if I manage to have a Trojan horse on a computer, we have seen recently a lot of attacks against multisig where Trojan horses can be used to steal or trick users into signing with cold wallet important on a fake data. We also have application security that we need to be taken care of, cloud security misconfiguration, and social media. So yeah, we don't have a lot of time, but there are so many threats to deal with in Web 3, also coming from Web 2. As a CISO, it is not the most relaxing job in the world because if the attackers have built correctly their way of exploitation, the execution is usually within minutes on chain. Ronin attack is one example of very strong social engineering where they stole more than $600 million. Wormhole, Wazir X more recently. So very, very big damage in minutes. So how do you prepare for that? On Web 2, my previous companies, you call an IR firm, they come, they take a mem dump, but we do not have the time for that, right? It's minutes. We don't have hours. We don't have days. We have to react quickly. And above all, after all, we also have governance and legal risk, which I know is a bit controversial in DeFi, but as a CISO, you also have to swim between the lanes and also keep due diligence and compliance wherever you can in order to support the users in various countries. So with all those threats and risks, what do we do now? What I did in every company that I come to do security, I usually do a risk assessment. Sometimes I use framework like NIST, like MITRE. So I had to adjust the threat actor and how it's bigger than usual in Web 3 than in Web 2 and their capabilities. There are a few minutes to effective immediate response. It's now a decentralized risk assessment versus centralized. It's not one entity. And it is not your typical CISO, SOC 2, or ISO 27001 checklist. It's not like you are going to install EDR, do some encryption, and you are safe. Maybe you are safe from SOC 2 or ISO 27001, but you are not really safe from Web3 hackers. So this actually presented an opportunity for me as a CISO to be practical, to focus on the important areas rather than just the checklist. And I tried also to navigate between constant changes in various countries and even due diligence by major vendors from different countries. Sorry. Yeah. So addressing Web3 risks. The first thing that you have to do in order to be prepared is to have an incident response plan ready with pre-built playbooks. Play a war game with your security team, imagine the worst case scenarios that can happen, and have a prepared list. Afterwards, build a real-time monitoring for those exact scenarios. How do you track them? There are many good Web3 security monitoring companies that you can work with and build those pre-built playbooks in order to detect them in real time. And you also have to have an emergency response for those exact pre-built playbooks. Those responses should also be decentralized by some kind of security council. Like if there is a risk of several companies that you work with report that there is a risk of lost money or steal asset, then you can maybe freeze the network, maybe pause, but you have to do that in a secure way without false positive, because otherwise this false positive can also become an attack vector. So this is challenging and also need to be decentralized. proactively navigate the rapid change in regulations as well. Other things you can do, war games, as been to in this conference already, SEAL is doing war games and other organizations and companies as well. Do it internally, do it externally, train your people with the IR plan that you have pre-built. Secure development, fuzzing, formal verification when you can, testing coverage, internal audits. And once you are ready, do the external audit and audit competition, which is also very useful. At the end, do an effective bug bounty program. Make sure that you scope the things that you care about, so you don't get, you can waste a lot of time if your bug bounty program is not scoped. Community and ecosystem involvement is highly important. For Starknet, we have a Starknet security community, and also it's important not just to have the community report to you issues and have a way to wake you up. It's also important to protect them, work with protect users from phishing, for example. We work with wallets, like our wallets, Bravos and Argent. We work with Blockade to protect users within the Web3 from phishing. So invest in protecting your users. And at the end, if you are hacked, make sure that you also follow the money solution so that you can return some of the funds. That's also important. So I'm running out of time. Summary, there is unique challenges in securing Web3, and coming from Web3, from Web2 to Web3, I learned a lot. I hope that other people will learn from that as well. Thank you.
Okay, thank you. So the next person to talk is me. So a little introduction there. The slides on there. Okay, I'll start by introducing myself for a bit. My name is Johan, and I've worked mostly in security automation and tooling, but I'm also an active bounty hunter. And sorry?
You have to use your laptop.
Oh, okay. Sorry. I need to set up my laptop. Okay, so I thought it would be fun to talk about some bug bounty horror stories, because usually what you see on Twitter is gonna be like your stories about, hey, I made $1 million bucks, holy shit, this bug bounty thing is really cool. But something you hear less about is all the cases where it goes wrong, although a lot of examples that I have today are actually probably going to be somewhat familiar. So there's going to be some spooky stories. And it doesn't work. OK, so this is the first one. It's a nice old one. This is not the way you do a bug report. So this is the Parity wallet. Someone was able to take over ownership and delete the contract, self-destructed. And they actually did so on mainnet and then reported the bug through a GitHub issue. I forget how many millions were locked because of this, but yeah, it's kind of scary if you wake up, see a GitHub issue, hey, I accidentally bricked your system. For the rest of the stories, I'm gonna try to not call anybody out for multiple reasons. In some cases, like it's hard to know the full story. And also, like, some of the ones are probably in the room, so, you know, not to make it too spicy. Everything should kind of be prefixed with this BACB. Bug bounties are great, but, you know, things happen. Let's go to the next one. Oh. Okay, so this one happened not too long ago. It's kind of buggy. Let me just move here. This one happened not too long ago. A kind of large exchange, Kraken, you might know it. There's a security company that found a bug, and to test the bug, they stole, I think, more than $3 million and reported it only a couple days, weeks after. I'm not sure about the details there, but yeah, that's got to be scary too, because as a exchange operator, suddenly a bunch of money is gone, and you don't know if it's like real hackers or not. So this is kind of like a lessons learned for white hats. Maybe don't just steal money, and maybe you should report the bug first. Another horror story, this is around a year ago. Protocol was hacked, 55 million was gone. It's actually in November, if anybody can guess which one it was. No? Okay, it was Kyberswap, and this is one of the most hilarious, like, white hat negotiations, in my opinion, because the guy had, well, first was like, okay, I'm tired, my demands will come tomorrow, so I hope he slept well. And then the day after, they got these demands, and he basically wanted the whole company. I don't believe they complied, but yeah. So I'm not sure if there's a lessons learned here, but yeah, I thought it was a fun horror story, because that's kind of crazy. Like, you get hacked, the hacker responds. Sometimes these negotiations actually work, but then, yeah, you get this demand. This is actually a super interesting story. I think it's a story I think happened 1.5 years ago. Someone found a bug in that was out of scope for a major protocol that's operated by a DAO. And their bug bounty, I believe, was managed by like this separate company. Because it was out of scope, they weren't able to like spend too much money on this bounty. So they agreed with the white hat that the white hat would suggest like an extra payout on the DAO's forum when it was proposed to pay out the base bounty. Now, this didn't go too well. And it's kind of a signal that bug bounties in DAOs are kind of difficult to do. So bug bounty discussions can be hard regardless of whether it's in a DAO or not. But if a DAO gets involved, it ends up even harder. So in this case, the DAO participants didn't have any information about the bug at all. And the conversation kind of went into a direction where there was name calling, or like the bounty hunter was called greedy, and eventually some people even suggested like lowering the bounty that was already agreed to. And I feel like the main takeaway here is two things. Like, make sure everything is set up well before someone reports a bounty, so that you don't need to fall back on this kind of system where someone has to go to your forums, where it's super difficult to agree on anything. And the second thing is, communicating with white hats is a PR problem. Like, you need to be aware of your image around this, because, yeah, derailing discussions on a public forum, it doesn't look good. Okay, so this one is even a little bit older. There was this white hat, found a bug, reported it, but the protocol didn't really respond within a day, I believe. So they were like, oh shit, I really gotta get this money safe, and they tried a white hat hack. Now, we all know that this can go really well, but in this case it went wrong because they were front-ran, and some money was lost. And I think here it's really important, if you want to be doing or execute a white hat hack, it's really important to be aligned with the team somehow. So either you've communicated with them, or in the best case scenario, it's them executing the white hat hack, not you, you're just helping. And you kind of only do this in the last case scenario, for example, the situations covered by the white hat safe harbor agreement. Okay, and this is another fun one that came up this year. This is a bounty platform that was blockchain enabled. And let me see. They put the titles of vulnerability reports and their severity on chain, which is not great because that kind of reveals a lot of information about vulnerabilities in systems that have a lot of impact. Lesson learned, don't do this. Beyond these, I wanted to point out that there's a lot of untold stories for both sides of the equations, for bounty hunters and projects. So what bounty hunters encounter a lot of the time is unnecessary delays, because protocols might not care too much about paying out when they already fixed the bug. You also have the fix and ghost, happens a lot. Fortunately, platforms like Immunify can take action like kicking people off a platform, but yeah, it doesn't always work. My favorite one, this happened to me once, is the security budget was tight, so they didn't have money to pay out the bug bounty. Great reason. This is an example, just I picked it from Twitter, from a couple, like last week, where someone reported a bounty, and then like a week after you go in, hey guys, have you had the time to look at this? And then, okay, we had time to look at it, and then it just takes long, a lot of the time. Conversely, there's also lots of problems for protocols that you're probably not aware of. There's like this fire hose of people that just want to make money by doing little work. So there's this thing called bug bounties. It's kind of insane. People just report seemingly random things. Hey, you're not following the best practice. And then saying, can I please have the money? And as a protocol, like you have to deal with this, and it's such a time sink. And of course, like the LLM revolution, and the problem here is LLMs can make really good sounding reports that are actually bogus in the end. So there's a lot of time drain from the project perspective, and unfortunately, in the communications between legitimate bounty hunters and projects, it can sometimes lead to some friction because protocols can be so used to grifters that they kind of go into the conversation in a semi-adversarial manner, or expecting the white hat to be somewhat adversarial. And this is kind of unfortunate. Of course, people get banned if they do bug bounties or if they use LLMs, but it's also something to be aware of. Like, it's good to know from both sides that everybody's kind of used to people doing things and making the process that much harder, that we can all maybe be nice to each other. Anyways, I kind of like bug bounties still, even though all these things happen. So I wanted to end with the statement that bug bounties are great. That's it for me. Is the next person? Okay. Let me quickly see. Oh, thank you. Okay, so next up is Valerian from Quantstamp, and he's going to talk about transient storage.
1, 2. Hi, I'm Valérian Calins. I work at Quantstamp, and today I will answer this question: is transient storage a transient trend? This is the plan for today, so let's start. The story of transient storage, or T-storage, started 6 years ago with EIP 1153. It was then introduced to the EVM with the DEFCON upgrade earlier this year. And as of today, you can use it in Viper and Solidity using opcodes or the dedicated keyword transient. It's cheaper than persistent storage. Each slot is identified by a byte32 identifier. And you can keep in mind that it has 2 scopes. First scope is at the level of the contract, because only the contract can access its own transient storage, and you need a dedicated view function to make it accessible to other contracts. Second scope is at the level of the transaction, because transient storage only exists until the end of the transaction, and at the end of the transaction, it is set back to 0. About the use cases, the EIP initially suggested 6 use cases, including transient reentrancy guards, tokens with persistent balances but transient approvals, and tokens where you can pay a fee to unlock the token transfers until the end of the transactions. But what about the usage in practice? So you can search for this on GitHub and browse the results. You will see that most of the results are clients or dev tools trying to support the DEFCON upgrade. And you will also see that actors such as Uniswap V4 or Balancer V3 are using it for flash accounting. And I listed other use cases below. As an adoption summary, most of the projects start using it with transient reentrancy guards. Then there is a common pattern for more complex use cases where you use transient context. Transient context, it's a set of transient storage variables that are used together in a consistent way. Most of the code bases also use dedicated libraries to manage their transient slots. And here is the Aussie transient slot .sol library as an example. And the adoption has been postponed in some cases. For instance, in one case, the rest of the code base was not ready for the Solidity compiler version 0.8.24. Let's move on to the security considerations. First, when you want to check if in a function the CI pattern is enforced, consider the persistent storage, but also the transient storage. The second one is when you target an EVM network, make sure that the transient storage is fully and correctly implemented. And for this, the tool EVM diff is very useful. Then beware of the concurrency between different slots, especially when you mix inheritance and delegate calls, because you can have some slot collisions or storage slot shifts. The last consideration is for the concurrency on the same slot. And here you can think about scenarios involving account abstraction, multisigs, multi-calls. And basically, it's if the same transient slot can be used by multiple use cases or for multiple actors, then there is a risk of unexpected behavior or of denial of service. Let's move on to the design patterns. The first one is transient read-only reentrancy guards. So sometimes by design you cannot avoid to expose some areas of your code to read-only reentrancies. And this pattern consists in temporarily locking related view functions before and after an area. So in this example, this contract has a storage variable A, a view function get A, and a function that is exposed to read-only reentrancy. I use the arrow to delimitate the start and the end of this sensitive area. For this pattern, you give an ID to the view function, here 42. You use a modifier, and at the start of the exposed reentrancy area, you will lock the view function with a dedicated function, and you will unlock it at the end of the area. The second one, I think it's the most important, is to safely manage the lifecycle of your transient context. So the rule number one is use single-purpose slots. In other words, make sure that the same slot is not used for separate use cases. And the second one is to avoid parallel executions for concurrent actors on the same slots. And here is a suggestion with a pseudocode. If you have a transient context TC and an actor Bob, first make sure that the transient context is not already locked or in use. Then you lock it for Bob, you sanitize all the slots of the transient context, you initialize it, then the context is active and ready to be used, but only for Bob. When you finish, you clear the slots and you unlock it from Bob. And the last pattern I will present you today is transaction level counters. So with this, you are able to make sure that a function cannot be called more than n times per transactions, or m times per transaction per user, or any more complex logic. The advantages is that it's cheaper than using persistent storage, and also it can prevent some hacks. For instance, if a min function is used in the same transaction that redeem function in a repeated amount of time. But it has also some disadvantages because it can limit or even break the composability of your protocol in that transaction. Think about account abstraction. And once again, thinking about account abstraction, maybe some transaction batchers could abuse the system and create a denial of service in their advantage. And this is the answer to the question. So no, we are not. Transient storage is not a transient trend. We are in a healthy early adoption phase, and transient storage is here to stay. It's well documented, useful, supported by most of the networks and dev tools. The main builders are already using it, and the security knowledge exists, but still has room for improvement. I added some resources if you want to learn more about this topic. And that's it for today. Thank you.
You want to say something? Cool. Okay. That was the last talk for this session and also the last session, which I think is why. Can I give my mic to him? Does it work? Let's try. Can you turn it off? And then a little bit of logistics. Here you go.
Can you put it somewhere?
Yeah. Oh, there's a mic. Cool. Thanks, everyone.
Okay. First of all, this is a pleasure for you to come here. So I have to first, I guess, I was asked by many of you, why and how DSS created. So first of all, it has been a while, but there are sort of two reasons in my mind. One, actually, this is what I love doing, is connecting domains. Actually, this is what I did in academia, sort of trying to understand how to connect. And here it's about connecting between the developers and the security researcher, which I think they are both good, but they can be better together. That's one reason. The second reason is purely selfish. I actually wanted to learn about this domain. So I thank you actually for teaching me. I have to pay you. I'll try. So thank you very much for teaching me, and hopefully this domain actually will grow more and understand. We heard today and yesterday about many talks. So that's about DSS. About you, I hope you enjoy. We are in the next day, hopefully, we're gonna publish a survey. Please answer, because we want to improve. Whether it will go next year to Buenos Aires or some other place, we need to improve and we want to improve. I think we already have some ideas and we messed out in some things, but we really want your help. So please, it doesn't take much. It takes 5 minutes. Please help us to improve. So now I have to go to the thank you part. So first of all, actually, one thing which is very surprising, we held it actually 3 times. We held it in Stanford. How many of you have been in Stanford? Probably not very much. Oh, few. 1, 2, 3. Great. So Stanford is an amazing place. It was an amazing place. It was amazing to start. Also, maybe it's surprising to you, but for us it was the cheaper because I'm academic and venue was for free. But Stanford was very difficult to, one of the things which is, and actually then we had it in France, and France was an amazing place. But I think the staff here are the best we have. So please give them thank you. I think they are all in the back. There is badge. So all of them, please, thank you. The staff, the people, really amazing. I don't know what you think, and maybe you'll see it in the survey, but we really, really feel we have been taken care of. We feel like the Aave is working. We feel like a lot of things. So thank you. That's the first thanks. The second thanks, and that's also surprising to me, is the speakers this year. The speakers this year are totally amazing, both for the talks and the workshop. Please give them big thanks. And not promotional. Things are very good. I mean, really, really I'm proud of people. We had these 3 years. The first year, then the second year, people say it started being promotional. Here I see it's going back. So that's great. So thank you all. Please thank them. Okay, thank you all, and try to think of something new in this field. And we also have the webinar, so you don't actually have to go to next year. And the webinar is not very selective. We are trying to learn about this domain. Anything which is useful, we have Nathan from the Ethereum funds. Please submit, and we'll make it. And it's not very selective. We actually want to hear. We heard about things like Eigenlayer, a lot of big protocol talking about it. Aave V4, Balancer V3, so all of it, a lot of protocol, and if you are doing something interesting in this domain and you want to use us, we will love it. So please, thanks to the speaker. The second thing is the steering committee. They're not listed here, but please thank them here. Many of them are still here. Some couldn't make it. Basically what happened, all the papers had reviewers. They have about three reviewers, and they help us, and we rank them. We did almost like an academic conference, so which basically we try to have, it's not really per review, but we try to make this content which is unique and new. And we want things to be original, and I think we did well. Actually, we didn't check. So thanks to the steering committee. Then I probably will forget. So we have all these people, all these companies. These are the best companies in Web3. These are the companies that supported us, and they supported us without getting anything. Well, they got some free tickets, but many of you got free tickets. So let's see them. So Electric Capital, it's a VC firm. Some of them are here. They are based in the Bay Area in New York. They are VC firm for basically developers. They are developer friendly. They, for example, support companies like Immunify. They are for DeFi. They are basically building things for developers. They also do the developer study. How many of you are familiar with the developer study? Few are. Okay, so they are doing some things about understanding this domain, so thanks them. And then we have QuantStamp. We see them in the talk later. They're actually one of the first security companies that have been around, and they actually did a lot of things. Thanks them. And then, of course, Aave needs no introduction here, but it's good to have such a protocol actually from day one, helping DSS with content and everything, so thanks them. Then we have Aptos. It's a newcomer. It's a layer 2. We have seen them. They actually contributed lectures. They contributed. They're also building the Move formal verifier. They are building the Move language. So thank them. We have Sigma Prime. Also, almost from the beginning, there's a security company, Mehdi. I don't know if he's here around, but thank them. We have Hexen, also coming new in security company, thanks them. We have Stellar. We had the speaker talking about storage. They are building Soroban. They are building the Rust implementation, thanks them. We have Eigenlayer, of course, very famous in this space, also coming from thank them. Open Zeppelin is a security company, build the libraries and everything, thanks them. Fuzzland, actually a new security company building Fuzzer. We heard about their talk. Tenderly, building the infrastructure, also leading a workshop, thanks them. Lido, also contributing from day one, liquid staking, need no introduction, but still thanks them. Starkware, we see in the last talk, building layer 2, zero knowledge, thanks them. Venn is actually building, we've seen Ironlock, maybe still in the workshop, sort of building the network of security. We have seen Asaf's talk this morning, thank them. By the way, these guys, I don't know if you know, they're also one of the earlier one in crypto. They did the first AMM in Bangkok. So they're actually coming from this field. Thank them, please. And then we have Spearbeat. They created a lot of content. They're doing bug bounty. They're doing Contina. They're doing now a lot of things. They're doing community. So thanks them. 12-bit, again, need no introduction, but they are also with us from the first one. Thank them. I don't know if Jocelyn here, Dan is not here. We have DDAP, Yanis. He's thanks also a company doing static analysis and security. Thank them. Trashblock, again, newcomer, thanks them. Ethereum France, supporting us for the second time, thanks them. And Ethereum is not here, but also they are supporting us for the second time, thanks them. Immunify, again, supporting us, again, thanks them, a bug bounty platform. Civic, also a security space, company in the space, thanks them. A Rare Skill is actually providing excellent education in this field and actually holding a workshop tomorrow. They're basically doing things about zero knowledge, so please thanks them. Sherlock, we heard Jack's talk. They are doing bug bounty platform, and thanks them. Community auditing. And asymmetric research is actually very interesting. They came very late. How many of you know about asymmetric research? So few of you, thanks. So asymmetric research is a new company, actually started from the Solana Foundation, and you've seen them actually. They have found one of the most interesting bugs in this space. So please check them. It's a very small team, but very prestigious, very interesting. So thanks them. I don't think they are here, but they wanted to support us. I guess they incubated in the job capital. So now I'm in the most pleasure part is to invite all the people that help us here to come up front, please. The volunteers, the V, which organized this event, Uri, which is actually without him, I'll be lost, Fiorella, which came in the last moment and saved us for everything. Thanks you. And all the volunteers, and I think Rajiv was here, but maybe I haven't seen Rajiv now. He's not around, no? Okay, so maybe just first, maybe we go up, no? No? Sure. I don't know if we can manage. Last time we did manage. Ali, right?
Yeah. Rajiv is going out for something else.
He's going out.
Yeah, it's gone out.
So no Rajiv, but it's fine. So maybe I don't want to embarrass you, but maybe just say a few words about you, everybody.
No, everybody will not.
Yeah.
Okay, I want to, not to talk about me, but to thank everyone for being here. It's a pleasure having you discussing security topics, DeFi topics. Like, you know, security is very, very important in the Web3 domain, and without security, we are totally wrecked. So I'm glad that we are organizing this and that you are attending and participating in this insightful discussion. So thank you for being here.
Lucas also has been with us
from the beginning, actually, from the Stanford.
So yeah, it's a pleasure to be part of this event again. Third time, seeing this grow since Stanford, since the first year, has been amazing. Participation has been growing, communities being building, active, so it's so great to see this growing, being part of this, and also thank the team, Securium, and also Spearbit, which I'm JSR at, so yeah, thank you. And let's keep securing Ethereum.
This conference, actually, all the context is just being shy. Yeah.
So I've been with DSS for the third year now, but this year was a bit different. It was pretty far away from the previous locations. We didn't have many local connections, and that's why we had to rely a lot on the community and on you, the volunteers, which did a tremendous job. So thank you for making this happen.
Leading this event, creating all the content, and leading it since 1 year.
Yeah, I'm almost since April, so I have been at DSS both from the attendee side and now from the organizing team side, so I have seen both sides. I'm really happy and excited to see everyone here, and actually having really, really high quality talks and people, and I want to thank everyone who bared with us all those months, and it's not only this team, it's also all this team for making that happen. Thank you.
So, hello. Thank you everyone for being with us. This is actually my first time in this summit, and I'm really proud and happy to be here. Thank you everyone for having us. Thank you.
Hi everyone, thank you for coming. Thank you for caring about security. It's good to see all these people, all these faces that by the time we're getting known by like each of us. And I would like to see you again next year. Glad to see you here and be here. Thanks.
Hi everyone. Thanks for coming. This was actually my first Web3 event, so I don't know what I was doing. So yeah, I hope I didn't do any mistakes. So yeah.
I just want to thank you all for being the heroes in the space and making it safer for the rest of us.
Great to work with a fantastic organizing team and the production teams. It's a great honor. Thank you.
First time at DSS. Thank you for organizing a fantastic event, V and Muli, and also thank you for everyone participating and being very friendly. Looking forward to be here next year also. Thank you.
Hi, so it's my first time as well, and I make all of their words my own. Thanks for the opportunity and thanks for being here.
Hi, everyone. Hi, everyone. Just wanted to quickly say thank you for coming, and you know, had a great time, and looking forward to next year.
Hello, everyone. Thank you all for coming, and it's awesome to see year by year how the best practices are improving, how tools are improving, and how entire security ecosystem is evolving and improving. Thank you.
So it's my first time as well, and thank you for giving me the opportunity, Uri, Muli, and V. And I believe I've learned a lot, and if there's any mistake, just I'm sorry for that, but yeah, I will improve. Thank you so much for joining.
Hello, this is my first time. I'm really happy to be attending this event, and I hope that all of us are glad and will still be there next year to help us out in any way you need us. Thank you.
Thank you.
Thank you, the speakers, and enjoy the rest of the event or going home. Thank you very much for coming.
Yeah, we have a happy hour with Halborn that starts in 20 minutes or so. Follow us. and see the information on the Telegram group. We would like to see you there.
Thank you so much.